Right now, somewhere in the darkness between stars, invisible predators drift through our galaxy. They have no light, no sound, no warning of their approach. And if one passed close enough to our solar system, we wouldn't see it coming until it was far too late. These are rogue black holes. Stellar corpses torn from their birthplaces, now wandering the Milky Way in complete silence. Scientists estimate there could be hundreds of millions of them out there, and we've barely detected a handful. The rest remain hidden, moving through space like cosmic ghosts, bending light around themselves, swallowing anything that crosses their path. What makes them truly terrifying isn't just their power. It's that we have almost no way to track them until they're already here. And when astronomers finally developed methods to spot these wanderers, what they found was deeply unsettling. Black holes form when massive stars collapse. We've known this for decades. A star 20 times the mass of our sun burns through its fuel, its core implodes, and gravity crushes everything into a point of infinite density. What's left behind is an object so dense that not even light can escape its pull. Most of these black holes stay where they formed, anchored in place by the remnants of their stellar neighborhood. But not all of them. When a massive star explodes as a supernova, the blast isn't always symmetrical. If the explosion throws more material in one direction than another, the newborn black hole gets kicked hard. Astronomers call these natal kicks, and they can launch a black hole across the galaxy at speeds exceeding 600 kilometers per second. That's more than 2 million kilometers per hour. Fast enough to escape the gravitational grip of its birthplace entirely. Once free, these objects become nomads. They don't orbit anything. They don't belong to any star system. They simply drift through the galaxy, following trajectories set by that violent birth moment, invisible and utterly indifferent to whatever lies in their path. Here's where it gets worse. Our galaxy has been forming stars for over 13 billion years. Millions of massive stars have lived and died in that time. Each one that met the right conditions created a black hole. And a significant fraction of those black holes received kicks strong enough to send them wandering. Do the math, and you arrive at a disturbing conclusion. The Milky Way should be filled with these things. Early estimates suggested tens of millions. More recent models push that number higher, potentially into the hundreds of millions. Picture that for a moment. Between 100 million and 400 million rogue black holes, drifting silently through the same space we occupy. Most are stellar mass black holes, between 5 and 50 times the mass of our Sun. Small by cosmic standards, but devastating by any measure that matters to us. And we can't see them. A black hole by definition emits no light. It's a hole in space where light goes to die. The only way we typically detect black holes is by watching how they affect their surroundings. If a black hole is pulling gas from a companion star, that gas heats up as it spirals inward, glowing brilliantly in X-rays before it vanishes beyond the event horizon. Binary systems like this are relatively easy to spot. We've cataloged dozens of them. But a rogue black hole traveling alone through empty space has nothing to feed on. No companion star. No accretion disk. No telltale X-ray signature. It's just a gravitational knot in the fabric of spacetime, moving silently through the void. For decades, astronomers assumed these objects were essentially undetectable. They were out there, sure, but finding them seemed impossible. Then someone realized we'd been thinking about the problem wrong. Even invisible objects reveal themselves through gravity. Einstein showed us this more than a century ago. Mass warps spacetime, and light follows those curves. When light from a distant star passes near a massive object, the object's gravity bends that light like a lens. If the alignment is precise enough, the background star appears to brighten temporarily as its light is magnified and focused toward us. Astronomers call this gravitational microlensing. The technique had been used successfully to find planets, distant stars, even other black holes in binary systems. But using it to hunt lone rogue black holes required a different approach entirely. You'd need to monitor millions of stars continuously, waiting for one to brighten in exactly the right way. The chances of catching such an event are microscopically small. The alignment has to be perfect, the timing has to be right, and you have to be watching that exact star at that exact moment. In 2011, a team of astronomers decided to try anyway. They pointed their telescopes toward the galactic bulge, the dense central region of the Milky Way where stars are packed close together. More stars mean more opportunities for alignment. They monitored the brightness of millions of stars simultaneously, searching for the characteristic signature of a black hole passing in front of them. For years, they found nothing conclusive. Hundreds of microlensing events, yes, but most could be explained by normal stars or brown dwarfs. Then in 2022, they announced something different. An event designated MOA-2011-BLG-191. The light curve was perfect. A star had brightened over several weeks, peaked, then faded back to normal. But the duration and shape of that brightening suggested something unusual. The lensing object wasn't a star. It was too massive and too dark. After ruling out other possibilities, the team concluded they detected a rogue black hole. Somewhere between 2 and 7 solar masses, drifting alone through the galaxy approximately 5,000 light-years from Earth. It had passed directly between us and a background star, briefly magnifying that star's light before continuing on its silent journey. This was the first time anyone had definitively detected an isolated black hole wandering through space. Not orbiting anything. Not feeding on anything. Just moving. And it raised an immediate question. If we found one, how many more are out there that we haven't found? The galaxy is enormous. 300 billion stars spread across 100,000 light-years. Even hundreds of millions of rogue black holes would be sparse in that volume. The chances of one passing close to any particular star are vanishingly small. But close is a relative term in space. A black hole doesn't need to hit something directly to affect it. Gravity works at a distance. If a rogue black hole passed within a few light-years of our solar system, we'd likely never notice. It would tug slightly on the orbits of distant comets in the Oort cloud, maybe nudge a few toward the inner solar system, but nothing catastrophic. Pass within 1 light-year, and the effects become more pronounced. Orbits destabilize. Long-period comets get redirected. The delicate gravitational balance that keeps our solar system stable starts to shift. Get closer than that, and things deteriorate rapidly. A black hole passing within the orbit of Neptune would gravitationally scatter the outer planets. Jupiter's orbit would shift. Saturn's rings might destabilize. The asteroid belt could be stirred into chaos, sending rocks careening through the inner solar system. Earth's orbit would change. Not immediately, not catastrophically in human terms, but enough to alter our climate over centuries. Enough to make our world unrecognizable. And if one passed within the orbit of Mars, we'd have months at best. Maybe weeks. The sun itself would be affected, its outer layers potentially stripped away as the black hole's gravity pulled at stellar material. Earth's orbit would become wildly elliptical or be ejected from the solar system entirely, flung into interstellar space to freeze in the darkness. The worst part isn't the destruction itself. It's the warning time. Or rather, the complete lack of it. Current detection methods only work when a rogue black hole passes directly in front of a background star from our perspective. By the time we detect that microlensing event, we're observing something that happened years or centuries ago, depending on the distance. The light we're seeing left that region of space long before we started watching. The black hole itself is already somewhere else entirely, continuing its journey along a path we can't predict. We have no early warning system. No way to scan ahead and spot an approaching threat. Gravitational wave detectors like LIGO can detect black hole mergers halfway across the universe, but a single black hole drifting through space produces no gravitational waves. It's silent on every wavelength we can measure, visible only through the brief distortion it causes when perfectly aligned with a distant light source. Astronomers are working on better detection methods. Upcoming surveys will monitor more stars more continuously, increasing the chances of catching microlensing events. The Vera Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every few nights, watching for anything that changes. That includes the subtle brightening caused by gravitational lensing. But even with better surveys, we're still looking at a reactive system. We find these objects after they've already passed, not before. And the galaxy is simply too large, too dark, too filled with empty space to monitor comprehensively. The number of rogue black holes out there almost certainly exceeds our ability to track them all. Which brings us to an uncomfortable probability calculation. With hundreds of millions of these objects wandering the Milky Way, and 13 billion years of galactic history behind us, what are the chances one has already passed close to our solar system? Or that one will in the future? The distances involved are staggering enough that the risk to any individual star system remains low over human timescales. But over millions of years, over billions, the odds shift considerably. And we're not just talking about direct hits. Even a distant passage could destabilize the Oort cloud, sending comets plunging toward the inner planets. Some researchers have suggested that periodic comet bombardments in Earth's history might be explained by exactly this mechanism. A rogue black hole passing through the outer solar system every few tens of millions of years, stirring up frozen debris and sending it inward. It's speculative, but it fits certain patterns in the geological record. And it suggests these invisible wanderers have been influencing our corner of space far longer than we've been here to notice. The galaxy's structure offers little comfort when you consider the mechanics. Rogue black holes don't travel in neat, predictable orbits like planets around a star. They follow paths determined by countless gravitational interactions over billions of years. A close encounter with another star system deflects the trajectory. Passage through a dense molecular cloud changes the velocity. The cumulative effect of these interactions creates something closer to a random walk than an orbital pattern. Which means prediction becomes functionally impossible beyond a certain distance. What makes this particularly unsettling is scale. We think of black holes as massive objects, and compared to everyday experience, they are. But in galactic terms, a stellar mass black hole is microscopic. The event horizon of a 10 solar mass black hole measures roughly 60 kilometers across. That's smaller than many cities. Now imagine trying to spot something that size, something that emits no light, against the backdrop of a galaxy 100,000 light-years in diameter. You're looking for a dark marble in an ocean at night. From another continent. The only reason we've detected any at all is because space isn't completely empty. Gas and dust exist between stars, thin beyond anything we'd call a vacuum on Earth, but present nonetheless. When a black hole moves through this tenuous material, it pulls some of it inward. That gas heats up through friction and compression, reaching temperatures where it emits X-rays. Not much. Not the brilliant accretion disks we see around supermassive black holes in galactic centers. Just a faint glow, barely detectable even with our most sensitive instruments. But here's the problem with using that detection method. It only works if the black hole happens to be passing through a region with enough gas to produce a visible signature. Most of interstellar space is far emptier than that. A black hole could pass within a light year of Earth, close enough to potentially affect the orbits of outer solar system objects, and we'd see nothing. No X-rays. No visible light. No radio emissions. Just gravitational effects we wouldn't notice until something started behaving strangely. The math on close approaches is genuinely disturbing. Researchers have calculated that a black hole passing within 50 astronomical units of the Sun, roughly the distance to the Kuiper Belt, would disrupt the orbits of trans-Neptunian objects significantly. Within 20 astronomical units, orbital perturbations would extend to the giant planets. Closer than 10, and Earth's orbit itself becomes unstable over timescales ranging from centuries to millennia, depending on the exact trajectory and mass involved. These aren't extinction-level events in the immediate sense. The black hole doesn't need to hit us to cause catastrophic problems. Orbital changes of even a few percent would alter Earth's climate dramatically. Seasons would shift. The length of the year would change. If the orbit became more elliptical, we'd experience temperature swings between perihelion and aphelion far more extreme than current seasonal variations. Glaciation cycles would accelerate or halt entirely. Ocean currents would reorganize. Weather patterns would transform beyond recognition. Life on Earth has survived worse. Mass extinctions punctuate the fossil record, some far more severe than what an orbital disruption might cause. But those events unfolded over thousands or millions of years. Ecosystems had time to migrate, adapt, or collapse gradually. A black hole passage could destabilize things within decades. Too fast for agricultural systems to adjust. Too fast for species to migrate to new climate zones. Too fast for human civilization to reorganize around new realities. The truly nightmarish scenarios involve closer approaches. If a rogue black hole entered the inner solar system, say within Mars's orbit, the effects would be immediate and overwhelming. Earth's orbit wouldn't just shift slightly. It would change fundamentally. We might be ejected from the solar system entirely, flung into interstellar space along a trajectory determined by the exact angle and speed of the encounter. Or we might fall inward, spiraling toward the Sun over a timescale of centuries. Either way, Earth as a habitable planet would end. Ejection means freezing. Without the Sun's heat, surface temperatures would plummet to near absolute zero within years. The atmosphere would condense and freeze, falling as snow that would eventually cover the entire surface in a layer hundreds of meters thick. Oceans would freeze solid to their beds. Any life that survived would exist in deep subsurface environments, perhaps around geothermal vents, living off Earth's internal heat rather than solar energy. Human survival would require either impossible engineering or simply wouldn't happen. Falling inward carries its own horror. The journey toward the Sun would take time, but the end result is incineration. Earth's orbit decaying, bringing us closer to a heat source that already makes the equator brutal during summer. Temperatures would rise steadily. Oceans would boil away. The atmosphere would be stripped by solar wind. Eventually, the planet would be torn apart by tidal forces before ever reaching the solar surface, debris scattered across the inner solar system like a planetary corpse. The galaxy doesn't care about any of this. These events occur with statistical regularity across billions of star systems. Most stars will experience close encounters with rogue objects over their lifetimes. Some will be disrupted. Some will capture new planets or have existing ones stripped away. It's part of the normal evolution of galactic structure. We just happen to be conscious observers existing during a period when our particular star system hasn't experienced such an event recently. Recently, in this context, means within the last few 100 million years. The geological record shows no evidence of sudden orbital disruptions on that timescale. Earth's climate has varied, sometimes dramatically, but always within ranges consistent with predictable astronomical cycles. The Milankovitch cycles that drive ice ages operate over tens of thousands of years and result from subtle variations in Earth's orbital eccentricity and axial tilt. Not the kind of violent perturbations a black hole passage would cause. But absence of evidence isn't evidence of absence over longer timescales. Go back far enough, and the record becomes unclear. The early solar system was chaotic. Planets migrated. Giant impacts occurred. The late heavy bombardment around 4 billion years ago reshaped the inner solar system. Could some of that chaos have been influenced by a passing rogue black hole? Possibly. We have no way to determine that from current evidence. The gravitational signatures would have been erased long ago by subsequent evolution. What we can determine is frequency based on what we observe elsewhere. Studies of stellar velocities in our galactic neighborhood show occasional stars moving at speeds inconsistent with normal orbital patterns. Hypervelocity stars, traveling fast enough to escape the galaxy entirely. Some of these gained their speed through close encounters with the supermassive black hole at the galactic center. Others might have been accelerated by interactions with rogue black holes in the disk. The distribution of these fast-moving stars gives us clues about how often such encounters occur. The numbers suggest a close approach between a rogue black hole and a random star system happens perhaps once every few 100 million years within any given volume of space. That sounds reassuring until you remember we're talking about an entire galaxy containing hundreds of billions of stars. Multiply that out, and you get thousands of these encounters happening somewhere in the Milky Way right now. This moment. As you process these words, a black hole is likely disrupting a solar system dozens or hundreds of light years away. We'll never see it. Never detect it. Never know which star just had its planetary system torn apart. The speed at which these objects move creates additional problems for detection. Stellar velocities in our region of the galaxy average around 200 kilometers per second relative to the local standard of rest. A rogue black hole might be moving faster or slower, depending on its history, but it's in that general range. At those speeds, an object crosses 1 astronomical unit, the distance from Earth to the Sun, in about 2 months. It could traverse the entire solar system in less than a year. Detection, analysis, and response would need to happen within that window. Except we can't detect them reliably in the first place. And even if we could, what response exists? You can't deflect a black hole. You can't destroy it. You can't negotiate with fundamental physics. The only option would be evacuation, and evacuating Earth's population to somewhere safer runs into the obvious problem that there is nowhere safer within reach. Generation ships heading to other star systems would take thousands of years to reach destinations that might themselves be threatened by rogue black holes. Underground bunkers might preserve some fraction of humanity through orbital disruption, depending on severity, but only if Earth remains in a relatively stable orbit around the Sun. Ejection into interstellar space makes that impossible. The planet becomes uninhabitable too quickly for any bunker to matter. This is the situation we exist within. A galaxy filled with invisible threats following unpredictable paths at velocities that leave no time for meaningful response. The odds of a direct impact remain low over human timescales. Low enough that it doesn't make sense to lose sleep over it specifically. But the odds of an encounter somewhere in our cosmic neighborhood, close enough to affect our understanding of how stable planetary systems really are, sit much higher. The question becomes what kind of encounter would actually matter to us. Not just theoretically, but in ways we could measure or experience within human lifetimes. Start with gravitational influence at a distance. A stellar mass black hole passing within a few light years of the solar system wouldn't cause immediate catastrophe, but it would perturb the Oort cloud. That's the spherical shell of icy bodies extending roughly halfway to the nearest star, loosely bound to the Sun's gravity. Disturb that region, and you send comets falling inward toward the inner solar system. Not immediately. The journey takes thousands to millions of years depending on initial position and velocity. But once started, the process continues regardless of whether the black hole remains nearby. Historical impact records on Earth and the Moon show periodic increases in cratering rates. Some researchers have proposed these patterns correlate with the solar system's oscillation through the galactic plane, where stellar density runs higher. More stars means more gravitational perturbations. More perturbations means more comets get nudged loose. The mechanism makes sense even if the specific correlations remain debated. A rogue black hole passing through the Oort cloud would produce similar effects, just concentrated in time rather than spread across millions of years of gradual oscillation. The increased impact rate wouldn't sterilize Earth. Life has survived multiple impact events far worse than anything a perturbed Oort cloud could produce. But it would stress ecosystems, potentially triggering extinctions among larger organisms less able to shelter or adapt quickly. Human civilization, dependent on stable agriculture and infrastructure, would face serious challenges. Not extinction level, but enough to reshape societies and potentially set back technological development by centuries. That scenario assumes the black hole stays several light years away. Move it closer and effects intensify. At 1 light year out, roughly a quarter of the distance to Proxima Centauri, gravitational effects become more direct. The outer planets would experience measurable orbital perturbations. Nothing dramatic over human timescales, but enough to show up in precision tracking data. Jupiter's orbit might shift by fractions of a percent. Saturn's rings could develop new gaps or resonances as orbital periods change slightly. These aren't catastrophic alterations, but they'd be detectable, and they'd tell us something massive had passed nearby. The inner solar system would feel weaker effects at that distance. Earth's orbit wouldn't change noticeably within a single human lifetime. But over centuries, small perturbations accumulate. Climate patterns depend partly on Earth's orbital eccentricity and axial tilt. Alter those parameters even slightly and you change how solar energy distributes across the planet's surface. Ice ages have been triggered by orbital variations smaller than what a passing black hole at 1 light year might induce. Now bring it closer still. Half a light year. A tenth. At these ranges, we're talking about an object whose gravitational influence begins competing with the Sun's hold on the outer planets. Neptune and Uranus could experience significant orbital changes within decades. Their moons might be stripped away entirely, sent tumbling into new orbits around the Sun or ejected into interstellar space. The inner solar system would still remain relatively protected by distance and the sun's stronger local gravity, but relatively does heavy lifting in that sentence. At a tenth of a light year, maybe 3 months of travel time at typical stellar velocities, detection becomes theoretically possible through gravitational lensing. The black hole's gravity would bend light from background stars, creating a characteristic pattern of brightening and positional shifts as it moves across the sky. Dedicated surveys searching for such events could potentially spot it, given enough luck and the right observational geometry. But that requires the black hole to pass almost directly between us and cataloged background stars, and it requires astronomers to be looking at the right patch of sky at the right time with equipment sensitive enough to catch subtle lensing signatures. The odds aren't favorable. Even if detected, the warning time measured in months doesn't allow for much beyond observation and calculation. We'd watch it approach, model its trajectory, estimate its mass based on lensing strength, and project what effects it might have on planetary orbits. Then we'd wait to see if the models were right. If the black hole passes within the outer solar system itself, within Neptune's orbit, we've moved from theoretical concern to immediate crisis. At those ranges, orbital mechanics become chaotic in the technical sense. Small changes in initial conditions produce wildly different outcomes. Whether Earth remains in a stable orbit or gets perturbed into a more elliptical path, whether the perturbation is mild or severe, whether we end up closer to the Sun or farther away, all of this becomes sensitive to precise details of the black hole's mass, velocity, and trajectory. Run the simulation 1,000 times with slightly different starting parameters and you get 1,000 different results. Some show minimal impact. Others show Earth's orbit elongating enough to create extreme seasonal temperature swings. A few show ejection from the solar system entirely. The disturbing part isn't that ejection scenarios exist. It's that we couldn't predict which outcome would occur until the black hole was already here, moving through the system, its gravity actively reshaping orbital paths in real time. By then it's far too late for any response beyond documentation. Consider what ejection actually means. Earth doesn't crash into the black hole. It doesn't get torn apart by tidal forces unless the approach is extraordinarily close, within a few million kilometers. What happens instead is the planet gets gravitationally kicked, like a billiard ball struck at an angle. The velocity change might be only a few kilometers per second, but that's enough. Earth's orbital velocity around the Sun sits at about 30 kilometers per second. Add or subtract even a small fraction of that and you change whether the orbit remains bound to the Sun. Once unbound, Earth drifts into interstellar space. The Sun shrinks to just another bright star in the sky, eventually indistinguishable from the others except by position. Surface temperatures drop rapidly as solar heating cuts off. Oceans freeze within years. The atmosphere begins condensing as temperatures fall below the freezing points of various gases. Carbon dioxide snow falls first, then nitrogen, then oxygen. Eventually you're left with a ball of ice coated in frozen air, drifting through the void at several dozen kilometers per second relative to the galactic frame. Deep underground, residual heat from radioactive decay in Earth's core continues for billions of years. Hypothetically, life could persist in deep crustal environments or around hydrothermal vents on the ocean floor, sealed beneath kilometers of ice. These ecosystems already exist in darkness, independent of photosynthesis, powered by chemical energy from the planet's interior. They might not even notice the Sun's absence, at least not immediately. Surface life ends completely. Everything dependent on solar energy, which means everything humans need to survive, ceases functioning within months. No agriculture. No renewable energy. No ecosystem services. Survival would require moving underground with nuclear or geothermal power, growing food under artificial light, and maintaining sealed habitats indefinitely. The technical challenges are immense but theoretically solvable. What's not solvable is doing this for billions of people with no preparation time. Even if a fraction of humanity survived in deep bunkers or sealed cities, you've essentially ended human civilization as we understand it. The survivors would live in permanent artificial environments, cut off from any natural world, maintaining themselves through technology that must never fail because there's no outside to escape to. This is assuming the ejection is gentle enough to leave Earth intact as a physical body. A closer approach could generate tidal forces strong enough to cause massive earthquakes, trigger volcanic eruptions, or in extreme cases, literally crack the planet's crust. The threshold for tidal disruption depends on how close the black hole passes and how fast. A stellar mass black hole would need to come within a few 100,000 kilometers to tear Earth apart through tidal forces alone. That's close, closer than the Moon's orbit. It's unlikely but not impossible. What's more likely, if a rogue black hole passes through the inner solar system at all, is significant orbital disruption without physical destruction. Earth survives as a planet but ends up somewhere it wasn't before, in an orbit that no longer supports the climate patterns civilization developed around. Maybe the new orbit is more elliptical, creating extreme seasonal variations. Maybe it's slightly closer to the sun, triggering runaway greenhouse effects. Maybe it's farther out, pushing the planet toward permanent glaciation. Each scenario creates different challenges, some potentially manageable with advanced technology, others not. The fundamental problem remains unchanged. We can't predict these events with useful lead time. We can't prevent them. We can barely detect the objects responsible. And the consequences range from inconvenient to civilization ending depending on variables we can't control. So we exist in a galaxy where these objects drift through the dark, occasionally reshaping solar systems they pass near, and we have no systematic way of knowing where they are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance doesn't mean ignoring the problem. It means acknowledging what we can and can't control, and focusing effort on the things that actually matter within our capability to influence. This brings us to something slightly more optimistic but equally strange. What happens if we reverse the scenario? Instead of losing the sun, what if Earth captured a second one? Binary star systems are common in the galaxy. Roughly half of all stellar systems contain two or more stars orbiting each other. If our solar system encountered a wandering star under precisely the right conditions, gravitational interactions could theoretically bind it into a stable configuration. The newcomer would need exactly the right mass, velocity, and trajectory. Too fast, and it simply passes through. Too slow or too close, and orbital chaos follows. Let's assume the best case. A star roughly half the Sun's mass approaches from a perpendicular angle to the solar system's plane, moving at just the right speed to be captured into a wide elliptical orbit. The two stars settle into a configuration where they orbit their common center of mass every few thousand years, staying far enough apart that planetary orbits remain mostly stable. Even in this ideal scenario, everything changes. First, there's no longer a single point in the sky that defines day and night, seasons, or climate stability. Depending on orbital positions, Earth might receive varying amounts of total radiation throughout the year. When both stars align on the same side, the planet gets hotter. When they oppose each other, one might be visible during what used to be night, eliminating true darkness for months at a time. Ecosystems evolved under predictable light cycles would face immediate stress. Plants time their growth, flowering, and dormancy to seasonal patterns that have remained consistent for millions of years. Disrupting that rhythm doesn't just inconvenience agriculture. It destabilizes the foundation of terrestrial food webs. Animals navigate, hunt, and reproduce based on day length and seasonal cues. Migratory birds use the sun's position for orientation. Nocturnal species depend on darkness. Coral reefs synchronize spawning to lunar cycles and water temperature patterns tied to solar radiation. All of these systems assume one sun following a predictable path. The climate effects cascade through every layer of atmosphere and ocean. Earth's climate system relies on differential heating between equator and poles to drive atmospheric circulation and ocean currents. Those patterns exist because solar radiation arrives at different angles across latitudes and varies predictably through the year. Adding a second star, even one much dimmer than the sun, introduces new heating patterns that don't align with the geography. Jet streams might shift latitude or weaken entirely. Ocean currents that distribute heat globally could alter course or speed. The intertropical convergence zone, which drives tropical weather patterns, might oscillate unpredictably or split into multiple bands. Then there's orbital mechanics. Even if Earth's orbit remains stable initially, long-term gravitational perturbations from the second star would accumulate. Over thousands of years, Earth's orbital eccentricity might increase, creating more extreme seasonal variations. The axial tilt that currently gives us moderate seasons could begin precessing faster or shifting to new angles. Other planets face worse outcomes. Mars, already in a precarious position with thin atmosphere and marginal temperatures, could be pushed into an orbit that makes it even less habitable. Jupiter and Saturn, the solar system's gravitational anchors, would experience altered orbits that ripple through the entire planetary arrangement. The asteroid belt, currently stable in gaps maintained by Jupiter's gravity, could destabilize. Resonances that previously kept asteroids in safe orbits might break down, sending debris inward toward the inner planets. Impact rates could increase significantly over geological timescales. None of this happens overnight. A captured star doesn't immediately scramble planetary orbits. The changes unfold over decades, centuries, millennia. But they're directional. The solar system wouldn't settle into a new stable state identical to the old one. It would transition toward a different equilibrium, one that might not include Earth in the habitable zone. From a human perspective, even the short-term effects present serious challenges. Agriculture depends on predictable growing seasons. Water resources rely on consistent precipitation patterns driven by stable atmospheric circulation. Infrastructure assumes certain temperature ranges and weather extremes. All of that gets recalibrated when the fundamental energy input to the climate system becomes variable. And we're still assuming the best case where the second star approaches gently and settles into a distant orbit. More likely scenarios involve closer approaches that don't result in capture but still perturb planetary orbit significantly during the encounter. A star passing through the outer solar system would gravitationally scatter comets from the Oort cloud, sending them falling inward. Some would miss Earth. Some wouldn't. The impact risk would spike for thousands of years after the encounter as these disturbed objects crossed the inner system. Planetary orbits themselves could shift. Not dramatically, not instantly, but enough to matter. Earth might end up in a slightly wider orbit, reducing solar radiation and triggering gradual cooling. Or a slightly tighter orbit, increasing temperatures and accelerating ice melt. Either direction creates a planet humans didn't evolve on and haven't built civilization around. The probability of capturing a second star remains extremely low. Space is vast, stellar encounters are rare, and the specific conditions needed for stable capture are narrow. But stellar flybys, close enough to disrupt things without capture, occur more frequently on geological timescales. The Sun will experience multiple close encounters with other stars over its remaining lifespan. Most will pass without incident. Some won't. And this assumes we're only dealing with normal stars. What if the intruder is a white dwarf, a stellar remnant much smaller but incredibly dense? Or a neutron star, packing more mass than the Sun into a sphere 20 kilometers across? The gravitational effects scale with mass, not volume. A neutron star passing through the outer solar system would wreak havoc despite being physically tiny. These objects are harder to detect at distance because they emit little light. A white dwarf shines dimly. A neutron star barely radiates in visible wavelengths. By the time we noticed one approaching, it might be too late to do anything beyond calculating the consequences. The galaxy contains billions of stellar remnants drifting through interstellar space. Most are isolated, moving on predictable paths that won't intersect our neighborhood. But on timescales of millions or billions of years, encounters become statistically inevitable. The solar system will interact with other massive objects. The question isn't if, but when and how severely. We can model these scenarios mathematically. We can run simulations showing what happens to planetary orbits under various perturbations. We can calculate impact probabilities and climate shifts. What we can't do is prevent them or predict them far enough in advance to matter. That leaves us in an odd position. We understand the risks. We know the mechanisms. We can describe in detail what would happen under different conditions. But we can't defend against threats operating at stellar scales with energies and masses that make human technology irrelevant. This isn't fatalism. It's recognition that some problems exist outside our ability to solve. You don't build contingency plans for events that would end technological civilization because there's no point. Either the event doesn't happen and the planning was unnecessary, or it does happen and the plans don't help. What matters instead is understanding our place in a dynamic galaxy where stability is temporary and change is guaranteed. The solar system occupies its current configuration because nothing has disturbed it recently. That's not a permanent state. It's a snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. The Sun formed 4.6 billion years ago from a collapsing molecular cloud. It will continue fusing hydrogen for another 5 billion years before exhausting its core fuel and expanding into a red giant. Within that time span, the solar system will experience multiple gravitational encounters with passing stars, clouds of interstellar matter, and possibly rogue planets or stellar remnants. Most encounters will be minor. A slight tug on the Oort cloud. A tiny shift in planetary orbits too small to measure. Occasionally, something more significant occurs. A star passes within a light year, scattering comets inward. A molecular cloud drifts through the system, altering solar radiation through increased dust. A massive object transits nearby, pulling planets into new configurations. These are not hypothetical scenarios invented to frighten people. They're documented processes observed in other stellar systems and predicted by our understanding of galactic dynamics. We exist in a galaxy that doesn't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. Acknowledging this doesn't mean giving up. It means recognizing which problems require solutions and which require acceptance. We can't prevent stellar encounters. We can understand them, model them, and perhaps detect them earlier with better observation networks. That knowledge serves a purpose even if it doesn't change outcomes. Human time operates on scales measured in decades or centuries. Stellar mechanics operate on scales measured in millions of years. That disconnect creates a perceptual problem. We evolved to recognize immediate threats. Predators, storms, drought. Our nervous systems weren't built to process dangers that unfold over timeframes longer than civilizations exist. A star passing within 2 light-years over the next million years doesn't trigger the same response as something happening next week. But the physics doesn't care about our perception. Gravity operates continuously. Orbits shift gradually. What seems stable on human timescales reveals itself as dynamic when viewed across proper intervals. Jupiter's orbit changes. Saturn's rings evolve. The Moon recedes from Earth at about 4 centimeters per year. These aren't static objects frozen in place. They're participants in an ongoing gravitational negotiation that never stops. Now scale that up to galactic levels. The Milky Way contains 200 billion stars, most with their own planetary systems. Add brown dwarfs, rogue planets, stellar remnants, molecular clouds, and regions of concentrated dark matter. Everything moves. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion, where encounters between systems happen regularly across cosmic timescales. Our Sun orbits the galactic center once every 230 million years. During each orbit, it passes through different regions of the galaxy. Spiral arms, interarm regions, areas of higher and lower stellar density. Each environment presents different risks. Spiral arms contain more massive stars, which means more supernovae, more stellar winds, more radiation. They also contain giant molecular clouds that can trigger ice ages by blocking sunlight. Interarm regions are quieter but not empty. Rogue objects drift through these spaces. Stellar remnants. Planets ejected from their original systems. Objects too dim to detect until they're relatively close. The galaxy doesn't maintain clear boundaries between safe and dangerous zones. It's all dangerous given enough time. What varies is the probability and severity of encounters. Right now, the solar system occupies a relatively calm neighborhood. The nearest star, Proxima Centauri, sits 4.2 light-years away. That's far enough that its gravitational influence on our planets is negligible. The next closest stars are also comfortably distant. This configuration is temporary. Stars move at different velocities relative to each other. In about 30,000 years, a red dwarf called Ross 248 will pass within 3.2 light-years of the Sun, becoming our closest neighbor for a time. Then it will continue on its path and something else will take its place. These close passes happen regularly on galactic timescales. Most are harmless. A star passing within 5 light-years exerts minimal gravitational influence on planets orbiting another star. The effects are measurable in simulations but negligible in practice. Closer encounters are rarer but more consequential. A star passing within 1 light-year would perturb the Oort cloud significantly, potentially sending comets into the inner solar system for millions of years afterward. A star passing within half a light-year could affect planetary orbits directly, though the changes would be subtle unless the encounter was extremely close. The problem is detection. We can track nearby stars with current technology, but only the relatively bright ones. Dim red dwarfs, brown dwarfs, and rogue planets are much harder to spot until they're already close. Infrared surveys have improved our ability to find these objects, but gaps remain. Something could be approaching that we won't notice until it's within a few light years. By then, we'd have thousands of years to study it but no ability to change its trajectory. Altering the path of a stellar mass object would require energy expenditures far beyond anything human technology can produce. You can't nudge a star the way you might deflect an asteroid. The mass difference is too large. The energies involved too extreme. Even if we had millions of years to prepare, the engineering challenges would be insurmountable. Which brings us back to the same conclusion. Observation and understanding, yes. Prevention, no. We can map nearby space. We can identify potential threats decades or centuries before they arrive. We can calculate exactly what will happen during an encounter. None of that changes the outcome. It just means we'll know what's coming. There's value in that knowledge even without the ability to act. Understanding allows for preparation of a different kind. Not physical defenses, but intellectual frameworks. If we know a stellar encounter will destabilize the Oort cloud in 50,000 years, that information becomes part of how future generations think about long-term survival. Maybe it influences where deep space probes are sent. Maybe it affects how astronomical databases are maintained. Maybe it does nothing practical but satisfies the human need to understand our environment. That need is real even when it doesn't lead to solutions. We study supernovae knowing we can't prevent them. We model black hole behavior knowing we'll never interact with one. We map the cosmic microwave background knowing it tells us about events we can't influence. Knowledge has value independent of utility. Stellar encounters fall into that category. They're important to understand because they're part of the environment we exist in. They shape planetary evolution. They influence the long-term habitability of solar systems. They determine which configurations of planets remain stable over billions of years. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. A distant encounter might scatter some comets. A close encounter could reshape orbits. An extremely close encounter could eject planets from the solar system entirely. These aren't equally likely. The probability decreases dramatically as encounters get closer. But over billions of years, even low-probability events become near certainties. The Sun will experience multiple close encounters before it exhausts its hydrogen fuel. Some will be minor. At least one might be significant. The galaxy guarantees change over sufficient timescales. What it doesn't guarantee is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, the system reorganizes into a new stable state that might look nothing like the original. This has already happened to countless other systems. We observe planetary systems with highly eccentric orbits, planets too close to their stars, gas giants in locations where they couldn't have formed. These are signatures of past disruptions. Encounters with other stars. Planetary migrations triggered by gravitational interactions. Systems that reorganized after their original configurations became unstable. Our solar system shows signs of its own past reorganization. The NICE model suggests that Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions. They migrated inward and outward after formation, possibly triggered by encounters with planetesimals or resonances between their orbits. This migration would have scattered smaller bodies throughout the solar system, explaining features like the late heavy bombardment 4 billion years ago. If that model is correct, the solar system has already experienced major gravitational reshuffling. What we see now is the result of that reorganization, not the original configuration. Which means change isn't hypothetical. It's already happened. The question is whether it will happen again during the remaining lifespan of the Sun. Probability suggests yes. Timing remains unknown. The galaxy contains too many variables to predict specific encounters far in advance. We can calculate general probabilities. We can identify nearby objects and track their movements. We can model what would happen under different scenarios. What we can't do is point to a specific date and say this is when the next major disruption occurs. That uncertainty is permanent. It's built into the nature of galactic dynamics. Too many objects moving in too many directions with too many possible interactions. Even perfect knowledge of current positions and velocities wouldn't allow precise predictions millions of years ahead because gravitational interactions are chaotic. Small changes in initial conditions produce large differences in outcomes over time. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. The math doesn't allow exact long-term predictions even in principle. We're left with statistical models and probability ranges. Useful for understanding general patterns but useless for predicting specific events. That's not a limitation of current technology. It's a fundamental feature of how gravity works in systems with multiple interacting masses. Chaos isn't something better computers can solve. It's an inherent property of the equations governing motion. Which means we'll never have certainty about future stellar encounters. We'll have better observations, more detailed models, improved probability estimates. We won't have schedules. The galaxy doesn't operate on schedules. It operates on physics, which produces patterns but not predictability. Stars move through space according to gravitational laws that allow probability calculations but resist precise forecasting over timescales measured in millions of years. The Sun's journey through the galaxy has already lasted 4.5 billion years. During that time, it's completed roughly 20 orbits around the galactic center. Each orbit takes between 200 and 250 million years, depending on the Sun's exact distance from the center and the distribution of mass in the galaxy. 20+ complete circuits means 20+ passages through the spiral arms, dozens or hundreds of close encounters with molecular clouds, and countless interactions with the changing gravitational landscape of the Milky Way. The solar system survived all of it. The planets remained in stable orbits. Earth maintained conditions suitable for life across geological timescales. Whatever encounters occurred during those billions of years, none were catastrophic enough to eject planets or sterilize Earth. That's not luck. It's statistics. Most stellar encounters are distant enough to cause minimal disruption. The dangerous ones are rare. Over billions of years, the rare events that do occur tend to fall within a range the system can absorb without complete destruction. But survival of past encounters doesn't guarantee immunity from future ones. Each passage through a spiral arm resets the probability. Each orbit through the galaxy exposes the Sun to new potential interactions. The gravitational environment changes constantly as stars move through their own orbits, clusters form and dissolve, and the galaxy's structure evolves. What protected the solar system during previous orbits might not be sufficient during future ones. The distribution of stars changes. Regions that were once relatively empty can become more crowded as stellar populations shift. The Sun's current path through the galaxy might take it through denser neighborhoods than it experienced in the past. Or it might lead it into quieter regions. There's no way to know without detailed mapping of stellar trajectories across millions of years, which remains beyond current observational capabilities. One factor that does influence encounter probability is the Sun's vertical oscillation through the galactic plane. The Sun doesn't orbit the galactic center in a flat circle. Its path carries it above and below the galactic plane in a wave-like motion, crossing through the plane approximately every 30 to 40 million years. When the Sun passes through the galactic plane, it encounters higher stellar densities than when it's above or below. The plane contains most of the galaxy's visible matter, including stars, gas, and dust. Crossing through it increases the probability of close encounters simply because there are more objects present. Some researchers have suggested this oscillation might correlate with mass extinction events on Earth, proposing that encounters with molecular clouds or increased comet impacts occur more frequently during plane crossings. The evidence remains debated. Extinction patterns don't show clear periodicity matching the oscillation cycle. Even if a correlation exists, it would demonstrate that galactic position influences Earth's history, not that future crossings will necessarily produce similar effects. Each crossing involves different molecular clouds, different stellar configurations, different gravitational contexts. Past patterns don't predict future outcomes with certainty. Beyond stellar encounters, the Sun faces long-term changes in the galaxy's overall structure. The Milky Way is currently on a collision course with the Andromeda Galaxy. The two galaxies will begin interacting in approximately 4 billion years, with a full merger occurring over the following few billion years. During galactic mergers, stellar orbits get disrupted on massive scales. Stars that once followed predictable paths around their galactic centers get scattered into new configurations as the two galaxies' gravitational fields interfere with each other. The Sun will likely survive the merger physically. Galactic mergers don't involve stars actually colliding because the distances between stars are enormous compared to their sizes. Even when two galaxies interpenetrate completely, the probability of any given star hitting another star remains vanishingly small. What changes is orbital structure. The Sun's current orbit around the Milky Way's center will become meaningless as that center merges with Andromeda's center. The combined galaxy, sometimes called Milkomeda, will have a different shape, different rotation, different gravitational architecture. The Sun will end up in a new orbit around the merged galaxy's center, potentially far from its current position. That repositioning might place the Sun in denser regions with higher encounter probabilities, or in sparser regions with lower probabilities. The outcome depends on details of the merger that can't be predicted precisely. Simulations show general patterns but can't specify where individual stars end up. Too many variables. Too many gravitational interactions occurring simultaneously. The merger timeline presents an interesting coincidence. 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It will have exhausted most of its hydrogen fuel and begun transitioning toward the red giant phase. The Andromeda merger will commence around the same time the Sun starts expanding. Earth's fate might be sealed by solar evolution before galactic dynamics become the dominant concern. As the Sun expands into a red giant, it will engulf Mercury and Venus. Whether it reaches Earth's orbit remains uncertain and depends on exact mass loss rates during the expansion. Even if Earth's orbit isn't physically consumed, the increased solar radiation will vaporize the oceans and strip away the atmosphere long before the Sun's surface reaches Earth's position. By the time the galactic merger creates new gravitational dynamics, Earth will likely already be uninhabitable. That doesn't mean stellar encounters before then are irrelevant. Between now and the Sun's red giant phase, roughly 5 billion years remain. During that time, the Sun will complete another 20 orbits around the galaxy. 20 more passages through spiral arms. Hundreds more opportunities for close encounters. The probability that at least one significant encounter occurs during those 5 billion years is not negligible. What constitutes a significant encounter? Definitions vary depending on what effects you're measuring. For disrupting the Oort cloud and potentially triggering comet showers, encounters within 1 or 2 light years matter. For perturbing planetary orbits directly, encounters need to be much closer, probably within a few thousand astronomical units. For ejecting planets entirely, encounters likely need to approach within hundreds of astronomical units. Each category has different probabilities and different consequences. Oort cloud disruptions are relatively common on million-year timescales. Direct planetary perturbations are rare but not impossible. Planetary ejections are extremely rare but have definitely occurred in other systems. The solar system probably won't experience a catastrophic close encounter during the next billion years. Probably. That's the strongest statement physics allows. The galaxy doesn't provide guarantees. Observation programs continue tracking nearby stars, measuring their positions, velocities, and trajectories. As data accumulates, predictions improve for specific stars over limited time periods. Gliese 710 will pass within 10,000 astronomical units in about 1.3 million years. HIP 85605 might come within 16,000 astronomical units in 240,000 years. These predictions carry uncertainty margins that increase with distance into the future. A star projected to pass at 10,000 astronomical units might actually pass at 8,000 or 12,000 depending on factors not fully constrained by current measurements. The difference matters when calculating gravitational effects on the Oort cloud. Small changes in closest approach distance produce large changes in the number of comets perturbed. Even with improving data, predictions beyond a few million years remain probabilistic rather than deterministic. The galaxy contains too many objects with too many possible interactions. The Sun's journey through the galaxy continues. Right now, it's moving toward the constellation Hercules at roughly 250 kilometers per second relative to the local standard of rest. That motion carries it through neighborhoods where stellar densities fluctuate, molecular clouds drift, and gravitational influences shift. Over the next 100 million years, the Sun will move several thousand light-years from its current position. New stars will become neighbors. Current neighbors will drift away. The gravitational landscape surrounding the solar system will transform completely multiple times before the Sun exhausts its hydrogen fuel. Each transformation brings new encounter possibilities. Each possibility carries a probability that can be calculated but not eliminated. The galaxy guarantees that change happens. It doesn't specify when or how severely. Our solar system exists in a dynamic environment where stability is temporary and disruption is eventual. Not immediate. Not predictable in detail. But inevitable given sufficient time. That's the nature of gravitational systems with many interacting bodies moving through space. Chaos emerges from deterministic laws. Probability replaces certainty. Patterns appear but predictions fail beyond certain timescales. The Sun will continue orbiting the galactic center, crossing through spiral arms, oscillating above and below the galactic plane, encountering molecular clouds and passing stars. Most encounters will be distant and inconsequential. Some will perturb the Oort cloud and send comets toward the inner solar system. A few might disturb planetary orbits enough to measure. One might eventually be close enough to fundamentally alter the solar system's architecture. We can't prevent it. We can't predict exactly when it will happen. We can only observe, calculate probabilities, and understand that the galaxy operates on timescales where rare events become commonplace. The question isn't whether the solar system will experience future disruption. The question is whether it will happen during a time frame that matters to us. For the next few million years, probably not. Beyond that, certainty dissolves into probability, and probability suggests that eventually, something significant will occur. The galaxy has 400 billion stars moving through space. The Sun is one of them, following its orbit through a constantly shifting gravitational landscape. Every orbit brings new encounters. Every encounter carries probabilities. Given enough orbits, those probabilities converge toward inevitability. That's not pessimism. That's mathematics applied to gravity operating across billions of years in a galaxy that never stops moving. The galaxy we inhabit operates without regard for our presence. Rogue black holes drift through the darkness between stars, following paths set by violent births millions or billions of years ago. Hundreds of millions of them, perhaps more, scattered across the Milky Way like invisible landmines in a cosmic ocean. We've detected a handful. The rest remain hidden, detectable only through rare gravitational lensing events that require perfect alignment and extraordinary luck. Detection methods improve. Surveys expand. Observation networks grow more sophisticated. None of it changes the fundamental problem. We're looking for objects that emit no light, produce no radiation, and reveal themselves only by bending the light of background stars during brief windows of alignment. Even when we catch these events, we're seeing something that happened years or centuries ago. The black hole itself has already moved on, continuing along a trajectory we can't predict with useful precision. The mathematics of galactic dynamics allows probability calculations but resists exact forecasting. Too many objects moving in too many directions with too many possible interactions. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. Chaos emerges from deterministic laws. Small changes in initial conditions produce wildly different outcomes over time. We can model general patterns but can't predict specific encounters millions of years ahead. That uncertainty is permanent. It's built into how gravity works in systems with multiple interacting masses. Better observations won't fix it. More powerful computers won't solve it. The galaxy doesn't operate on schedules we can map. It operates on physics that produces patterns but not predictability. What matters is understanding our position within this dynamic system. The solar system exists in its current configuration because nothing has disrupted it recently. That's not a permanent state. It's a temporary snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. Change is guaranteed over sufficient time. What isn't guaranteed is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, everything reorganizes into a new stable state that might look nothing like what came before. This has happened to countless other systems. We observed the signatures in eccentric orbits, misplaced planets, and configurations that couldn't have formed naturally. Evidence of past encounters that reshaped entire solar systems. Our own system shows signs of reorganization in its past. the planets might not occupy their original positions. The late heavy bombardment 4 billion years ago suggests major gravitational reshuffling occurred. What we see now could be the result of that ancient chaos, not the initial arrangement. Which means change isn't hypothetical. It's already happened here. The question is whether it will happen again on timescales that matter to anything currently alive. Probability suggests yes, eventually. Timing remains unknown. The Sun will experience multiple close encounters with other stars, molecular clouds, and possibly rogue black holes before it exhausts its hydrogen fuel. Most will be minor. Some might be significant. One could potentially be catastrophic. The galaxy guarantees encounters over billions of years. It doesn't specify which ones will matter or when they'll occur. We can't defend against threats operating at stellar scales. We can't deflect a black hole or alter the trajectory of a passing star. The mass differences are too large. The energies involved too extreme. Even with millions of years to prepare, the engineering challenges would remain insurmountable. You can't nudge a stellar mass object the way you might deflect an asteroid. What we can do is observe, understand, and acknowledge which problems exist outside our ability to solve. Knowledge has value independent of utility. We study phenomena we can't influence because understanding our environment matters even when we can't control it. Rogue black holes are part of that environment. They shape galactic evolution. They influence which planetary configurations remain stable over billions of years. They determine, in ways we're only beginning to understand, which systems survive long enough for complex life to develop. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. The galaxy contains 400 billion stars moving through space, countless stellar remnants, molecular clouds, rogue planets, and objects we haven't cataloged yet. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion where encounters between systems happen regularly across cosmic timescales. Most are harmless. Some aren't. The difference comes down to distance, mass, velocity, and timing. Variables we can measure in nearby objects but can't predict far in advance for the galaxy as a whole. So we exist in a dynamic galaxy where invisible predators drift through the darkness, occasionally reshaping solar systems they pass near. We have no systematic way of knowing where most of them are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance isn't fatalism. It's recognition of what we can and can't control, and focusing effort on things that actually matter within our capability to influence. The galaxy operates according to physical laws that don't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. We're participants in that process, not exempt from it. Understanding that doesn't change outcomes. It just means we'll know what we're looking at when the galaxy reminds us that stability is always temporary.
Right now, there's something lurking 26,000 light-years away that's warping the fabric of space and time itself. This object contains 4 million times the mass of our Sun compressed into a region smaller than Mercury's orbit. We've known it existed for decades, but we only saw its face for the first time in 2022. At the heart of our galaxy sits Sagittarius A star, the supermassive black hole that anchors the Milky Way. Everything in our cosmic neighborhood, including our sun and the billions of stars around us, orbits this invisible monster. But calling it invisible isn't quite accurate anymore. Scientists recently captured an image that changed everything we thought we understood about the center of our galaxy. The story begins not with cutting-edge technology, but with a crackling radio signal detected in 1933. Karl Jansky, working at Bell Telephone Laboratories, was trying to track down sources of static that interfered with radio communications. He built an antenna system and started scanning the sky. What he found was completely unexpected. A persistent radio signal kept appearing from the direction of Sagittarius. It wasn't random noise. It wasn't interference. The signal was coming from space itself, specifically from the center of our galaxy. Jansky had accidentally discovered radio astronomy, and he pointed us toward one of the most profound mysteries in the universe. For decades, that radio source remained just that. A mystery. A bright spot on radio telescopes with no clear explanation. Scientists knew something unusual sat at the galactic center, but they couldn't see it, couldn't measure it, couldn't understand what it was. Then in 1974, Bruce Ballack and Robert Brown made a discovery that would eventually win others a Nobel Prize. Using the baseline interferometer at the National Radio Astronomy Observatory, they detected something remarkable. Within that larger radio source Jansky had found, there was a compact, incredibly bright component. Something small. Something intense. Something unlike anything they'd seen before. Robert Brown gave it a name that stuck. Sagittarius A star. The asterisk wasn't random. In atomic physics, excited states are marked with asterisks. Brown thought this radio source was exciting. He had no idea how right he was. Throughout the 1980s, evidence mounted. This wasn't just an unusual radio source. The emissions, the brightness, the compact nature of the object, everything pointed toward a single conclusion. A black hole. Not just any black hole, but a supermassive one, sitting right at the gravitational anchor point of our entire galaxy. But here's where it gets interesting. You can't actually see a black hole. Light can't escape it. So how do you prove something exists when it's fundamentally invisible? You watch what dances around it. Stars near the galactic center move in ways that defy normal explanation. They whip around an invisible point at velocities that should be impossible. Star S2, one of the closest stars to Sagittarius A star, completes an orbit in just 16 years. That might sound slow until you realize its orbit is elliptical, bringing it screaming past the black hole at nearly 5,000 kilometers per second. Scientists tracked S2 and other stars for decades. They measured positions. They calculated velocities. They mapped orbits with obsessive precision. What they found was undeniable. These stars were orbiting something with a mass of roughly 4.3 million suns, confined in a volume no larger than 17 light-hours across. Nothing else could explain it. No cluster of dead stars. No exotic form of matter. Only a supermassive black hole could pack that much mass into that small a space without collapsing into something even stranger. Reinhard Genzel and Andrea Ghez spent years on this work. 16 years of tracking stellar orbits. Thousands of observations. Complex calculations. Their teams worked independently, using different telescopes, different methods. They both reached the same conclusion. In 2020, they shared the Nobel Prize in Physics for proving Sagittarius A star is a supermassive compact object, and that a black hole is the only possible explanation. But proving it exists and actually seeing it are two different challenges entirely. The problem is scale. Sagittarius A star sits 26,000 light-years away. From Earth, it appears smaller than a grain of salt viewed from New York to Los Angeles. To photograph something that tiny at that distance requires a telescope the size of Earth itself. We don't have a telescope the size of Earth. We can't build one. Physics won't allow it. So scientists did something audacious instead. They built a virtual telescope using 8 radio observatories scattered across the planet, from Hawaii to Antarctica, from Chile to Spain. The Event Horizon Telescope isn't a single instrument. It's a coordinated network synchronized to within a fraction of a millimeter using atomic clocks locked to GPS time standards. When all 8 telescopes observe the same target simultaneously, their data can be combined to create an image with resolution 4,000 times better than Hubble. The technical challenges were staggering. Each telescope generated petabytes of data. Internet speeds couldn't handle the transfer, so hard drives were physically shipped to a central processing facility. The observations happened in 2017. It took 5 years of calculations to process the data into a single image. On May 12, 2022, the world saw Sagittarius A star for the first time. Not the black hole itself, which remains invisible, but the glowing ring of superheated matter spiraling around it just outside the event horizon. A donut of light, bent and twisted by gravity so intense it warps spacetime into knots. The image shows a bright, thick ring roughly 52 million kilometers in diameter. That's larger than Mercury's entire orbit around the Sun. The ring isn't uniform. It has brightness variations, regions where matter glows more intensely as it accelerates toward the point of no return. What you're seeing isn't the black hole. It's the shadow of the event horizon surrounded by photons that barely escaped. Some of that light orbited the black hole multiple times before reaching us, bent around by gravity in ways that seem to violate common sense but perfectly match Einstein's predictions. The interior of that ring appears dark, not because nothing is there, but because any light crossing the event horizon can never come back. That darkness is the most direct view we have of the boundary between our universe and whatever lies beyond. Scientists compared this image to one captured 3 years earlier. M87 star, a supermassive black hole in a galaxy 55 million light-years away. M87 star is a monster, containing 6.5 billion solar masses, more than 1,000 times heavier than Sagittarius A star. It could swallow our entire solar system without noticing. The two black holes look nearly identical. Same ring structure. Same shadow. Same basic geometry. This tells us something profound about the universe. General relativity works. Black holes of vastly different sizes, in completely different environments, separated by millions of light-years, all follow the same rules. Gravity doesn't care about scale. But Sagittarius A star revealed something unexpected in follow-up observations. When astronomers examined it in polarized light, they detected organized magnetic fields spiraling from the edge of the event horizon. Strong fields. Structured fields. Fields that look remarkably similar to those around M87 star. This matters because M87 star shoots jets of matter thousands of light-years into space, powered by those magnetic fields. Sagittarius A star shows no obvious jets. It's quiet by comparison, feeding on material at a rate scientists compare to a human eating 1 grain of rice every million years. Yet those magnetic fields suggest Sagittarius A star might have a hidden jet. Something we haven't detected yet. Something subtle. The similarity to M87 star implies that strong, organized magnetic fields might be universal to all supermassive black holes, regardless of how actively they're feeding. Recent observations added another surprise. Sagittarius A star is spinning fast. Analysis of X-ray and radio data shows it rotating at roughly 60% of the maximum possible speed for a black hole. That spin warps spacetime so severely that the black hole's shape distorts from a sphere into something more like a football. This rotation creates a region called the ergosphere, where spacetime itself is dragged around the black hole. Nothing inside the ergosphere can remain stationary. Everything, even light, is forced to move in the direction of the spin. The faster a black hole rotates, the larger and more powerful this region becomes. The spin also tells us about Sagittarius A star's history. Black holes gain angular momentum by consuming matter that orbits in a preferred direction. The fact that our black hole spins so rapidly suggests it's been fed by accretion disks aligned in roughly the same plane for billions of years. But here's what makes Sagittarius A star truly fascinating for scientists. It's not just the closest supermassive black hole. It's close enough that we can watch individual stars orbit it. We can measure how gravity affects the flow of time near the event horizon. We can test Einstein's predictions under the most extreme conditions nature allows. When star S2 made its closest approach in 2018, scientists detected gravitational redshift. The star's light was stretched to longer wavelengths as it climbed out of the black hole's gravitational well, exactly as general relativity predicts. Time literally runs slower near Sagittarius A star than it does here on Earth. These observations push physics to its limits, probing the boundary between the quantum world and the cosmic one. And as our instruments improve, we're discovering that the galactic center is far stranger than anyone expected. In 2023, scientists using the Atacama Large Millimeter Array discovered something they weren't expecting. Space tornadoes. Massive vortices of gas and dust swirling around Sagittarius A star, invisible to optical telescopes but blazing in radio wavelengths. These aren't gentle spirals. They're violent cyclones of superheated matter, rotating at tremendous speeds, churning the space around the black hole into a cosmic storm system. The discovery changed how we think about so-called quiet black holes. Sagittarius A star may eat slowly, but it's anything but calm. The tornadoes stretch across light years of space, powered by magnetic fields and the black hole's rotation. They create turbulence in the accretion disk, stirring matter like a cosmic blender. This turbulence explains something that had puzzled astronomers for years. Why does Sagittarius A star flare so unpredictably? The black hole produces 5 to 6 major flares every day, plus countless smaller ones. Each flare is a burst of radiation, sometimes in X-rays, sometimes in infrared, sometimes in radio waves. The flares are erratic. No pattern. No predictability. Observations in 2023 and 2024 showed that the black hole looks different almost every time you observe it. One day it's bright in one wavelength. The next day, completely different. The space tornadoes drive this chaos. They create pockets of hot, dense gas that spiral inward. When these pockets cross the event horizon, they release bursts of energy. The timing depends on turbulence patterns that shift constantly. It's like trying to predict exactly when a specific wave will break on a stormy ocean. You know waves are coming, but the details are impossible to forecast. The James Webb Space Telescope caught one of these flares in mid-infrared light in 2022, the first detection at that wavelength. The flare lasted about an hour, bright enough to stand out against the background glow of the galactic center. What causes the flare itself? Material falling toward the event horizon accelerates to a significant fraction of light speed. Friction heats it to millions of degrees. At those temperatures, atoms are stripped of their electrons. The resulting plasma radiates intensely before vanishing forever beyond the point of no return. But here's what makes the recent discoveries truly unsettling. Sagittarius, a star, wasn't always this quiet. January 2026 brought a revelation that rewrote our understanding of the black hole's recent history. The XRISM Space Telescope, launched in 2023 with unprecedented X-ray resolution, detected something extraordinary while observing a giant gas cloud near the galactic center. The cloud was glowing in X-rays. Not from its own energy, but reflected light. Light that originated from Sagittarius, a star, centuries ago. The cloud acts as a cosmic mirror, showing us what the black hole looked like in the past. And what XRISM revealed is startling. Within the last few hundred to 1,000 years, Sagittarius, a star, erupted with ferocious intensity. An outburst that made it shine in X-rays 10,000 times brighter than today. 10,000 times. For perspective, that would make it visible across the entire galaxy, a beacon of high-energy radiation flooding the Milky Way's central regions. What triggered such an eruption? We don't know for certain. One possibility is that a large object, maybe a gas cloud tens or hundreds of times more massive than G2, fell into the accretion zone all at once. When massive amounts of material suddenly become available, the accretion disk can enter a different regime entirely. Instead of the slow, steady trickle we see today, the disk becomes thick, hot, and chaotic. Material piles up faster than it can fall in. The result is an outburst, a phase where the black hole feeds ravenously before settling back into dormancy. These outbursts might be common over long timescales. We're just seeing Sagittarius, a star, during a quiet phase, a lull between feeding frenzies that could last centuries or millennia. The XRISM data provides something no direct observation ever could. A window into the black hole's behavior before humans had telescopes. Before we knew black holes existed. The X-ray echo traveled through space for hundreds of years before reaching the gas cloud and bouncing toward Earth. It's like receiving a letter from the past, written in high-energy photons. This discovery raises an immediate question. If Sagittarius, a star, erupted that violently so recently in cosmic terms, will it happen again? And if it does, what would that mean for Earth? At 26,000 light-years away, we're safe from direct harm. The black hole's gravity doesn't reach us. Neither does the radiation from normal flaring activity. But an eruption 10,000 times more powerful. That changes the calculation. High-energy X-rays and gamma rays from such an event could, in theory, affect Earth's upper atmosphere. Not catastrophically. We're too far away for that. But measurably. Some scientists speculate that ancient cosmic events might be recorded in ice cores or geological layers, subtle signatures of radiation bursts from the galactic center. No one has found definitive evidence yet. But we're looking. The space tornado's discovery connects to another mystery. The stability of stellar orbits near the black hole. Recent observations using the ERIS instrument at the Very Large Telescope revealed that several dusty objects follow stable orbits around Sagittarius, a star, some for potentially thousands of years. These aren't normal stars. They're compact, dense structures, possibly young stars still forming or exotic objects we don't fully understand. Earlier theories predicted they'd be torn apart or consumed quickly. Instead, they persist. Their stability suggests that the region immediately around the black hole, despite the tornadoes and flares, maintains a kind of dynamic equilibrium. Chaos at small scales. Order at larger ones. This challenges our mental models. We tend to think of black holes as cosmic vacuum cleaners, consuming everything nearby. But Sagittarius A star demonstrates something more subtle. Less than 1% of material that enters the black hole's gravitational influence actually crosses the event horizon. The rest is ejected, blown away by magnetic fields and radiation pressure, or simply fails to lose enough angular momentum to fall in. The black hole is picky. It's surrounded by swirling matter, but most of that matter never gets consumed. It orbits, radiates, heats up, and eventually escapes or settles into stable configurations. The 2014 encounter with gas cloud G2 illustrated this perfectly. Astronomers predicted fireworks. A massive cloud, 3 times Earth's mass, was on a collision course with the accretion zone. Models suggested we'd see a dramatic brightening, maybe a sustained outburst lasting months or years as the cloud was shredded and consumed. Instead, nothing happened. The cloud passed through its closest approach. Sagittarius A star barely reacted. Some scientists called it a flop. But it wasn't a failure of prediction so much as a revelation about how black holes actually feed. The cloud stretched, distorted by tidal forces, but didn't dump its material into the black hole all at once. Most of it stayed in orbit or was blown outward. Only a tiny fraction, if any, crossed the event horizon. This tells us that accretion is a delicate process. You can't just throw matter at a black hole and expect it to fall in. The matter has to lose angular momentum. It has to cool. It has to navigate magnetic fields and radiation pressure. All of these factors act as barriers, filtering what reaches the event horizon. Sagittarius A star sits in the middle of a vast reservoir of potential fuel, but it's starving because the delivery mechanisms are inefficient. It's like being surrounded by food you can't quite reach. Which brings us back to the question of jets. M87 star shoots jets tens of thousands of light-years into space. Those jets are powered by magnetic fields anchored in the accretion disk and twisted by the black hole's spin. The fields act like particle accelerators, launching matter outward at nearly the speed of light. Sagittarius A star has the same magnetic field structure. The same spin. So where are its jets? One possibility is that they exist but are too faint to detect easily. The black hole's low accretion rate means less material available to fuel the jets. They might be there, just weak and hard to see against the bright background of the galactic center. Another possibility is orientation. If the jets point toward or away from us rather than perpendicular to our line of sight, they'd be much harder to observe. Or maybe the jets are intermittent. During quiet phases like now, they shut down completely. During outbursts like the ones RISM detected, they roar to life, pumping energy into the surrounding galaxy before fading again. This would make Sagittarius A star a variable jet source, active only during specific feeding events. If that's true, we might never see strong jets in our lifetimes. Or we might see them suddenly appear if the black hole enters another eruption phase. The uncertainty is part of what makes this object so compelling. We're watching a system that operates on timescales far longer than human civilization, trying to understand its behavior from a handful of snapshots. The magnetic fields themselves are a subject of intense study. They're not static. They twist, reconnect, and reconfigure constantly, driven by the motion of ionized gas in the accretion disk. When field lines reconnect, they release enormous amounts of energy, possibly triggering some of the flares we observe. This process, called magnetic reconnection, is the same phenomenon that powers solar flares on the Sun. But near a black hole, the energies involved are millions of times greater. The fields can also launch winds, streams of charged particles blown outward from the disk. These winds carry away angular momentum, allowing fresh material to spiral inward. Without the winds, the accretion disk would choke on its own rotation. Understanding these processes requires observations across the electromagnetic spectrum. Radio telescopes see the cool outer regions of the accretion disk. Infrared instruments detect warm dust and gas slightly closer in. X-ray observatories probe the hottest material near the event horizon. Each wavelength reveals a different part of the story. Combine them, and you start to see how the whole system operates, how energy flows from the outer disk inward, how matter heats and radiates, how magnetic fields shape and control the chaos. Sagittarius A star is a laboratory for extreme physics, accessible in ways no other supermassive black hole can match. And the more we learn, the stranger it becomes. One detail makes this especially puzzling: the black hole's spin. Sagittarius A star rotates at about 60% of the theoretical maximum speed. That's fast enough to drag spacetime itself into a vortex around the event horizon. This rotation warps the fabric of reality into what physicists call the ergosphere, a region where nothing can stay still. Even light gets swept along by the current. Spin matters because it determines how efficiently a black hole can launch jets. The faster it rotates, the stronger the magnetic fields can become, and the more energy can be extracted from the rotation itself. This process, called the Blandford's-Najek mechanism, converts rotational energy into electromagnetic radiation and particle acceleration. It's one of the most efficient energy conversion processes in the universe. Sagittarius A star has the spin. It has the magnetic fields. So why the silence? Maybe we're asking the wrong question. Instead of wondering why the jets are weak, perhaps we should ask what makes M87 star's jets so strong. That black hole weighs over 1,000 times more than ours. Its accretion disk is enormous, a swirling reservoir of matter extending billions of kilometers. Material pours in constantly, maintaining high densities and strong magnetic fields throughout the disk. Sagittarius A star's accretion disk is tiny by comparison. The material feeding it comes in fits and starts, never forming the kind of sustained, organized flow needed to power persistent jets. What fuel does arrive gets consumed quickly, leaving gaps between feeding events. During those gaps, the magnetic field structure might partially collapse, only to rebuild when fresh material arrives. This creates a feedback loop. Weak accretion leads to weak magnetic fields. Weak fields can't sustain strong jets. Without jets to carry away angular momentum, material can't fall in efficiently, keeping accretion weak. The system locks itself into a low-energy state. But that's not the whole story. In 2025, astronomers using the Atacama Large Millimeter Array discovered something unexpected: space tornadoes. Spiral structures in the gas surrounding Sagittarius A star, rotating at tremendous speeds. These weren't jets exactly, but they weren't ordinary accretion disk turbulence either. They were organized, coherent flows of material being flung outward by magnetic forces. The discovery changed how we think about quiet black holes. Even when not producing classical jets, they're far from inactive. Energy and matter move in complex patterns, driven by magnetic fields that constantly reconfigure themselves. The tornadoes might be failed jets, structures that start to form but can't quite break free of the disk's gravity. Or they might be a different kind of outflow entirely, one we hadn't recognized before because we were looking for the wrong signatures. What makes these tornadoes possible? The answer lies in magnetic reconnection. When field lines twisted by the black hole's rotation and the disk's turbulence intersect, they can snap and reconnect in new configurations. This releases energy explosively, heating gas and accelerating it outward. The process happens constantly throughout the accretion disk, creating pockets of intense activity embedded in otherwise calm regions. Each reconnection event is like a miniature explosion. Too small to see individually from Earth, but collectively they produce the flares we observe. Some flares are minor, barely detectable. Others reach X-ray energies, bright enough to stand out against the background radiation of the galactic center. And occasionally, very rarely, something much larger happens. This rhythm detection of that ancient eruption tells us Sagittarius, a star, is capable of violence we haven't witnessed directly. Within the last few hundred to 1,000 years, it's shown 10,000 times brighter than today. That level of luminosity requires a massive influx of material, far more than the black hole currently receives. Something had to deliver a huge amount of gas to the inner accretion disk all at once. What could cause that? One possibility is a stellar disruption event. A star wandering too close to the black hole gets torn apart by tidal forces. The debris forms a temporary accretion disk, much denser and hotter than normal. As this material spirals inward, it releases enormous amounts of energy before disappearing beyond the event horizon. The whole process might last months or years, producing a dramatic flare visible across the galaxy. Another possibility is the collision of gas clouds. The galactic center is crowded with molecular clouds, massive concentrations of hydrogen and dust. If two clouds collide near the black hole, the impact could compress the gas, causing it to lose angular momentum and fall inward rapidly. Again, you get a temporary surge in accretion and a corresponding burst of radiation. Or maybe it's something more gradual. Small disruptions accumulating over time, each one adding material to the accretion disk until it reaches a critical threshold. Then the disk becomes unstable, dumping its contents onto the black hole in a feeding frenzy. This kind of cyclic behavior is seen in other accreting systems, from young stars to white dwarfs. There's no reason black holes should be immune. Whatever the cause, the eruption left evidence scattered throughout the surrounding space. X-rays from the event traveled outward at the speed of light, eventually striking clouds of gas located thousands of light-years away. When those X-rays hit the clouds, they ionized the gas, causing it to glow. That glow is what SRISM detected. Not direct emission from the black hole, but an echo reflected off distant material. The clouds act as time machines of a sort. By measuring the properties of the reflected X-rays, astronomers can reconstruct what the original eruption looked like. How bright it was, how long it lasted, what kind of spectrum it produced. It's like finding a mirror that shows you an event from centuries ago, preserved in the light still bouncing around the galaxy. This technique, called X-ray echo mapping, only works because the galactic center is so densely packed with gas. In a quieter region of space, the X-rays would travel outward forever, never encountering anything to reflect them. But near Sagittarius, a star, clouds are everywhere, creating a natural network of reflectors. Each cloud captures a slightly different view of the same event, like witnesses standing at different positions around a crime scene. Comparing these different views reveals details impossible to see any other way. The geometry of the eruption. Whether it was symmetric or directional. How the radiation output changed over time. All of this information remains encoded in the echoes, waiting to be decoded by sensitive instruments like XRISM. The discovery raises a critical question. If Sagittarius A star erupted that violently just a few centuries ago, could it happen again? And if it did, what would the consequences be for life in the galaxy? The answer depends on how far the effects reach. X-rays from the black hole don't travel in all directions equally. They're beamed preferentially along certain paths, shaped by the geometry of the accretion disk and any jets or winds present during the eruption. If Earth happened to lie along one of those beams, we'd receive a much higher dose of radiation than if we were off to the side. At our distance of 26,000 light-years, even a major eruption probably wouldn't sterilize the planet. Earth's atmosphere and magnetic field provide significant shielding. But there could be subtle effects. Increased ionization in the upper atmosphere. Disruption of radio communications. Possible impacts on satellite systems. Nothing catastrophic, but noticeable. Closer to the galactic center, the story would be different. Stars within a few thousand light-years of Sagittarius A star could receive dangerous levels of radiation during a major outburst. Any planets orbiting those stars might lose their atmospheres or suffer mass extinctions. The region immediately surrounding the black hole becomes temporarily uninhabitable, sterilized by high-energy photons. This has implications for where life can exist in the galaxy. The galactic center, despite its abundance of stars and raw materials, might be too violent to support stable biospheres. Eruptions from the central black hole, combined with frequent supernovae from massive stars, create an environment of chronic radiation exposure. Life might emerge there, but it wouldn't last long. Our position in a quieter spiral arm starts to look less random. Perhaps there's a habitable zone in galaxies just like there's a habitable zone around stars. Too close to the center and radiation becomes a problem. Too far out and heavy elements become scarce. Somewhere in between lies the sweet spot where civilizations can develop without being periodically sterilized by their own galactic core. The XRISM discovery forces us to reconsider what we thought we knew about galactic habitability. For decades, astronomers assumed the habitable zone in galaxies was purely a function of heavy element abundance. You need metals to build rocky planets. You need carbon, nitrogen, and oxygen for organic chemistry. The outer regions of galaxies, where few stars have lived and died, lack these ingredients. Therefore, life should cluster toward the galactic center where generations of stellar nucleosynthesis have enriched the interstellar medium. But radiation changes everything. What good is having the right chemistry if periodic eruptions sterilize your planet every few thousand years? The galactic center might be materially rich but energetically hostile. It's like trying to build a house in a war zone. You have all the materials you need, but the environment keeps destroying your work. This realization reshapes our understanding of where to search for extraterrestrial intelligence. SETI programs have traditionally focused on sun-like stars regardless of their galactic location. The assumption was that any stable star with the right temperature could potentially host life. We're starting to see why that might be naive. Stars near the galactic center face challenges beyond just the occasional black hole eruption. The stellar density there is orders of magnitude higher than in our neighborhood. Close encounters between stars are common. Gravitational perturbations can disrupt planetary orbits, sending worlds careening into their suns or flinging them into interstellar space. Any civilization trying to develop there would face constant astronomical chaos. Then there's the matter of supernovae. Massive stars live fast and die young, exploding as supernovae that release enormous amounts of gamma radiation. Near the galactic center, where massive stars are abundant, these explosions happen frequently. A civilization within a few thousand light-years of the core might face a nearby supernova every few million years. That's not enough time for complex life to recover between events. The picture emerging is one of concentric zones. An inner region, extending perhaps 5,000 light-years from Sagittarius A star, where conditions are simply too violent for stable biospheres. Regular black hole eruptions, frequent supernovae, and gravitational chaos create an environment where life might spark occasionally but never endures long enough to develop intelligence. Beyond that lies a transition zone. Still dangerous, but with longer periods of calm between catastrophes. Life could potentially develop here, but it would face periodic resets. Civilizations might rise and fall repeatedly, never quite achieving the stability needed for long-term technological development. And then there's our region. About 26,000 light-years from the center, far enough that black hole eruptions are mere background noise. Supernova rates are low. Stellar encounters are rare. The galaxy provides abundant heavy elements without the accompanying radiation hazards. It's not that we're in a special place. It's that life capable of asking these questions can only arise in places like this. This brings us back to the original mystery. Why is Sagittarius A star so quiet now if it was so active just centuries ago? The answer lies in understanding what triggers these eruptions in the first place. Black holes don't decide to erupt. They respond to their feeding patterns. When a large amount of material suddenly falls toward the event horizon, it releases tremendous energy. The material doesn't fall straight in. It spirals, forming an accretion disk where friction heats the gas to millions of degrees. Most of the time, Sagittarius A star feeds on a thin trickle of material. Stellar winds from nearby stars. Diffuse gas from the interstellar medium. This steady diet produces the low-level activity we observe today. But occasionally, something more substantial wanders too close. A gas cloud. A disrupted star. When that happens, the feeding frenzy begins. The recent discovery of space tornadoes around Sagittarius A star adds another layer to this story. Using the Atacama Large Millimeter Array, astronomers detected massive rotating structures in the gas surrounding the black hole. These aren't tornadoes in the atmospheric sense. They're magnetic whirlwinds, channeling material toward and away from the event horizon in complex spiraling patterns. What makes these structures remarkable is their persistence. They exist even during Sagittarius A star's quiet periods, suggesting they're a permanent feature of the environment near the black hole. The magnetic fields threading through the gas create these rotating structures, and the rotation helps explain why so little material actually reaches the event horizon. Think of it this way. Material falling toward a black hole carries angular momentum. It can't just drop straight in because physics won't allow it. Instead, it has to lose that angular momentum somehow, and magnetic fields provide the mechanism. The rotating structures we observe are essentially cosmic drains, allowing material to slowly spiral inward while shedding its angular momentum through electromagnetic interactions. But here's what's fascinating. These same magnetic structures also provide an ejection mechanism. Not all material falling towards Sagittarius A star makes it past the event horizon. A significant fraction gets redirected, flung back out into space at high velocities. This creates a feedback loop. The black hole feeds, but it also pushes material away, limiting its own growth rate. The implications extend beyond our galaxy. If magnetic tornadoes are a common feature around supermassive black holes, they help explain why these objects grow so slowly. Sagittarius A star weighs about 4 million solar masses. That sounds enormous, but it's actually quite modest for a galactic center black hole. Some supermassive black holes exceed 10 billion solar masses. Why the huge variation? Part of the answer might be feeding efficiency. Black holes with stronger magnetic fields or more organized rotating structures might eject more material, growing slower as a result. Those with weaker fields or more chaotic environments might feed more efficiently, ballooning to enormous sizes. The details of the magnetic environment could determine the ultimate mass a black hole achieves. This connects to another puzzle: the relationship between black hole mass and galaxy properties. Astronomers have known for decades that there's a tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of stars in its bulge. Bigger galaxies have bigger black holes, in very predictable ratios. But why? The traditional explanation invoked feedback. As black holes feed, they emit radiation and drive winds that heat the surrounding gas, preventing it from cooling and forming new stars. This regulates both the black hole's growth and the galaxy's star formation, creating the observed correlation. The discovery of magnetic structures around Sagittarius A star suggests the process might be more complex. What if the magnetic fields themselves play a regulatory role? As a galaxy grows and more material funnels toward the center, the magnetic field strength increases. Stronger fields create more efficient ejection mechanisms, limiting how much material actually reaches the black hole. The system self-regulates through electromagnetic processes, not just radiation pressure. Testing this idea requires observations of many different black holes at various stages of activity. Sagittarius A star provides one data point, currently in a quiet phase but with evidence of recent violent activity. M87 star, the other black hole we've imaged directly, represents the opposite extreme. It's actively feeding, driving powerful jets visible across millions of light-years. Comparing the magnetic structures around these two objects reveals how different feeding modes produce different electromagnetic geometries. The polarized light observations of both black holes show remarkably similar magnetic field patterns despite the thousand-fold mass difference. This suggests that the basic physics governing these structures remains consistent across enormous scales. Whether you're dealing with a 4 million solar mass black hole or a 6 billion solar mass monster, the magnetic fields organize themselves in similar ways. That universality is what makes Sagittarius A star such a valuable laboratory. We can study it in detail precisely because it's relatively small and close. The phenomena we observe there likely occur around every supermassive black hole, but most are too distant or too massive to examine with the same precision. Our galactic center becomes a template for understanding black hole behavior throughout the universe. Which brings us to perhaps the most important question. What will Sagittarius A star do next? The X-ray echo observations prove it can erupt violently. The magnetic tornado discoveries show it's constantly processing material in complex ways. The flare observations demonstrate it's perpetually active on small scales. Put all this together and you have a system that's fundamentally unpredictable. Black holes don't operate on human timescales. An eruption that occurred 500 years ago is essentially yesterday in cosmic terms. The fact that we haven't seen another major outburst in recorded history means nothing. The next one could happen tomorrow or 10,000 years from now. We simply don't know enough about the triggering mechanisms to make predictions. What we do know is that monitoring needs to continue. Every observation adds another piece to the puzzle. The observational campaigns tracking Sagittarius A star involve technology operating at the absolute limit of what's physically possible. Consider what's required to watch individual stars orbiting the black hole. These aren't leisurely observations through a backyard telescope. They demand decades of continuous monitoring using the world's largest optical instruments, coordinated across multiple sites, operating in wavelengths blocked by Earth's atmosphere. The Keck Observatory in Hawaii and the Very Large Telescope in Chile have tracked these stellar orbits since the 1990s. That's over 30 years of accumulated data, capturing positions accurate to within milliarcseconds. To put that precision in perspective, it's like measuring the width of a human hair from 2,000 miles away. The stars themselves move at thousands of kilometers per second, completing orbits in timeframes ranging from a few years to several centuries. Star S2, the poster child of these observations, completes one orbit every 16 years. Astronomers have now watched it complete more than 2 full trips around the black hole. Each passage provides another test of general relativity, another measurement of the black hole's mass, another constraint on alternative theories of gravity. The data quality improves with every orbit as detector technology advances and analysis techniques become more sophisticated. But S2 isn't the speed demon of the galactic center. That distinction belongs to S4714, which screams past Sagittarius A star at nearly 8% the speed of light. Its orbit brings it to within 12 astronomical units of the event horizon, closer than Saturn orbits our Sun. At that proximity, relativistic effects become impossible to ignore. Time dilation, gravitational redshift, orbital precession. All the exotic predictions of Einstein's theory manifest in measurable ways. Tracking these stars requires adaptive optics, a technology that compensates for atmospheric turbulence in real time. Earth's atmosphere constantly shifts and warps, blurring astronomical images. Adaptive optics systems measure these distortions hundreds of times per second and adjust the telescope's mirror to counteract them. The result is images nearly as sharp as if the telescope were floating in space, revealing details that would otherwise remain hidden. The technical achievement becomes even more impressive when you consider the environment being observed. The galactic center is one of the most crowded regions in the sky, packed with millions of stars separated by distances smaller than our solar system. Picking out individual stellar orbits from this stellar traffic jam requires not just sharp images but sophisticated computer algorithms that can track specific stars across decades of observations. Those algorithms face a particular challenge. Stars occasionally disappear behind dust clouds, or their light gets confused with nearby companions. The tracking software must maintain identity across observation gaps, sometimes spanning years, while the stars continue moving along their predicted paths. Any error in identification corrupts the orbital data, potentially invalidating years of careful measurements. Beyond the stellar orbits, understanding Sagittarius A star requires simultaneous observations across the entire electromagnetic spectrum. Radio telescopes track the compact radio emission from the immediate vicinity of the event horizon. Infrared observations penetrate the dust and reveal hot gas swirling inward. X-ray detectors catch the high-energy flares produced when magnetic field lines reconnect. Each wavelength tells a different part of the story. The coordination required is staggering. When Sagittarius A star produces a flare, astronomers want to catch it simultaneously in radio, infrared, and X-rays. This means scheduling telescope time across facilities on different continents, operated by different organizations, often booked years in advance. A single coordinated observation campaign might involve a dozen telescopes and hundreds of people. These multi-wavelength campaigns have revealed something unexpected about how material flows toward the black hole. The traditional model pictured a relatively smooth accretion disk, with matter spiraling gradually inward like water circling a drain. the reality appears far more chaotic. Material clumps into dense blobs that orbit for a while before either falling in or getting ejected. The magnetic fields threading through this material create turbulence that churns the disk continuously. Understanding this turbulence matters because it determines how efficiently the black hole can feed. If the magnetic fields are too strong, they prevent material from settling into a stable disk, instead driving it away in winds and jets. If they're too weak, they can't transport angular momentum effectively, causing material to pile up rather than flow smoothly inward. Sagittarius A star appears to operate in a middle regime where feeding is possible but highly inefficient. That inefficiency explains why our galactic center is so quiet compared to active galactic nuclei in other galaxies. Some black holes shine with the luminosity of 1 trillion suns, visible across billions of light years. Sagittarius A star barely radiates more than an ordinary star, despite having 4 million times the sun's mass. The difference lies entirely in the feeding efficiency. Active black holes are gorging. Ours is barely nibbling. Yet even that minimal feeding produces measurable effects throughout the inner galaxy. The radiation and winds from Sagittarius A star heat the surrounding gas, preventing it from cooling and forming new stars. This creates a dead zone around the galactic center, a region where star formation has essentially stopped. The feedback mechanism operates even at low accretion rates, demonstrating how black holes influence their surroundings regardless of their activity level. The recent discovery of magnetic tornadoes adds another layer to this picture. These structures aren't metaphorical. They're actual rotating columns of magnetized gas, extending outward from the black hole like enormous whirlwinds. The ALMA observations that detected them operate at millimeter wavelengths, specifically chosen to trace the distribution of dust and molecules in the immediate vicinity of the black hole. What makes the tornado analogy APT is the rotational structure. The magnetic fields spiral around the black hole's rotation axis, creating a helical pattern that looks remarkably similar to atmospheric tornadoes on Earth. The physics is completely different, of course. These aren't pressure-driven vortices, but magnetic structures shaped by the black hole's spin and the angular momentum of infalling material. The tornadoes might explain another puzzle. How does Sagittarius A star manage to eject so much material despite being relatively inactive? The answer could lie in these magnetic structures, which act like cosmic conveyor belts, lifting material away from the black hole before it crosses the event horizon. This process removes angular momentum from the disk while simultaneously preventing most of the material from actually feeding the black hole. Testing this hypothesis requires detailed comparison between observations and simulations. Computational models of magnetized accretion have become increasingly sophisticated, running on supercomputers and incorporating the full complexity of general relativistic magnetohydrodynamics. These simulations can reproduce many features seen in actual observations, from the overall structure of the accretion flow to the timing and brightness of individual flares. But simulations have limitations. They require assumptions about initial conditions, magnetic field strengths, and turbulent viscosity. Different choices produce different outcomes, and it's not always clear which assumptions best match reality. This is where multi-wavelength observations become crucial. They provide independent constraints that help narrow down the parameter space, ruling out models that don't match the data. The flare observations are particularly constraining. Sagittarius A star produces 5 to 6 major flares per day, each lasting anywhere from minutes to hours. The exact timing and brightness distribution of these flares depends on the physical conditions in the accretion flow. Models that predict too many flares, or flares that are too bright, can be eliminated. Models that match the statistical properties provide insight into the underlying physics. Recent observations from the James Webb Space Telescope added a new dimension to flare studies by detecting mid-infrared emission for the first time. This wavelength regime traces slightly cooler material than the near-infrared observations that have been standard for years. The Webb detection suggests that flares involve larger volumes of gas than previously thought, extending further from the black hole and cooling as they expand. All these observations feed into a growing realization. Sagittarius A star isn't just a point mass sitting quietly at the galaxy's center. It's an active, dynamic system constantly processing material through complex electromagnetic interactions. The fact that we can study it in such detail, watching individual flares and tracking the motion of gas clouds week by week, represents an unprecedented opportunity in astrophysics. No other black hole can be studied with comparable resolution. Even M87 star, despite being imaged first and producing spectacular jets, remains too distant for the kind of detailed time-resolved observations possible with Sagittarius A star. Our galactic center provides the only laboratory where we can watch black hole physics unfold in real time, testing theoretical predictions against direct observations. Which raises an important question about the future. What comes next in our study of the galactic center? The technology continues improving. Adaptive optics systems become more sophisticated. Interferometric arrays add more telescopes and longer baselines. X-ray observatories achieve better sensitivity and time resolution. Each advance reveals finer details, pushing our understanding deeper. One instrument on the horizon deserves special attention. The next generation Event Horizon Telescope, currently in planning stages, will incorporate more stations, wider frequency coverage, and improved sensitivity. This enhanced array could produce movies instead of static images, tracking the motion of hot spots as they orbit the black hole. Imagine watching plasma blobs spiral inward, frame by frame, as they approach the point of no return. The scientific value would be extraordinary. But there's a challenge unique to Sagittarius A star that makes imaging harder than you'd expect. The black hole's accretion flow varies on timescales of minutes. During the hours needed to collect data from telescopes around the globe, the source changes its appearance. It's like trying to photograph someone who won't hold still. The image you eventually reconstruct represents an average over time, blurring out rapid variations that might reveal crucial physics. M87 star, despite being vastly more distant, actually proved easier to image because its accretion disk evolves much more slowly. The larger mass means longer orbital periods and more stable emission. For Sagittarius A star, the rapid variability requires new analysis techniques that can account for time-dependent structure. Researchers have developed methods to model the changing brightness patterns, essentially creating multiple snapshots from the same dataset and stitching them together into a coherent picture. The next decade will likely bring several major advances. Orbital monitoring will continue, with star S4714 providing particularly interesting data as it makes repeated close approaches. Each pass tests general relativity under increasingly extreme conditions. If deviations from Einstein's predictions exist, they should show up in the precise timing and trajectory of these ultra-close orbits. Flare monitoring will become more systematic. Instead of occasional observations when telescope time becomes available, dedicated programs will track Sagittarius A star continuously for extended periods. This sustained coverage will capture the full statistical distribution of flare properties, constraining models of magnetic reconnection and particle acceleration near the event horizon. Polarization observations will map magnetic field structure in unprecedented detail. The Event Horizon Telescope can already measure polarization, but future observations with improved calibration and more stations will produce sharper maps showing exactly how magnetic fields thread through the accretion flow. This addresses one of the biggest unknowns in black hole physics: the role of magnetic fields in controlling matter inflow and outflow. Gravitational wave astronomy might even contribute. Current detectors aren't sensitive to the frequencies that stellar mass objects orbiting Sagittarius A star would produce, but future space-based observatories could potentially detect gravitational radiation from spiraling compact objects. This would provide a completely independent measurement of the black hole's mass and spin, cross-checking results from electromagnetic observations. All these future observations connect to bigger questions about galaxy evolution. Supermassive black holes don't exist in isolation. They grow alongside their host galaxies through complex feedback processes that we're only beginning to understand. The black hole's gravity influences stellar orbits out to large distances. Jets and winds, when active, can heat or expel gas that might otherwise form stars. The relationship between central black hole mass and galaxy properties hints at deep connections between these phenomena. Sagittarius A star's current quiescence makes it unusual among supermassive black holes. Most galaxies at similar distances show evidence of more vigorous accretion, with bright nuclei and sometimes spectacular jets. Our black hole seems to be starving, fed only by occasional stellar winds and small gas clouds wandering too close. Why? Part of the answer might lie in the Milky Way's history. Major galaxy mergers tend to funnel gas toward the center, feeding the central black hole and triggering intense activity. The Milky Way hasn't experienced a major merger in several billion years, leaving Sagittarius a star with limited fuel. Small satellite galaxies have merged with us more recently, but they don't deliver enough gas to the very center to wake the black hole from its slumber. The recent discovery of an ancient eruption changes this picture somewhat. A few hundred to 1,000 years ago, Sagittarius A star blazed 10,000 times brighter than today. What triggered that outburst? Perhaps a gas cloud or disrupted star provided temporary fuel, or maybe we're seeing the tail end of episodic accretion cycles that occur naturally in low-luminosity systems. The XRISM observations that revealed this event represent just the beginning of studying the black hole's past behavior through light echoes. Understanding these eruptions matters for galactic evolution. Even brief periods of enhanced activity can significantly impact the surrounding environment. High-energy radiation and particle outflows heat nearby gas, potentially suppressing star formation in the central region. Over cosmic time, multiple such episodes could shape the distribution of matter throughout the inner galaxy. Looking even further ahead, new technologies will enable observations currently impossible. Quantum sensors might detect subtle gravitational effects with unprecedented precision. Neutrino telescopes could potentially observe high-energy neutrinos produced in the accretion flow, providing a completely different window into the physics near the event horizon. Advances in computing power will allow ever more detailed simulations, incorporating additional physics and running at higher resolution. One particularly exciting prospect involves using pulsars as probes of spacetime. Several pulsars orbit in the galactic center region, though none as close as the stars being tracked optically. If a pulsar were discovered in a tight orbit around Sagittarius A star, its radio pulses would provide exquisitely precise measurements of orbital motion and gravitational effects. The regular ticking of a pulsar acts like a natural atomic clock, revealing tiny deviations caused by the black hole's gravity. The search for such objects continues. Pulsars are faint and easily missed in surveys, especially in the crowded and obscured galactic center. Dedicated radio monitoring programs sweep the region regularly, looking for the characteristic periodic signals. Finding even one pulsar in a close orbit would revolutionize black hole studies, enabling tests of general relativity far more stringent than anything currently possible. Beyond pure science, Sagittarius A star serves another role. It anchors our understanding of cosmic scales and the nature of extreme physics. Every measurement, every image, every observation contributes to humanity's expanding knowledge of the universe. The black hole at our galaxy's heart represents the nearest example of phenomena that occur throughout the cosmos, from the centers of distant quasars to the merging black holes that produce gravitational waves. As technology progresses and observations accumulate, our picture of Sagittarius A star will continue evolving. What seems mysterious today might become routine tomorrow. Phenomena we haven't yet imagined could emerge from future data. The history of astronomy teaches that every improvement in observational capability reveals unexpected discoveries. Consider how far we've come. Less than a century ago, the existence of black holes was pure speculation. 50 years ago, we didn't know for certain that our galaxy harbored a supermassive black hole. 20 years ago, we couldn't track individual stars orbiting it. Today we have an image of the event horizon itself and are mapping magnetic tornadoes in the accretion flow. What will the next 20 years bring? Perhaps movies of the accretion disk. Maybe detection of gravitational waves from inspiraling objects. Possibly evidence of a weak jet or detailed measurements of space-time curvature. The only certainty is that Sagittarius A star will continue surprising us, revealing new aspects of black hole physics with each technological advance. The black hole at our galaxy's center stands as both a destination and a beginning. Every answer generates new questions. Every observation opens new avenues of investigation. This 4 million solar mass object, sitting 26,000 light-years away, represents one of the richest laboratories in all of astrophysics. And we've only just started exploring it. The story of Sagittarius A star is far from finished. We've spent decades discovering what it is, years learning how it behaves, and we're only now beginning to understand what it means. This black hole doesn't exist as some isolated curiosity at the galaxy's center. It's the gravitational anchor for everything around us, the central mass that keeps hundreds of billions of stars, including our own sun, locked in their cosmic orbits. Every observation reveals something unexpected. The magnetic tornadoes weren't predicted by theory. The ancient eruption caught everyone by surprise. The similarity between our relatively tiny black hole and the monster at M87 center challenges assumptions about how these objects work. Even the simple fact that Sagittarius A star remains so quiet despite sitting in a region rich with potential fuel continues puzzling researchers. What makes this ongoing investigation so valuable is proximity. At 26,000 light-years away, Sagittarius A star sits close enough that we can resolve details impossible to see in more distant black holes. We can track individual stars completing their orbits in real time. We can watch flares emerge and fade over the course of hours. We can measure how space-time curves near the event horizon with precision unmatched anywhere else in the universe. Other galaxies host larger black holes, more active black holes producing spectacular jets visible across cosmic distances. But none of them can be studied with the intimacy our galactic center allows. M87 star, despite its fame as the first black hole ever imaged, remains a distant giant. We see its overall structure but miss the fine details that reveal how black holes actually work moment to moment. The discoveries keep coming because the technology keeps improving. The Event Horizon Telescope will add more stations, improving resolution and enabling time-resolved imaging. Adaptive optics systems will achieve sharper views of the stellar orbits. X-ray observatories will track flares with better sensitivity. Each improvement pushes our understanding deeper into the physics of extreme gravity. But perhaps the most important realization is this. Sagittarius A star represents a system fundamentally different from what early theories predicted. Black holes were once thought to be simple objects, described completely by just their mass and spin. The reality involves complex magnetic fields, turbulent accretion flows, episodic eruptions, and feedback mechanisms that regulate feeding efficiency. The magnetic tornadoes demonstrate that even quiet black holes maintain complex electromagnetic structures. The ancient eruption proves that current behavior doesn't predict future activity. The similarity to M87 star suggests universal principles governing all supermassive black holes despite vast differences in mass and environment. These aren't isolated facts, but pieces of a larger picture still coming into focus. Looking forward, the questions multiply faster than answers arrive. Will we detect a hidden jet once instruments become sensitive enough? What triggers the episodic eruptions that apparently occur every few centuries? How do the magnetic fields actually transport angular momentum through the accretion disk? Can we find a pulsar in a close orbit to provide even more precise tests of general relativity? Each question leads to others. Understanding the magnetic field structure requires better polarization measurements, which demand improvements to interferometric techniques. Predicting future eruptions means modeling the supply of gas to the inner accretion zone, which requires mapping the distribution of material throughout the central parsec. Every advance opens new territory for investigation. The broader implications extend beyond our galaxy. Supermassive black holes occupy the centers of most large galaxies throughout the universe. Understanding Sagittarius A star provides insights into how these objects form, grow, and influence galactic evolution everywhere. The feedback mechanisms operating in our galactic center probably operate in distant galaxies billions of light-years away, shaping cosmic structure on the largest scales. There's something profound about studying an object we'll never visit, never sample directly, never examine except through photons that travel 26,000 years to reach our instruments. Everything we know about Sagittarius A star comes from watching light that began its journey toward Earth before human civilization existed. The photons captured by the Event Horizon Telescope left the galactic center while mammoths still walked the Earth. Yet from those ancient photons, we've reconstructed the geometry of spacetime near the event horizon. We've measured the black hole's mass to exquisite precision. We've mapped magnetic fields and tracked plasma motions. We've tested Einstein's theory under conditions he never imagined. The black hole reveals itself not through direct observation but through its influence on everything around it. That's the nature of studying extreme physics. You can't bring a black hole into the laboratory. You can't experiment with different parameters to see what happens. The universe provides the laboratory, and we observe what nature chooses to reveal. Sagittarius A star happens to be positioned perfectly for detailed study, close enough to resolve, massive enough to be interesting, yet quiet enough that the surrounding environment remains stable. The coming decades will bring observations that seem impossible today. Technology marches forward relentlessly. Detectors become more sensitive. Telescopes achieve better resolution. Analysis techniques grow more sophisticated. What we learn from the next generation of observations will likely reshape our understanding as profoundly as the Event Horizon Telescope image did. But some mysteries might persist. We may never witness another major eruption like the ones RISM detected through its light echo. Human lifetimes, even human civilizations, represent mere instants compared to the timescales on which Sagittarius A star operates. We're studying a system that changes on scales of centuries, millennia, millions of years. Our observations capture brief snapshots of a process vastly longer than recorded history. That limitation makes every observation more precious. We can't run the experiment again. We can't ask the black hole to repeat an interesting behavior. We get one chance to capture each event, and if we miss it, the opportunity vanishes perhaps for thousands of years. This urgency drives the continuous monitoring campaigns, the coordinated observations, the push for better instruments. The black hole at our galaxy's center will outlive our Sun. Long after Earth becomes uninhabitable, long after the Sun exhausts its nuclear fuel, Sagittarius A star will continue orbiting through the galaxy, occasionally feeding on whatever material wanders too close, erupting when circumstances align just right. It's existed for billions of years and will exist for trillions more, an almost eternal fixture of our cosmic neighborhood. Yet for this brief moment in cosmic history, we're here to observe it. An intelligent species evolved on a planet orbiting an ordinary star in one of the galaxy's spiral arms, and that species developed the technology to peer into the heart of its galaxy and understand what lurks there. We're watching the black hole that holds our galaxy together, measuring its properties, testing fundamental physics in its vicinity. Future observers, whether human descendants or entirely different intelligences, will build on what we've learned. They'll have better instruments, more complete theories, deeper understanding. But they'll also look back at these early observations, the first image, the first detection of magnetic tornadoes, the first stellar orbit measurements, as the foundation everything else was built upon. We're living through the opening chapter of humanity's relationship with the black hole at our galaxy's center, and that story has barely begun.
NASA just confirmed something that rewrites everything we thought we knew about life in our solar system. Beneath the icy surface of Ganymede, Jupiter's largest moon, there's an ocean. Not a puddle, not frozen water deposits. An actual ocean larger than all of Earth's surface water combined, hidden under miles of ice in the most hostile environment imaginable. And the implications are staggering. For decades, scientists suspected water might exist on distant moons. They had theories, models, mathematical predictions. But Ganymede was different from the start. When Galileo first spotted it in 1610 through his primitive telescope, he had no idea he was looking at what might be the most important body of water in the known universe. He just saw a bright dot orbiting Jupiter. For centuries later, we're staring at data that suggests this frozen world harbors more liquid water than our entire planet. The confirmation didn't come from a single observation. It emerged from years of meticulous detective work, analyzing magnetic fields, studying how Ganymede interacts with Jupiter's radiation, and piecing together clues that individually meant nothing but together painted an undeniable picture. The Hubble Space Telescope played a crucial role, not by taking pretty pictures, but by watching something most people would find utterly boring. Auroras. Ganymede has auroras, just like Earth. Shimmering lights dancing across its surface, generated by charged particles interacting with its magnetic field. But here's where it gets interesting. These auroras wobble. They rock back and forth in a specific pattern, and that pattern only makes sense if there's a massive conducting layer beneath the ice. Salt water conducts electricity. Ice doesn't. The math was unavoidable. Jupiter's magnetic field is brutal. It's the strongest planetary magnetic field in our solar system, roughly 20,000 times more powerful than Earth's. This field constantly batters Ganymede, which has its own magnetic field, the only moon in our solar system that does. When these two fields interact, they create observable effects on the surface. The auroras shift. They move. And by measuring exactly how they move, scientists could calculate what must be underneath. The ocean isn't sitting right below the surface. Ganymede's structure resembles a layered cake of ice and water. The outermost layer is solid ice, roughly 100 miles thick. Beneath that, liquid ocean. Below the ocean, another layer of ice. Then possibly another ocean. The entire structure extends down hundreds of miles, with the deepest ocean potentially sitting on a rocky seafloor rich in minerals. Temperature plays a bizarre role here. The surface of Ganymede hovers around -170 degrees Celsius. At that temperature, any exposed water would freeze solid in seconds. But deep beneath the ice, pressure and internal heat from tidal forces keep the water liquid. Jupiter's gravity squeezes and stretches Ganymede as it orbits, generating friction, creating warmth. Not enough to make the moon comfortable, but enough to maintain liquid water in the darkness below. The sheer volume is difficult to grasp. Earth's oceans contain roughly 1.335 billion cubic kilometers of water. Ganymede's subsurface ocean likely contains more. Some estimates suggest 2 to 3 times Earth's total water volume, all hidden beneath an alien ice shell, never touched by sunlight, existing in permanent darkness at pressures that would crush most submarines instantly. This discovery fundamentally changes the search for life beyond Earth. For years, the focus remained on Mars. Red dirt, ancient riverbeds, the possibility of microbial life clinging to existence in underground pockets. Mars made sense because it's close, relatively accessible, and clearly had water in its past. But Ganymede has water now. Liquid, stable, potentially rich in the chemistry needed for biology. Life on Earth exists in the strangest places. Deep ocean vents spewing superheated water create ecosystems thriving without sunlight. Microbes live miles underground in solid rock. Organisms survive in Antarctic lakes sealed beneath ice for millions of years. If life can adapt to those conditions here, why not in Ganymede's ocean? The ingredients are present. Water, energy from tidal heating, and potentially organic compounds delivered by ancient asteroid impacts. The history of this discovery stretches back further than most realize. The Voyager missions in the late 70s provided the first close-up images of Ganymede, revealing a surface unlike anything seen before. Strange grooves, impact craters, and regions of different ages suggested geological activity. Something was reshaping this moon's surface, but without plate tectonics or volcanic activity, the mechanism remained mysterious. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, gathered data that hinted at subsurface oceans on multiple moons. Its magnetometer detected induced magnetic fields around Ganymede, Europa, and Callisto, suggesting conducting layers beneath their surfaces. But the data was incomplete, subject to interpretation, and scientists remained cautious. Extraordinary claims require extraordinary evidence. That evidence accumulated slowly. Computer models improved. Understanding of tidal heating mechanisms deepened. Observations from Earth-based telescopes added pieces to the puzzle. The Hubble aurora measurements provided the breakthrough, offering indirect but compelling proof that couldn't be explained any other way. The scientific community reached consensus. Ganymede has an ocean. But knowing an ocean exists and understanding it are entirely different challenges. The ice shell separating this ocean from space presents an almost impenetrable barrier. 100 miles of solid ice. No drill bit created by human engineering could penetrate that thickness. Any mission to directly sample Ganymede's ocean requires technology that doesn't exist yet, solutions to problems we're only beginning to understand. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023. It won't arrive at Jupiter until 2031, then spend years studying Ganymede, Europa, and Callisto in unprecedented detail. JUICE carries instruments designed to peer through the ice, map the ocean's depth, analyze its composition, and search for signs of geological activity. It won't land, won't drill, won't sample the water directly. But it will transform our understanding. NASA's Europa Clipper, launching in 2024, focuses primarily on Europa, another Jovian moon with a subsurface ocean. But its findings will inform our understanding of Ganymede. These moons share similar characteristics, formed under comparable conditions, subjected to the same gravitational forces. Lessons learned from one apply to the others. The timeline frustrates everyone involved. Space missions take decades from conception to data collection. JUICE won't provide its most detailed Ganymede observations until the mid-2030s. Any follow-up mission to actually land on the surface and attempt to reach the ocean wouldn't launch until the 2040s at the earliest, possibly later. We're looking at a multi-generational project, where scientists designing today's missions may never see their ultimate conclusions. Yet the discovery itself, the confirmation that this ocean exists, represents a pivotal moment. For the first time in human history, we know with confidence that another world in our solar system harbors vast amounts of liquid water. Not ancient water, not frozen deposits that might melt someday. Water existing right now, potentially supporting ecosystems we can't yet imagine. The chemistry of Ganymede's ocean remains largely unknown. Is it fresh water or salt water? What minerals are dissolved in it? Are there organic compounds? Does the rocky seafloor host hydrothermal vents like those on Earth? Each question branches into dozens more, creating a web of mysteries that will occupy scientists for generations. Tidal heating provides the energy source, but how much energy? Earth's ocean vents support complex ecosystems because they pump out heat and chemicals continuously. If Ganymede's ocean floor has similar features, the energy budget might support life. If it's geologically dead, just cold dark water sitting motionless for billions of years, the prospects dim considerably. The multiple ice and water layers add complexity. Some models suggest up to 3 separate oceans stacked vertically, each isolated from the others by ice layers of different densities and crystalline structures. Communication between these layers would be minimal or non-existent. Life could potentially exist in one layer while others remain sterile. Or each layer might host distinct ecosystems adapted to specific conditions. Radiation presents another factor. Jupiter's magnetosphere traps high-energy particles that constantly bombard its moons. Ganymede's magnetic field provides some protection, but the surface still receives significant radiation doses. The ice layer shields the ocean from this radiation, but organic molecules on or near the surface would be quickly destroyed. Any life on Ganymede must exist deep, protected by miles of ice from the hostile radiation environment above. The philosophical implications ripple outward. If life exists in Ganymede's ocean, it would prove that biology isn't unique to Earth. The argument shifts from whether life exists elsewhere to how common it might be. If two bodies in one solar system both harbor life, the universe likely teems with it. Every star becomes a possibility, every planet and moon a potential incubator. But we're getting ahead of ourselves. Right now, we have confirmed water and plausible conditions. That's all. The leap from conditions to actual biology remains enormous, filled with uncertainties and assumptions. Life might be common, or Earth might be a cosmic fluke that won't repeat for billions of light years in any direction. What makes Ganymede particularly intriguing is its stability. Mars lost most of its water billions of years ago. Venus turned into a hellscape. Earth's oceans face eventual evaporation as the sun ages. But Ganymede's ocean, locked beneath protective ice and powered by tidal forces that will continue for billions of years, might be more stable than anything on Earth. If life took hold there, it could persist longer than life on our own planet. The size of Ganymede itself matters. At 5,268 kilometers in diameter, it's larger than Mercury, the smallest planet in our solar system. If Ganymede orbited the Sun instead of Jupiter, we'd classify it as a planet. Its substantial gravity holds onto a thin atmosphere, primarily oxygen produced when radiation splits water molecules on the icy surface. The oxygen immediately freezes or gets stripped away by Jupiter's magnetosphere, but its presence confirms water is being processed. Human exploration of Ganymede belongs to science fiction for now. The radiation alone makes crewed missions nearly impossible with current technology. Any spacecraft approaching Jupiter enters a radiation environment that would kill unprotected astronauts within hours. Shielding heavy enough to protect humans would make the spacecraft too massive to launch economically. Robotic missions remain our only viable option for the foreseeable future. That limitation doesn't diminish the significance. Robots can go where humans cannot, endure conditions we'd never survive, and operate for years without food, water, or breathable air. The Voyager probes, launched in 1977, still send data from interstellar space. Properly designed, a mission to Ganymede's ocean could operate for decades, slowly unraveling its mysteries. The technical challenges are staggering but not insurmountable. We need better power sources for long-duration missions far from the sun where solar panels become useless. We need autonomous systems capable of making decisions without waiting for instructions from Earth, since radio signals take nearly an hour to travel between Jupiter and home. We need materials that can withstand extreme cold, high radiation, and the crushing pressures of deep ice. Engineers are already working on concepts. Nuclear-powered cryobots that could melt through ice. Autonomous submarines designed for alien oceans. Instruments sensitive enough to detect organic molecules in tiny water samples. Each component pushes the boundaries of current technology, but none require physics we don't understand. It's engineering, not magic. The cost will be enormous. A mission to land on Ganymede, drill through the ice, and explore the ocean would likely exceed $20 billion, possibly much more. That's a significant fraction of NASA's entire annual budget. International collaboration could spread the cost, but coordinating such a complex mission across multiple space agencies introduces its own challenges. Yet the alternative is remaining ignorant about what might be the most important discovery in human history. If life exists in Ganymede's ocean, finding it would answer humanity's oldest question. We are not alone. And if the ocean is sterile despite having the right conditions, that tells us something equally important about how rare and precious life might be. The next decade will lay the groundwork. JUICE and Europa Clipper will provide the detailed reconnaissance needed to plan future missions. They'll map the ice thickness, identify regions where it's thinnest, search for cracks or areas of geological activity where access might be easier. They'll measure the ocean's salinity, depth, and temperature as precisely as possible from orbit. Based on that data, space agencies will design the next generation of missions. Maybe a lander that can survive on the surface long enough to conduct detailed studies. Perhaps a penetrator that can punch through several miles of ice and deploy sensors. Possibly even a submarine, delivered through a borehole, that could explore the alien sea. Human curiosity demands answers. We've spent centuries wondering whether we're alone in the universe. Now we know where to look. Beneath the ice of a distant moon, in an ocean larger than all of Earth's seas combined, the answer might be waiting. The engineering challenges alone could fill textbooks. Ganymede's surface temperature hovers around -160 degrees Celsius. Electronics freeze. Lubricants solidify. Batteries lose efficiency. Every component must be designed to function in conditions that would instantly shut down equipment built for Earth. Then there's the ice itself. We're not talking about a frozen pond. The ice shell could be 50 miles thick in places. That's nearly 10 times the height of Mount Everest, except vertical and solid. Drilling through that much ice isn't a matter of bringing a bigger drill. The pressure increases with depth. The ice at the bottom behaves differently than the ice at the top, transitioning from brittle crystal to something more plastic, almost flowing under its own weight. A cryobot melting its way down would need to generate enormous heat continuously, requiring either a radioisotope thermoelectric generator or a compact nuclear reactor. The power source must be small enough to fit in a deployable probe yet robust enough to operate for months or years. It needs to survive radiation from Jupiter. It must avoid contaminating the very environment we're trying to study with Earth microbes that might hitchhike on the spacecraft. Planetary protection protocols will be stricter for Ganymede than for any previous mission. If there's even a possibility of indigenous life, we cannot risk introducing terrestrial organisms that might outcompete or contaminate native biology. Every surface must be sterilized. Every seal must be perfect. The probe becomes a self-contained bubble of Earth technology, isolated from the alien world it's trying to explore. Now add communication problems. A probe beneath miles of ice cannot send radio signals back to an orbiter. Ice blocks electromagnetic radiation effectively. This means either the probe must carry an extremely long cable, unreeling it as it descends, or it must operate completely autonomously, storing data until it can surface or relay information through the borehole. autonomy introduces new complications. The probe needs artificial intelligence sophisticated enough to navigate unknown terrain, identify interesting features, avoid hazards, and make scientific decisions without human input. If it encounters something unexpected, it cannot phone home for instructions. Round-trip light time to Jupiter means waiting nearly 2 hours for a response to any question. In a dynamic environment, that delay could be fatal to the mission. Consider the submarine concept. Once through the ice, the vehicle must operate in total darkness under pressures that could reach several hundred atmospheres if the ocean is deep enough. It needs propulsion systems that work in extremely cold water. It requires sensors that can detect and analyze whatever might be floating in that alien sea, from simple organic molecules to potential life forms. What happens if the submarine encounters something alive? The protocol must be designed in advance. Does it collect samples? Does it observe without touching? How do you balance scientific curiosity with the ethical implications of disturbing an alien ecosystem that has existed in isolation for billions of years? These aren't abstract philosophical questions. Mission designers must answer them before launch because there's no opportunity to revise the plan once the spacecraft leaves Earth. Every contingency must be anticipated. Every failure mode must have a backup. Space exploration runs on redundancy and careful planning, not improvisation. The timeline stretches across decades. JUICE launched in 2023 and won't arrive at Jupiter until 2031. Europa Clipper launches in 2024 with arrival in 2030. Both spacecraft will spend years conducting flybys, gathering data, refining our understanding. Based on their findings, a lander mission might launch in the late 2030s, arriving in the mid-2040s. A drilling mission could follow in the 2050s. A submarine exploring the subsurface ocean might not splash down until the 2060s or later. This assumes steady funding, no major technical setbacks, and sustained political will across multiple administrations and international partnerships. Space missions operate on timescales that outlast careers, sometimes outlast entire space agency strategic priorities. The people who design these missions often retire before launch. The scientists who propose investigations might not live to see the results. Yet the work continues because the questions matter. Does life exist elsewhere? Is Earth unique, or is biology a common outcome when the right conditions persist long enough? Ganymede offers a test case. It has liquid water, energy sources, and complex chemistry in a stable environment that has existed for billions of years. If life can arise and persist there, it suggests the universe might be teeming with biology in places we never thought to look. The alternative is equally profound. If Ganymede's ocean is sterile despite having everything life needs, that implies something about Earth's biosphere is special, rare, perhaps unique. It means the origin of life requires more than just the right ingredients. It suggests we might be alone after all, or at least that living worlds are far more scarce than optimistic estimates predict. Scientists debate these possibilities constantly. Some argue life is inevitable given the right conditions, that chemistry naturally progresses toward biology, that the universe should be full of microbes at minimum. Others counter that Earth's biosphere might depend on a precise sequence of unlikely events, that life requires not just water and energy but specific catalysts, particular mineral surfaces or rare chemical pathways that don't exist everywhere. Ganymede will provide evidence, not proof, because proving life doesn't exist anywhere is impossible. You can only prove it does exist by finding it. But if we search thoroughly and find nothing, that shifts the probabilities. It means life is either rarer than we hoped or hidden in ways we don't yet understand. The search itself will advance technology in unexpected ways. Developing autonomous systems for Ganymede will improve robotics here on Earth. Materials that can withstand Jupiter's radiation environment will find applications in nuclear facilities and medical equipment. Power systems designed for deep space will influence energy technology for remote terrestrial locations. Space exploration has always produced spin-off benefits far beyond its primary objectives. But those practical applications aren't why we go. We go because not knowing is intolerable. Humans don't look at locked doors and walk away satisfied. We pick the lock, we break it down, we find another entrance. Ganymede is a locked room the size of a planet, and we've just started examining the hinges. The ocean might be vast and empty, devoid of anything more interesting than water and dissolved salts. That would be disappointing but still valuable. We'd learn about oceanography in low-gravity environments. We'd understand how heat flows through icy moons. We'd gather data about chemistry in sealed systems isolated for geological timescales. Or we might find something that changes everything. Not necessarily intelligent life. Even single-celled organisms would be revolutionary. Bacteria, if we can call them that, adapted to crushing darkness and extreme cold. Microbes that derive energy from chemical gradients rather than sunlight. Simple life following different biochemical rules, using different molecules, perhaps not even based on DNA. That last possibility excites biologists especially. All life on Earth uses the same genetic code, the same basic molecular machinery. We're all related, descended from a common ancestor that lived billions of years ago. But if life arose independently on Ganymede, it might have found different solutions to the same problems. Different information storage molecules. Different energy currencies. Different ways of building cells and regulating metabolism. Comparing Earth life to Ganymede life, if it exists, would reveal which aspects of biology are universal and which are accidents of history. It would show us what life must do to exist versus what Earth life happens to do because that's how it evolved here. That knowledge would transform biology from a historical science describing what happened on one planet to a predictive science explaining what must happen anywhere. The implications extend beyond pure research. Understanding life's minimal requirements would guide searches for habitable planets around other stars. It would inform discussions about terraforming, about creating conditions for life in places currently sterile. It might even reveal new approaches to biotechnology, new ways of engineering organisms or synthesizing useful compounds. But these practical considerations fade next to the fundamental question. In 4.5 billion years of Earth's history, in hundreds of millions of species that have lived and died, in all the complexity of the biosphere from bacteria to blue whales, has life happened only once? Or is it happening right now, independently, in a dark ocean beneath the ice of a distant moon? We're close to finding out. Not tomorrow. Not next year. But within the lifetime of people alive today, we will send machines to Ganymede capable of answering that question. They'll drill through the ice, sample the water, analyze what they find with instruments sensitive enough to detect organic molecules at concentrations of parts per billion. If those instruments find nothing, we'll build better ones. We'll look in different locations. We'll develop new techniques. The absence of evidence doesn't mean evidence of absence, especially when searching an ocean millions of cubic kilometers in volume. But if we find something, anything that moves on its own, that consumes energy, that reproduces, that fits any reasonable definition of life, then we'll know. Human beings will have discovered that we are not alone in the universe. That life exists beyond Earth. That the cosmos is not a sterile void punctuated by one lonely living world, but a place where biology emerges wherever conditions allow. And if a frozen moon of Jupiter hosts life, what about the hundreds of billions of other planets and moons in our galaxy alone? The discovery wouldn't happen all at once. There'd be no single dramatic moment when a scientist points at a screen and shouts that we found aliens. Instead, it would unfold through careful analysis, repeated tests, heated debates in conference rooms and academic journals. Someone would notice unusual chemical signatures in return samples. Organic molecules with strange isotope ratios. Compounds that seem too complex to form through simple chemistry. The first papers would be cautious, hedging their conclusions, suggesting that further investigation is warranted. Then other teams would examine the same data and reach similar conclusions. The evidence would accumulate slowly. Lipid-like molecules that could form membranes. Polymers that might store information. Traces of metabolic processes that can't be explained by known geological chemistry. At some point, the weight of evidence would become overwhelming. The scientific consensus would shift from skepticism to acceptance. But convincing the broader world would take longer. News media would sensationalize the findings, alternating between wild speculation and dismissive skepticism. Social media would erupt with conspiracy theories. Religious leaders would grapple with theological implications. Philosophers would debate what it means for humanity's place in the cosmos. Politicians would argue about funding priorities and international cooperation. Meanwhile, scientists would already be planning return missions. Not just sample return this time, but direct observation. Submersibles that can swim through Ganymede's ocean for months or years, equipped with cameras and sensors and AI systems sophisticated enough to recognize life when they see it. Because finding evidence of life and actually observing living organisms are two very different achievements. Consider what those organisms might look like. On Earth, life in similar environments, deep ocean hydrothermal vents shrouded in permanent darkness, has evolved into bizarre forms. Tube worms 3 meters long with no mouth, no digestive system, surviving on bacteria that live in their tissues. Eyeless shrimp clustering around volcanic vents, their backs covered in light-sensitive organs that detect the faint infrared glow of superheated water. Fish with enormous mouths and bioluminescent lures, adapted to a world where food is scarce and every meal counts. Ganymede's life would face similar pressures but with crucial differences. Earth's deep ocean is connected to the surface. Organic matter drifts down from the sunlit zones above. Dead plankton, fish carcasses, even whale falls that sustain entire ecosystems for decades. Ganymede's ocean has no such connection. No photosynthesis occurring anywhere in the system. No rain of organic carbon from above. Everything must derive from chemistry. From the reactions occurring where water meets rock, where minerals dissolve and precipitate, where temperature and pressure create gradients that life can exploit. This means Ganymede's biosphere, if it exists, would be fundamentally limited in a way Earth's is not. The total amount of chemical energy available sets a hard ceiling on how much life can exist. On Earth, photosynthesis captures roughly 100 terawatts of solar energy. That's the foundation supporting everything else, from bacteria to humans. Ganymede's chemical energy budget would be orders of magnitude smaller. Maybe a few gigawatts at most, possibly much less. This has profound implications for what kind of life could exist there. Forget anything large or complex. No fish swimming through the darkness. No predators hunting prey. The energy simply isn't there to support such lifestyles. Instead, we'd expect to find microbial communities clustered around hydrothermal vents and chemical gradients. Perhaps biofilms coating rock surfaces, slowly metabolizing minerals. Maybe free-floating cells drifting through the ocean, living at such a slow pace that their metabolism would be barely detectable. These organisms would likely reproduce slowly, grow slowly, evolve slowly. Where Earth bacteria can double in number every 20 minutes under ideal conditions, Ganymede microbes might take days or weeks. Their generation times could be measured in years. Evolution on Ganymede might proceed at a glacial pace compared to Earth, simply because there's less energy available to power the biochemical processes that drive mutation and selection. Yet that slowness wouldn't make them any less alive. They'd still be consuming energy, maintaining themselves against entropy, reproducing, evolving. They'd still represent an independent origin of life, a second example of biology emerging in the universe. And studying them would be incredibly difficult precisely because of that slow pace. Detecting metabolism when it happens over weeks instead of hours requires patience and sensitive instruments. Distinguishing living processes from chemical reactions becomes harder when both occur at similar speeds. Proving that something reproduces when reproduction takes months to complete means waiting months between observations. Traditional microbiological techniques developed for Earth organisms, techniques that rely on culturing bacteria in labs and watching them grow, might not work at all. We'd need entirely new approaches. Genetic sequencing, if Ganymede life uses anything resembling DNA or RNA. Chemical analysis of cell components. Microscopic observation of cellular structures. Isotope tracing to track the flow of elements through metabolic pathways. Each technique would have to be adapted for organisms that might not resemble Earth life in any obvious way. And there's a darker possibility worth considering. What if we contaminate Ganymede's ocean before we even realize it harbors life? Every spacecraft we send carries Earth microbes, despite our best sterilization efforts. Sun bacteria can survive the vacuum of space, survive intense radiation, survive years of dormancy. If even a few cells reach Ganymede's ocean, they might find conditions suitable for growth. Earth microbes, adapted to environments with abundant energy, might outcompete native Ganymede organisms in the same way invasive species devastate island ecosystems on Earth. We could destroy an entire alien biosphere before we even confirm it exists. This is why planetary protection protocols are so important, why we heat-sterilize spacecraft components, why we plan trajectories that avoid impacting potentially habitable worlds. But protocols aren't perfect. Accidents happen. Missions fail. A spacecraft could crash on Ganymede's surface, its fragments eventually working their way through cracks in the ice to the ocean below. Or perhaps contamination has already occurred through some path we haven't anticipated. Natural processes, for instance. Meteorite impacts eject material from planetary surfaces into space. Rocks from Mars have landed on Earth. Rocks from Earth might have reached Ganymede over the solar system's history. If Earth microbes arrived on Ganymede millions of years ago, encased in rock from an impact event, could they have survived? Could they have adapted to the conditions there? This raises an unsettling question. If we find life on Ganymede, how do we prove it originated there independently rather than being related to Earth life that contaminated the Moon long ago? The answer lies in biochemistry. If Ganymede organisms use the same genetic code as Earth life, the same amino acids, the same basic molecular machinery, that would suggest a common origin. Either contamination or panspermia, the idea that life spreads between worlds on meteorites. But if Ganymede life uses different molecules, different information storage systems, different metabolic pathways with no clear connection to Earth biochemistry, that would prove independent origin. Testing this requires bringing samples back to Earth, analyzing them in laboratories with equipment too sophisticated to send to Ganymede. Which creates another problem. How do we safely return samples that might contain alien microbes? What if those microbes, despite evolving in a completely different environment, turn out to be dangerous to Earth life? The risk is probably minimal. Organisms adapted to Ganymede's high-pressure, low-energy environment likely couldn't survive in Earth's oxygen-rich atmosphere at normal pressure. They'd be as out of place here as we would be there. But probably isn't the same as certainly. So any sample return mission would require extraordinary precautions. Sealed containment from the moment samples are collected. Analysis in high-security biosafety facilities. Protocols for sterilization if anything goes wrong. We've done this before, actually. Apollo astronauts returning from the Moon were quarantined in case they brought back lunar pathogens. We now know the Moon is sterile, but the precaution was reasonable given what we knew then. Samples from Ganymede would require similar or greater care, because unlike the Moon, Ganymede actually might harbor life. These practical challenges, the engineering problems and safety protocols and mission designs, can make the search for life seem like a purely technical exercise. Build the right instruments, follow the right procedures, analyze the data correctly. But beneath the technical details lies something more profound. We're attempting to answer a question humans have asked since we first looked up at the night sky. Are we alone? For most of history, that question was purely philosophical. We could speculate, imagine, tell stories about other worlds and other beings. But we couldn't actually investigate. We couldn't go looking. Now we can. Not easily. Not quickly. But we have the technology and the knowledge to send machines to distant worlds in search for life. Ganymede represents our best near-term opportunity. Not the only one. Mars might harbor life in subsurface aquifers. Enceladus, another moon of Saturn, has a similar subsurface ocean that might be even more accessible than Ganymede's. Titan has liquid methane seas and complex organic chemistry. Each world offers a different chance to find biology beyond Earth. But Ganymede stands out because of what we already know about it. The ocean is definitely there. It's in contact with rock. It's existed for billions of years. The conditions, while extreme by Earth standards, fall within the range that could potentially support life. We're not guessing, we're hoping. We're investigating a real possibility based on solid evidence. That investigation requires missions that don't exist yet. We have orbiters studying Jupiter's moons from a distance. We have plans for future missions with more sophisticated instruments. But actually landing on Ganymede, drilling through kilometers of ice, reaching the ocean below. That's beyond our current capabilities. Not impossible. Just difficult and expensive and years away from being technically ready. Which means the search for life on Ganymede exists in a strange state. We know enough to make it compelling. Not enough to actually do it. We're caught between possibility and practicality, between what we want to know and what we can currently achieve. Consider what a Ganymede lander would need to accomplish. First, survive the journey. Jupiter's radiation environment is brutal. Electronics that work fine on Earth or even Mars would fail within hours near Jupiter without heavy shielding. The lander needs protection, but protection adds mass, and mass makes landing harder. Then there's the landing itself. Ganymede's surface is ancient ice, hard as rock, covered with craters and ridges and fracture systems. Finding a safe landing site requires detailed mapping. Avoiding hazards requires precision navigation. All while operating with a communication delay that makes real-time control from Earth impossible. Signals take nearly an hour to travel between Jupiter and Earth at light speed. Commands sent now won't arrive for 43 minutes. Responses take another 43 minutes to return. Any crisis must be handled autonomously by the spacecraft itself. After landing comes the real challenge. Drilling. Not through a few meters of ice, but potentially kilometers. Earth has drilled through ice sheets in Antarctica and Greenland, reaching depths of several kilometers. But those drills are powered by massive equipment, operated by teams of engineers, supported by supply chains bringing fuel and replacement parts. A Ganymede drill would have none of that. It would need to be compact enough to fit on a spacecraft. Light enough to launch from Earth. Powerful enough to penetrate kilometers of ice harder than concrete. Reliable enough to work without maintenance in an environment where the average temperature sits at -160 degrees Celsius. Some designs propose using heat to melt through the ice rather than mechanical drilling. A heated probe slowly descends, melting ice above it which refreezes after it passes, sealing the hole. This approach is elegant and potentially more reliable than mechanical systems. But it's also slow. Estimates suggest it could take years to reach significant depths. Years during which the probe must continue functioning, powered by a nuclear battery that slowly loses strength as its radioactive fuel decays. Other approaches use a combination of heating and mechanical drilling, or cryobots that navigate through existing cracks rather than drilling new holes, or autonomous submarines deployed through access points where ice is thinner, perhaps near the dark terrain where the ocean might be closer to the surface. Each approach has advantages. Each faces enormous engineering challenges. None have been tested in conditions resembling Ganymede's actual environment. We're not talking about adapting existing technology. We're talking about inventing new systems for problems we've never encountered. And we need those systems to work the first time, because there won't be a second chance to retrieve a probe that gets stuck halfway through an ice sheet 300 million kilometers from Earth. Assuming we solve the drilling problem, assuming we reach the ocean, what happens next? The probe needs to function underwater in conditions nothing from Earth was designed for. Pressure at the ocean floor could exceed 2,000 times Earth's surface pressure. Saltwater with unknown chemistry might corrode materials in unexpected ways. The complete absence of light means any instruments must bring their own illumination. Swimming or moving along the bottom requires propulsion systems that work in dense, cold liquid under crushing pressure. Sampling the water, analyzing it for chemical signatures or biological material, transmitting results back to the surface through kilometers of ice and then across space to Earth. Every step presents technical obstacles. But suppose we overcome them. Suppose a probe successfully lands, drills through the ice, reaches the ocean, begins exploring. What would it actually look for? Life, if it exists in Ganymede's ocean, might not be obvious. It wouldn't be fish swimming past the camera or alien whales breaching near the probe. It would most likely be microbial, single-celled organisms, possibly forming communities like the microbial mats found near Earth's hydrothermal vents, but nothing large or complex enough to see with a camera. Detection would rely on chemistry, looking for organic molecules that shouldn't exist without biological processes. Measuring ratios of chemical isotopes that indicate metabolic activity. Searching for patterns in molecular structure that suggest evolutionary optimization rather than random chemical reactions. On Earth, we can distinguish biological from non-biological processes with high confidence because we understand Earth biochemistry thoroughly. We know what molecules life uses, how they're structured, what isotope ratios result from different metabolic pathways. Ganymede life, if it exists, might work completely differently. It might use molecules we'd never associate with biology. It might produce isotope ratios that look random to us but actually represent alien metabolism. We might find clear evidence of life and not recognize it because we're looking for Earth patterns in an alien system. Or we might find ambiguous results. Organic molecules that could be biological or could be from non-biological chemistry. Isotope ratios that suggest metabolism or could result from geological processes. Energy gradients that look like they're being exploited by life or might just be natural chemical reactions finding equilibrium. The Viking landers on Mars in the 1970s faced exactly this problem. They conducted experiments designed to detect Martian microbes. Some results looked positive. Others were inconclusive. Decades later, scientists still debate whether Viking detected life or just unusual chemistry. A similar situation on Ganymede would be frustrating. We'd have invested billions of dollars and decades of work to reach a moon of Jupiter, drill through its ice, sample its ocean, and come back with results that don't definitively answer the question we went there to investigate. But even ambiguous results would be valuable. They'd tell us something about Ganymede's ocean chemistry. They'd reveal whether organic molecules exist there and in what concentrations. They'd help us understand the energy available for potential life and whether chemical conditions could actually support biology. Negative results would also matter. If we thoroughly sampled Ganymede's ocean and found no evidence of life, no organic molecules, no chemical signature suggesting biology, that would itself be significant. It would suggest that even with liquid water, the right chemistry, and billions of years, life doesn't automatically emerge. It would imply that life requires conditions beyond just liquid water and chemical building blocks. That the jump from chemistry to biology requires something special we don't yet understand. Which brings us back to the fundamental question driving this entire investigation. How does life begin? We know it happened at least once, on Earth, roughly 4 billion years ago. We don't know if it was inevitable or fantastically unlikely. We don't know if it requires specific conditions that are rare in the universe or if it emerges readily wherever basic requirements are met. Finding life on Ganymede would suggest it's relatively common. Two independent origins in the same solar system would imply life emerges frequently throughout the universe. Not finding life on Ganymede, especially after thorough searching, would suggest it's rare. That Earth might be unusual or even unique among the countless worlds in our galaxy. Both answers would be profound. Both would reshape how we understand our place in the universe. But one answer requires us to actually go there and look. Not just theorize or speculate based on distant observations. We need direct investigation. Ganymede challenges us in ways that push against our current technical limits. The radiation environment around Jupiter. The extreme cold. The massive ice shell. The crushing pressures in the deep ocean. Each obstacle has solutions, but implementing those solutions in a single integrated mission that actually works requires innovation and resources and time. Multiple space agencies have proposed concepts. Europa Clipper, launching soon, will study Jupiter's moons including Ganymede, gathering data that will help plan future missions. JUICE, the Jupiter Icy Moons Explorer, will orbit Ganymede directly, mapping its surface and ice shell in unprecedented detail. These are reconnaissance missions. They'll tell us where to look. They won't answer whether life is actually there. That requires landing. That requires drilling. That requires direct sampling. The earliest realistic timelines put such a mission in the 2040 period. Possibly later depending on funding and technical development. Which means if you're watching this now, the answer to whether life exists on Ganymede might not come in your lifetime. Or it might come tomorrow if we get extraordinarily lucky with existing data. Science operates on timescales that don't align with human patience. We want answers now. The universe provides them when it's ready, following its own schedule that doesn't care about our curiosity or our lifespans. Yet we keep looking. We keep planning missions and developing technology and training scientists who will analyze data from instruments that don't exist yet, studying a world most people will never even see clearly except in images taken by robots we send across the solar system. The search continues because some questions demand answers regardless of how difficult finding them might be. Maybe the answer isn't hiding in some distant ocean after all. Maybe we're approaching this entire question from the wrong angle, fixating on complexity when the real story is far stranger. Because there's another possibility we haven't fully confronted. Life might not be limited to places like Earth or Ganymede. It might exist in forms and locations so fundamentally different from what we know that we wouldn't recognize it even if we were looking directly at it. Consider Titan, Saturn's largest moon. It has lakes and rivers and rain, a complete hydrological cycle just like Earth. Except the liquid isn't water. It's methane and ethane, hydrocarbons flowing across a world where the surface temperature sits at -179 degrees Celsius. Chemistry at those temperatures operates under completely different rules. Reactions that happen instantly on Earth take geological timescales on Titan. Molecules that are gases here are liquids there. And yet Titan's atmosphere shows chemical imbalances that don't make sense without some active process continuously producing certain compounds. Something is consuming hydrogen at the surface. Something is depleting acetylene. The measurements are real. The interpretations are contested. Could be geological. Could be atmospheric chemistry we don't understand. Could be life, but life's so alien it doesn't resemble anything in our experience. Imagine organisms that use liquid methane instead of water as a solvent. That builds cell membranes from compounds stable at cryogenic temperatures. That metabolize in slow motion across timescales measured in Earth years rather than seconds. Would we even recognize their biochemistry as life? Our definitions are built around Earth biology. Carbon chains in water. DNA and RNA. Proteins folded in specific configurations. Energy from breaking chemical bonds in particular ways. Strip away those specifics and what's left? What's the irreducible core that separates living systems from complex chemistry? Self-replication, maybe. The ability to make copies. But crystals do that and we don't call them alive. Metabolism, extracting energy from the environment. But fire does that. Response to stimuli. Lots of chemical systems respond to their surroundings without being alive. The technical definition usually involves all of these together plus evolution, the capacity to change over generations through variation and selection. Yet even that gets murky at the edges. Viruses evolve but exist in a gray zone between chemistry and biology. Prion replicate and cause harm but contain no genetic material at all. We might be searching for Earth life in other locations when the universe has invented entirely different solutions to the same fundamental problem. How to persist. How to make order in a universe that tends toward disorder. How to harness energy flows to maintain complexity. Saturn's moon Enceladus shoots geysers of water into space from an underground ocean. The Cassini spacecraft flew through those plumes and detected organic molecules, salts, silica particles. Everything you'd expect from hydrothermal activity on an ocean floor. Almost identical to environments on Earth where life thrives around deep sea vents. But Enceladus is tiny. Its ocean might be only 10 kilometers deep. The entire moon is barely 500 kilometers across. Could something that small sustain life for billions of years? Does it matter? If life exists there, it exists. Size is a human concern. Biology doesn't care about our intuitions regarding what's possible. Venus presents a different kind of puzzle. The surface is hellish, hot enough to melt lead, pressure crushing enough to destroy spacecraft within hours. But 50 kilometers up in the atmosphere, conditions are surprisingly mild. Temperature and pressure similar to Earth's surface. Sulfuric acid clouds, yes, but microbes on Earth survive in acid. Thrive in it, even. And there's this persistent mystery in Venus's atmosphere. Phosphine, a gas that on Earth is only produced by life or human industrial processes. The detection has been challenged, reanalyzed, debated intensely. Maybe it's there, maybe it's not, maybe the instruments were misread. But if it is there, if it's real, then something is producing it. Life floating in the clouds of Venus would be genuinely alien, organisms that never touch solid ground, reproducing in droplets of sulfuric acid, cycling through the atmosphere for their entire existence. These scenarios push against our assumptions. We think of life as something that happens on surfaces, in oceans, in contact with rock. But why? Because that's how it works here. The universe might not care about our provincial expectations. And then there are the truly strange possibilities. Worlds where ammonia replaces water. Planets with silicon-based chemistry instead of carbon. Environments where life operates at temperatures near absolute zero or in the nuclear furnaces of stellar cores. Pure speculation, sure, but speculation constrained by physics and chemistry, not fantasy. The point isn't that any specific scenario is likely. The point is we don't know the boundaries of what's possible. Every time we think we've found life's limits, something on Earth survives in a place we thought was sterile. Microbes in nuclear reactor cooling pools. Organisms in subglacial lakes isolated for millions of years. Life in the driest deserts, the deepest ocean trenches, inside solid rock kilometers below the surface. Earth life adapted to those places, evolved to tolerate extremes. But what if life started in extremes elsewhere? What if the universe is full of biology that would find Earth hostile and bizarre, organisms for whom our comfortable temperatures and abundant water are toxic? Finding any form of life beyond Earth would be revolutionary. Finding life radically different from our own would be even more so. It would prove life isn't a single solution but a category of solutions. That the universe experiments with multiple approaches to the same fundamental challenge. The search has to account for this uncertainty. We can't only look for Earth twins. We need strategies for detecting life we don't recognize, biosignatures we haven't imagined. Which is extraordinarily difficult because you can't search for something when you don't know what you're searching for. Atmospheric chemistry offers one approach. Life, any life, has to exchange matter and energy with its environment. Those exchanges leave traces, chemical imbalances that persist because something is actively maintaining them. Oxygen in Earth's atmosphere is a biosignature because without life constantly producing it, oxygen would react away. It's chemically unstable over geological time. Other worlds might have different biosignatures. Gases that shouldn't coexist found together. Ratios of isotopes that don't match non-biological processes. Seasonal variations in atmospheric composition that suggest biological cycles. We can look for patterns without knowing exactly what's causing them. But that requires getting close enough to analyze atmospheres in detail. For planets around other stars, that means next-generation space telescopes powerful enough to separate a planet's light from its star's glare and break that light into spectra revealing chemical composition. The technology exists. The telescopes are being built. Within a decade we'll have the capability to study potentially habitable exoplanet atmospheres. And then what? We detect oxygen and methane together on a world 30 light-years away. Strong suggestion of life, not proof. Could be geological. Some process we don't understand producing those gases without biology. We'll debate it, analyze it, propose follow-up observations. But we won't know for certain. Not the way we'd know if we could land and look directly. The frustrating truth is certainty might be impossible for life beyond our solar system. We could find compelling evidence, strong suggestions, patterns that look biological. Absolute proof would require sending probes to other star systems, missions that would take thousands of years with current technology. Or developing fundamentally new propulsion methods, which might happen eventually but not soon. So we're left with probabilities and indirect evidence and scientific arguments that won't satisfy everyone. Which is fine, actually. Science doesn't require certainty to make progress. It requires better questions and methods for answering them. Within our solar system we can achieve certainty. We can send robots to drill and sample and analyze with instruments sophisticated enough to detect life if it's there. Mars, Europa, Enceladus, Titan, Ganymede. Each world gets us closer to answering whether life is common or rare, whether Earth is typical or exceptional. And maybe the answer is both. Maybe simple life, microbes, basic cells, emerges readily throughout the universe wherever conditions permit. But complex life, multicellular organisms, intelligence, remains vanishingly rare. That would explain why we see no obvious signs of technological civilizations despite billions of habitable planets in our galaxy. Or maybe we're alone. Maybe life requires such a specific sequence of unlikely events that Earth is genuinely unique. For billion years of evolution on the only living world in the observable universe. That possibility terrifies some people. The cosmic loneliness of it. Personally, it seems no more lonely than the alternative. If life is everywhere, we're still separated by distances that make communication nearly impossible. If life is rare, at least we're special. Both scenarios leave us fundamentally isolated in a vast universe, responsible for preserving the only consciousness we know exists. The search continues not because we expect easy answers but because not searching would be worse. Accepting ignorance when knowledge is possible. Living with questions we could answer if we tried. That's not how humans operate. We're curious to the point of obsession, willing to spend decades and billions pursuing answers to questions most people never think about. And perhaps that obsession is itself evidence of something profound. The fact that we care about questions with no immediate practical benefit. That will dedicate careers to understanding whether microbes exist beneath Martian ice. That we build telescopes to analyze the atmospheres of worlds we'll never visit. This curiosity might be the most distinctively human trait we possess, more defining than tool use or language or social organization. Other intelligent species, if they exist, might not share it. They could be perfectly content within their own worlds, never wondering what lies beyond. Evolution doesn't guarantee curiosity. It guarantees survival strategies, and sometimes curiosity helps survival by driving exploration and innovation. But it's not inevitable. We could have evolved to be incurious, satisfied, uninterested in questions beyond immediate needs. We didn't. Something in the particular path human evolution took produced minds that can't stop asking why. Minds that see a star and wonder what it's made of. That find a fossil and reconstruct entire extinct ecosystems. That detect a chemical signature on a distant moon and immediately start planning missions to investigate. This compulsion has costs. Resources spent on space exploration could address immediate terrestrial problems. The billions invested in Mars rovers don't feed hungry people or cure diseases or solve climate change. Critics make this argument constantly, and it's not entirely wrong. Priorities matter. But the assumption that we must choose between cosmic exploration and earthly welfare creates a false dichotomy. Human civilization is wealthy enough to pursue multiple goals simultaneously. The amount spent on space science represents a tiny fraction of global economic activity. NASA's entire annual budget is less than what's spent on pet food in the United States. We're not choosing between feeding people and exploring Mars. We're choosing between various forms of discretionary spending, and some of that spending generates knowledge rather than consumption. Knowledge has value beyond immediate application. Understanding how planets form helps us understand our own planet's history. Studying extreme environments on other worlds informs our understanding of life's limits. Developing technology for space missions produces innovations that find terrestrial applications. GPS, weather forecasting, communications satellites, medical imaging techniques, all emerged from space programs. But even without practical spin-offs, the knowledge itself matters. Knowing whether we're alone in the universe changes how we think about existence, meaning, our place in reality. It's the kind of knowledge that shifts perspective, that makes us see ourselves differently. And that has value even if it doesn't produce marketable products. The search for life also forces us to confront uncomfortable possibilities about our own future. If we find dead worlds that once had life, worlds where biological activity left traces before going extinct, that tells us something about planetary evolution. Life emerges, thrives for a while, then disappears. Not a comforting pattern. Mars might be such a world. Early in its history, warmer, wetter, potentially habitable. Then it lost its magnetic field, its atmosphere stripped away by solar wind, surface water evaporating or freezing, whatever life existed either dying or retreating underground. A world that had its chance and lost it. Earth could follow the same trajectory. Not tomorrow, not in human timescales, but eventually. Our sun is gradually brightening, increasing energy output as it ages. In 1 billion years, maybe less, Earth's oceans will boil away. The planet will transition from habitable to sterile, life's 4 billion year run ending not with catastrophe but with slow inexorable change. Unless life spreads beyond Earth first. Unless consciousness finds ways to persist across multiple worlds, backing itself up against planetary disasters. This is one argument for space exploration that transcends curiosity. Survival of life itself as a phenomenon, as a process, as the universe's method for organizing matter into increasingly complex patterns. We're the only species capable of deliberately spreading life to other worlds. Every other organism is confined to Earth, dependent on this single planet's continued habitability. We have the technology to change that. Not easily, not soon, but possible within foreseeable futures. Establishing self-sustaining colonies on Mars or in orbital habitats or on moons throughout the solar system. Whether we should do this is a separate question. Planetary protection protocols exist specifically to prevent contaminating other worlds with Earth life before we've had a chance to study them in pristine condition. If Mars has indigenous life, even just microbes, introducing Earth organisms could destroy or outcompete them before we discover they exist. But if Mars is dead, if Europa and Enceladus contain only chemistry without biology, if we're genuinely alone in this solar system, then spreading life becomes not contamination but continuation. Taking the process that started on Earth and extending it outward, giving it redundancy, ensuring that life in general isn't dependent on one planet's survival. This assumes life has value, that preserving and spreading it matters. Not everyone accepts that premise. From a purely physical perspective, life is just complex chemistry. The universe doesn't care whether organized matter continues existing or breaks down into simpler forms. Stars will keep burning, galaxies will keep rotating, the cosmos will expand regardless of whether life persists anywhere. Yet we care. Consciousness cares about its own continuation. We value existence over non-existence, complexity over simplicity, preservation over destruction. These preferences aren't logically necessary. They're built into us by evolution because organisms that don't prioritize survival don't leave descendants. But the fact that our values are evolutionary products doesn't make them meaningless. We're parts of the universe that have become aware of themselves. Matter organized in specific ways that allow reflection, contemplation, understanding. The universe experiencing itself through consciousness. Poetic language, but also accurate description of what's happening when human brains process information about reality. If consciousness is rare, if Earth represents the only location in vast cosmic volumes where this self-awareness exists, then its preservation becomes critically important. Not because some external authority values it, but because we value it, and we're the only judges available. If consciousness is common, if billions of worlds host thinking beings, then our individual survival matters less to the cosmic story. But it still matters to us, to the particular instance of awareness that exists here and now. Either way, the search continues. Rovers drill into Martian soil. Probes fly through the plumes of icy moons. Telescopes scan distant atmospheres. Scientists analyze data, refine hypotheses, design better instruments. Each mission adds information, narrows possibilities, brings us incrementally closer to answering questions that might not have answers we like. Maybe we find life everywhere we look. Simple, persistent, unremarkable. The universe teeming with microbes that never evolve past basic cellular organization. That would tell us life is easy but complexity is hard. That the gulf between chemistry and biology is narrow but the gulf between microbes and intelligence is vast. Maybe we find nothing. Decades of searching, increasingly sophisticated instruments, samples from dozens of worlds, all sterile. Earth alone, life a statistical fluke, consciousness an accident that happened once. That would tell us we're precious beyond measure, the universe's only attempt at self-understanding. Maybe we find something we don't expect. Life based on different chemistry, using different solvents, storing information in molecules we haven't considered. That would expand our understanding of what's possible, show us that biology isn't limited to the one example we know. Any of these outcomes changes everything. Not immediately, not in ways that affect daily existence for most people. But fundamentally, philosophically, in how we conceptualize ourselves and our significance. The wait continues. Missions are years in planning, years in transit, months or years analyzing results. Science operates on timescales that don't align with human patience. We want immediate answers to questions that require decades of careful work. But some questions are worth the wait. Some knowledge is worth pursuing even when acquisition is slow and expensive and uncertain. The search for life beyond Earth is that kind of question. Fundamental enough to justify the investment, profound enough to change everything if answered. So we keep looking. Building better instruments, sending more sophisticated probes, analyzing data with increasing precision. Each generation of scientists adding to the work of previous generations, standing on accumulated knowledge, pushing the boundary of what's known slightly further outward. And maybe, eventually, we'll know. Not through dramatic revelation but through accumulated evidence that finally crosses the threshold from possibility to certainty. A moment when the data becomes undeniable, when all reasonable doubt evaporates, when we can say with confidence that yes, life exists beyond Earth. Or no, we're alone after all. Both answers transform us. Both force reconsideration of assumptions we didn't know we were making. Both open new questions even as they resolve old ones. That's how knowledge works. Each answer generates more questions. Each discovery reveals new mysteries. We're not approaching some final understanding where all questions get resolved. We're expanding the boundary between known and unknown, and the boundary circumference grows faster than its area. The universe is larger and stranger than we imagine. Probably larger and stranger than we can imagine. Our brains evolved to handle problems at human scales, understanding objects we can see and touch, timescales we can experience. Cosmic questions push against those cognitive limits. But we keep pushing anyway. Because that's what consciousness does. It reaches beyond itself, grasps for understanding that might be perpetually just out of reach. And sometimes, occasionally, it succeeds. Sometimes the universe yields its secrets, reveals its patterns, shows us something true. The search for life is that kind of reaching. An attempt to understand our context, our cosmic neighborhood, whether we share this vast space with others. And whether we find life or find ourselves alone, either answer is worth knowing. So that's where we are. Standing at the edge of something that could redefine everything we thought we knew about our place in existence. Ganymede's ocean isn't speculation anymore. It's confirmed. Real liquid water, vast beyond comprehension, sitting beneath ice in the darkness of space. And we're close enough to reach it, smart enough to design missions that could actually get there, curious enough to keep pushing even when the timeline stretches across decades. The answer might come from Ganymede, or Europa, or Enceladus, or from some unexpected corner of the solar system we haven't looked at carefully enough. It might not come at all, at least not in our lifetimes. But the searching itself matters. The fact that we're capable of asking these questions, of building the tools to investigate them, of dedicating resources and careers to understanding whether we're alone. Every mission teaches us something. Every dataset narrows the possibilities. Every failure informs the next attempt. We're not stumbling blindly anymore. We're methodically eliminating uncertainty, building toward conclusions that will stand regardless of what we want them to be. And maybe that's the real story here. Not whether life exists on Ganymede, but that we've become the kind of species that can find out. That we've developed the technology, the knowledge, the sheer stubborn determination to send machines across hundreds of millions of kilometers and ask questions about oceans we'll never see directly. The universe doesn't owe us answers. It doesn't care about our curiosity or our need to understand. But it's revealing itself anyway, piece by careful piece, to minds capable of interpreting the evidence. We're part of the cosmos trying to understand itself. And sometimes, when we look hard enough and think carefully enough, understanding happens. Ganymede waits beneath its ice. Silent. Patient. Holding secrets that might transform us. The search continues because we are parts of the universe trying to understand itself. Piece by careful piece, the universe reveals itself to minds capable of interpreting evidence. The answer is waiting. And soon, through our courage and science, we will know. Right now, 642 light-years away, a star is dying. Not gradually fading over billions of years, but preparing for one of the most violent events the universe can produce. And we're watching it happen in real time. Betelgeuse. The name alone carries weight in astronomy circles. This red supergiant marks the shoulder of Orion, visible to anyone who looks up on a winter night. For thousands of years, it glowed steadily. Then in late 2019, something changed. The star dimmed, dramatically. Astronomers scrambled to their instruments, because they knew what this might mean. A supernova. An explosion so powerful it would briefly outshine every other star in our galaxy combined. Visible during the day, casting shadows at night. A celestial event that happens maybe once per century in a galaxy like ours, and we might be about to witness it. But here's what makes this genuinely unsettling. We have no idea when. Could be tonight. Could be 100,000 years from now. The light we see left Betelgeuse in the 1380s, when the Ming Dynasty was just beginning. If it exploded tomorrow, it actually happened during the Renaissance, and we're only now receiving the news. The star itself is almost incomprehensible in scale. Place it where our sun sits, and its surface would extend past the orbit of Jupiter. Every second, Betelgeuse burns through mass equivalent to Earth's moon. It's so large that its outer atmosphere is actually cooler than the deeper layers we can detect, creating convection cells the size of our entire solar system. Scientists discovered something else recently. The dimming in 2019 wasn't just a fluke. Betelgeuse had ejected a massive chunk of its own surface into space. A piece of star, flung outward, temporarily blocking our view. The sheer violence required to tear that much material away from a supergiant's gravity suggests internal processes we're only beginning to understand. Stellar physics gives us the framework. Betelgeuse is fusing heavier and heavier elements in its core. Hydrogen is long gone. Helium, exhausted. Now it's burning carbon, oxygen, silicon. Each stage happens faster than the last. Silicon fusion, the final step before catastrophe, takes about 1 day. 1 day between normalcy and detonation. The core contracts under its own gravity. Temperatures spike. Pressures mount. Eventually, even silicon can't hold back the collapse. In less than a second, the core implodes, then rebounds. The shockwave tears through millions of kilometers of stellar material. What took millions of years to build destroys itself in hours. That's the supernova. But the story doesn't end with the explosion. What remains is stranger. The core, compressed beyond anything we experience in everyday physics, becomes either a neutron star or a black hole. In Betelgeuse's case, given its mass, we're likely looking at a black hole. A point in space where gravity is so extreme that not even light escapes. The entire mass of a star, compressed into a region smaller than a city. Meanwhile, the outer layers race outward at roughly 10% the speed of light. This expanding shell carries every element the star forged over its lifetime. Iron, gold, uranium, everything heavier than helium. These materials will eventually seed new star systems, new planets, possibly new life. Every atom in your body heavier than hydrogen was created in a star that died before our sun was born. The supernova remnant becomes a nebula. Glowing debris spreading across light years, enriching the interstellar medium. Within these clouds, gravity begins pulling material together again. The cycle continues. Now consider what this means for us. At 642 light-years, Betelgeuse is close. Not dangerously close, but close enough to matter. When it goes, we'll see effects beyond just a bright light in the sky. The explosion releases more than visible light. Gamma rays, X-rays, ultraviolet radiation, all pour out in the initial burst. Earth's atmosphere will absorb most of this, but satellites might not fare as well. Communication systems could experience disruptions. GPS might lose accuracy. Nothing catastrophic, but noticeable. Then there's the neutrino flux. These ghostly particles barely interact with matter, but a supernova produces them in staggering numbers. Trillions will pass through your body every second for weeks. Detectors worldwide will register the surge, giving astronomers unprecedented data about the explosion's mechanics. The visible brightness is what captures imagination, though. At peak, Betelgeuse will reach apparent magnitude -12, roughly as bright as a half moon. You'll see it during the day. At night, it'll cast noticeable shadows. For weeks, possibly months, our sky will have two moons, one white, one red. Cultures throughout history have marked supernovae. The 1006 event was recorded on three continents. The 1054 explosion created the Crab Nebula and appeared in Chinese and Middle Eastern texts. Native Americans left pictographs depicting it. These weren't just scientific observations but events that shaped mythology and worldview. What happens to us when Betelgeuse goes? Nothing physically dangerous, but something profound psychologically. We'll have front-row seats to cosmic violence on a scale that makes our largest nuclear weapons look like firecrackers. It'll be a reminder, visible every night, that the universe operates on timescales and energy scales that dwarf human concerns. Astronomers are preparing. Telescopes across every wavelength stand ready. When the light arrives, we'll have perhaps hours of warning from neutrino detectors before the visible light reaches us. Every major observatory will pivot to Orion. This will be the most studied astronomical event in human history. The data will be invaluable. We've never observed a supernova this close with modern instruments. Our models of stellar evolution, nuclear physics, even general relativity, will face their most rigorous test. Whatever we think we know about how massive stars die, Betelgeuse will either confirm it or force us back to the drawing board. There's also the question of what we'll find afterward. The neutron star or black hole left behind will be young, hot, energetic. We might detect pulsar emissions, jets of material shooting from the poles at near light speed. The nebula itself will be a laboratory for studying shock physics, dust formation, and chemical enrichment of space. But I mentioned earlier that the timing is uncertain. Let's dig into why that's so frustrating. Stellar models tell us Betelgeuse is near the end. Its behavior, the dimming events, the mass loss, all point to a star in its final stages. But final stages, for a supergiant, might mean tomorrow or 100,000 years from now. The physics becomes chaotic. Small changes in core conditions produce wildly different outcomes. We're essentially trying to predict the exact moment a Jenga tower falls. We know it's unstable. We can see pieces missing. But that final trigger, the precise instant when structural integrity fails completely, that's incredibly difficult to forecast. The 2019 dimming gave us hope for better predictions. If we could understand what caused it, maybe we could identify pre-supernova signatures. The research that followed revealed the surface ejection, but also showed us how much we still don't know. Betelgeuse is variable on multiple timescales. It pulsates. It sheds mass irregularly. Separating normal variability from end-stage behavior is like diagnosing a patient whose symptoms keep changing. Some astronomers think we're seeing the final centuries. Others argue we might have tens of thousands of years left. The uncertainty stems from how we measure stellar evolution. We can't watch a single star age. We observe millions of stars at different life stages and piece together the sequence. It's like understanding human aging by taking snapshots of random people and arranging them by apparent age. You'll get the general progression right, but predicting any individual's remaining lifespan becomes much harder. Recent observations added another wrinkle. Betelgeuse might have a companion star. If true, the dynamics change completely. Binary interactions can trigger supernovae earlier than expected, or delay them, or create entirely different outcomes. We thought we understood this star, and then realized we might have been looking at a system, not a singleton. The implications stretch beyond academic curiosity. Understanding supernovae helps us understand galactic evolution, element formation, even cosmology. Type Ia supernovae, a different class from what Betelgeuse will produce, serve as distance markers across the universe. They helped us discover that cosmic expansion is accelerating, leading to the concept of dark energy. Getting the physics right matters for our entire picture of how the universe works. And there's something else. Something that connects directly to why this particular star captures our attention beyond the scientific interest. Human timescales collide with cosmic timescales in strange ways. Betelgeuse might explode while you're reading this. Or it might wait until our civilization is dust. From the universe's perspective, there's no difference. A few thousand years either way is a rounding error. But for us, the difference between witnessing this event and having it remain theoretical is everything. We stand at a unique moment. We had the technology to study a nearby supernova in detail, but we lack the ability to predict when it'll happen. Our instruments are ready. Our models are sophisticated. But nature keeps its schedule, indifferent to our preparations. There's a philosophical tension here that's worth examining. We study the universe by observing light that left its source years, centuries, or millennia ago. When we look at Betelgeuse, we're seeing photons that began their journey around 650 years ago, give or take. The star might have already exploded. The shockwave could be racing toward us right now, and we wouldn't know until the light arrives. This isn't speculation. It's the fundamental constraint of information traveling at light speed. We're always looking backward in time. That delay creates an odd psychological state. Astronomers monitoring Betelgeuse know that the supernova they're waiting to observe might have already happened during the Middle Ages. The light carrying that information could arrive next week, or next century. There's no way to check. No faster-than-light telephone line to call and ask if the star is still there. We wait, instruments ready, knowing that the event we're preparing for might be a historical fact we just haven't learned about yet. Let's shift perspective for a moment. What would it actually look like from Earth? The first indication would come from neutrinos. These ghostly particles barely interact with matter, which means they stream out from the core collapse essentially unimpeded. Neutrino detectors around the world, designed primarily for particle physics research, would register a sudden spike. These facilities are networked specifically for this purpose. When one detector sees an anomalous burst, it alerts the others. If multiple detectors confirm simultaneously, astronomers worldwide get an automated notification. Supernova imminent. Look up. The neutrino warning would give us maybe a few hours head start. Possibly a day. Then the light would arrive. Not gradually. Supernovae brighten dramatically, exponentially. Within hours, Betelgeuse would go from roughly magnitude 0 to potentially magnitude -11 or 12. For context, the full moon sits at magnitude -13. We're talking about a single point of light nearly as bright as the moon, visible in broad daylight. Orion would be unrecognizable. The constellation would have a second sun blazing where the Hunter's Shoulder used to be. That peak brightness would last weeks, maybe months, then a slow decline over years. But even after fading, Betelgeuse would remain visible to the naked eye for potentially decades. The expanding debris cloud would eventually form a nebula, visible through telescopes for thousands of years. This isn't a brief light show. It's a multi-generational transformation of our night sky. The scientific return would be staggering. Every telescope on Earth and in orbit would immediately swing toward Orion. We'd capture the light curve with unprecedented detail, tracking how brightness changes second by second. Spectroscopy would reveal the composition of ejected material, testing our models of nucleosynthesis. Did the supernova produce the expected ratios of elements? Are there surprises in the chemical signature? X-ray and gamma-ray observations would probe the shock wave physics. Radio telescopes would track the expanding shell as it plows into surrounding material. And then there's the neutrino data itself. These particles carry information about the core collapse that light cannot provide. Light gets trapped, bounced around, delayed by the dense stellar material. Neutrinos escape immediately, carrying direct information about nuclear reactions in the collapsing core. Detecting them in large numbers would let us peer into physics we can't access any other way. The temperature, the density, the exact sequence of nuclear processes, all encoded in the neutrino spectrum and timing. Previous nearby supernovae were observed with far more primitive instruments. Supernova 1987A in the Large Magellanic Cloud, while spectacular, occurred before we had modern detector networks. We caught neutrinos, which was revolutionary, but with limited sensitivity. We got optical observations, but without the resolution and wavelength coverage we have now. Betelgeuse would be the first nearby supernova in the era of space telescopes, gravitational wave detectors, and coordinated global observation networks. The data hall would rewrite textbooks. But there's something else happening alongside the scientific opportunity: cultural impact. Betelgeuse going supernova would be the most dramatic astronomical event in human history, at least in recorded history. The 1006 supernova was brighter, but occurred before the scientific revolution. Ancient observers recorded it with awe but without understanding. The 1054 supernova created the Crab Nebula. Chinese astronomers documented it. Indigenous peoples across the Americas incorporated it into their traditions. But again, no scientific apparatus to study it properly. A supernova in Orion would reach everyone. You can't miss Orion. It's visible from almost everywhere on Earth. Every culture recognizes it. Suddenly, that familiar pattern would change. Children would grow up with a sky that looks different from the one their parents knew. Photographers would capture the light illuminating landscapes. Artists would respond. Writers would find metaphors. The supernova would become part of human culture in ways we can't fully predict. There's precedent for celestial events capturing public imagination, though nothing quite at this scale. Comet Hale-Bopp in 1997 became a cultural phenomenon. People who never looked up started watching the skies. But Hale-Bopp was a visitor, here and gone. Betelgeuse would be a permanent change. The supernova would fade, but the sky would remain altered. We'd live with the consequence, the glowing remnant, for the rest of our species' existence. Now, let's address something often glossed over in popular discussions. Could this actually be dangerous? The short answer is no, but the reasoning matters. Supernovae release tremendous energy, including gamma rays. At close range, within a few dozen light years, a supernova could potentially damage a planet's atmosphere. The gamma rays would interact with atmospheric molecules, creating nitrogen oxides that deplete ozone. Without ozone protection, surface life would face increased ultraviolet radiation from the star. Betelgeuse is too far away for this to be a concern. The inverse square law is brutal. Intensity drops with the square of distance. At 650 light-years, the gamma-ray flux reaching Earth would be negligible. Detectable, certainly. Scientifically valuable, absolutely. But not hazardous. We'd receive more radiation from eating a banana than from Betelgeuse's supernova. This isn't speculation. We can calculate these things precisely. The physics is well understood. Some articles sensationalize this, either through misunderstanding or for clicks. You'll see headlines about killer stars or cosmic threats. It's nonsense. Real astronomers aren't concerned about danger. They're excited about the scientific opportunity. The distinction matters because public misconceptions about astronomy can undermine science communication. We need people to understand that space, while genuinely dangerous in many ways, doesn't threaten us with random nearby supernovae. The galaxy isn't that hostile. What could genuinely affect us is more subtle. The supernova's effect on the solar wind dynamics, perhaps. Earth's magnetosphere protects us from charged particles streaming from the sun. A supernova would add a temporary burst of high-energy particles to the cosmic ray background. Our magnetosphere would handle it, but satellites might experience slightly elevated radiation. Nothing catastrophic. Maybe some temporary communication disruptions. GPS might lose accuracy. ISS would need to monitor exposure levels. Astronauts might need to shelter in more shielded areas during peak flux. Again, manageable. Not apocalyptic. The real challenge would be observation coordination. Every major observatory would want time on every major telescope. Conflicts would arise. Who gets priority? How do you balance spectroscopic observations against photometric monitoring, against polarimetry, against imaging? Normally, telescope time is allocated months or years in advance through competitive proposals. A supernova would trigger directors' discretionary time at every facility, overriding scheduled observations. Some astronomers would be thrilled. Others, whose carefully planned observations get bumped, less so. There's also the amateur astronomy community to consider. Betelgeuse is bright enough that backyard telescopes could contribute real data. In fact, amateur observations might prove crucial for continuous monitoring. Professional telescopes can't watch one target constantly. They need to split time between multiple objects, multiple projects. Amateurs, coordinating globally, could maintain near-continuous coverage. We saw this work effectively with other transient events. The amateur community has become genuinely valuable for time-domain astronomy. Social media would transform the experience compared to historical supernovae. Real-time updates, images, data, all shared instantly worldwide. Scientists could communicate findings directly to public audiences. Misinformation would also spread rapidly, of course. Distinguishing signal from noise would be challenging. But overall, the transparency would be unprecedented. You'd be able to follow the supernova's evolution as it happens, explained by experts, discussed by millions. Educational impact deserves mention. A visible supernova would provide a teaching moment like no other. Students could observe with their own eyes a phenomenon they'd only read about. Teachers could connect textbook physics to something happening overhead. The abstract becomes concrete. Kai ban ko the chi te veo no. Bao tung qua ha kasi ze dung kak kuok trian lam. Kak kung thien van se kap not kak bui trin dien qua ho. Su kien nai se trien kam hung cho mot the he kak na thien van hoc, jong nu chuang trin apollo de trien kam hung cho kak the he na qua hoc va ky su truoc day. But we keep circling back to the central frustration. When we have this extraordinary opportunity ahead of us, maybe, or maybe not for 100,000 years. The uncertainty undermines planning. Observatories can't keep resources on standby indefinitely. Research teams can't maintain readiness for decades. Funding agencies want timelines. Yet the universe doesn't provide them. Betelgeuse will explode on its own schedule, indifferent to our preparations or impatience. We've built the instruments. We've developed the theory. We've coordinated the networks. Now we wait. And waiting, in astronomy, often defines the job more than the observations themselves. What we do know is that Betelgeuse isn't behaving like other red supergiants we've studied. Most stars in this phase show relatively predictable brightness variations. Long-period pulsations, yes. But within expected ranges. Betelgeuse keeps surprising us. The great dimming of 2019 to 2020 caught everyone off guard. The star's brightness dropped to around 40% of normal. Some astronomers genuinely wondered if we were watching the prelude to explosion. Spectroscopic analysis eventually revealed the truth. Betelgeuse had ejected material that condensed into dust, temporarily blocking our view. The star itself hadn't actually dimmed that dramatically. We were seeing an obscuration event. But that explanation raises its own questions. Why did Betelgeuse eject that much material at that particular time? Red supergiants lose mass continuously through stellar winds. The rate varies, certainly, but that particular ejection seemed unusually vigorous. Was it a surface convection event? Some models suggest that massive convection cells in red supergiant envelopes can bring hot material to the surface, creating localized bright spots. When those regions rotate out of view, the star appears dimmer. Combine that with dust formation and you get dramatic brightness changes. Except we're not entirely certain that's what happened. Alternative models exist. Maybe the dimming involved magnetic activity. Betelgeuse does have a magnetic field, though measuring it precisely is difficult. Could magnetic loops trap material, then release it suddenly? Solar flares operate on this principle, scaled way down. A stellar version might produce the observed effects. We're speculating, though. The truth is we saw something unprecedented and we're still working out what it meant. This uncertainty pervades supernova prediction. We're trying to forecast an event we've never actually witnessed up close in real time with modern instruments. SN 1987A happened in a large Magellanic Cloud, 168,000 light-years away. Close enough to study extensively, far enough that resolution was limited. Betelgeuse at 550 light-years would give us detail we've never had before. But only if it explodes while we're ready. The waiting game has psychological dimensions worth examining. Astronomers dedicate careers to studying objects that might not do anything interesting during their professional lifetime. You could spend 30 years developing expertise in supernova physics and never witness the one event that would define your field. That's the gamble. Some researchers pivot to other topics, hedging their bets. Others commit fully, accepting that the universe operates on timescales indifferent to human careers. There's nobility in that commitment. Also frustration. Imagine explaining to funding committees why your telescope time should go toward monitoring a star that probably won't explode this year, or next year, or the year after that. Competing proposals promise guaranteed results. Yours offers a possibility. Funding agencies generally prefer certainty. Yet Betelgeuse observations continue. Not constantly, but regularly. The star remains on monitoring lists. Photometry gets collected. Spectra get recorded. Data accumulates slowly, building a baseline against which any future changes will be measured. That baseline has value regardless of whether Betelgeuse explodes soon. We're learning about red supergiant behavior in unprecedented detail. The variations, the mass loss, the atmospheric dynamics, all of it contributes to stellar evolution models. When the next red supergiant explodes somewhere else, we'll understand it better because of Betelgeuse. The question of what we'd actually see during the explosion deserves more detailed exploration. The initial brightening would be gradual, probably over hours. Neutrinos would arrive first, traveling essentially at light speed and passing through matter almost without interaction. Neutrino observatories around the world maintain constant vigilance for the characteristic burst signature. They detect it before anyone saw anything visually. Minutes to hours later, the shock wave from the core collapse reaches the stellar surface. The star's outer layers begin exploding outward. This is when brightness starts increasing dramatically. Over the course of a day or so, Betelgeuse would brighten from magnitude 0.5 to perhaps magnitude -11 or -12. Roughly the brightness of a half-moon, concentrated in a single point. You could read by it at night. Easily. During the day, it would be visible to the naked eye, a bright star hanging in daylight sky. The color would shift too. Betelgeuse appears reddish now because its surface temperature is relatively cool for a star, around 3,500 Kelvin. During the supernova, the expanding material heats up. The color would shift toward white, maybe even slightly blue. The expanding debris would be glowing from the energy of the explosion itself, not from fusion anymore. Peak brightness would last weeks, maybe a couple months. Then gradual fading over years. But even after fading below naked eye visibility, the supernova remnant would remain a target for telescopes for centuries. The expanding shell of debris, glowing in various wavelengths, would evolve constantly. Radio observations would track the shock wave as it plows through surrounding space. X-ray telescopes would study the hot interior regions. Infrared would pierce any dust that forms. Optical telescopes would monitor the overall structure. Each wavelength reveals different physics. The remnant would become a laboratory for studying extreme conditions we can't replicate on Earth. Nuclear physics, particle acceleration, shock wave dynamics, all happening in real time at scales we can actually resolve. Most supernova remnants we study are ancient, their explosions having occurred thousands of years ago. A fresh one at Betelgeuse's distance would be transformative. Consider the scientific papers that would emerge. Hundreds in the first year alone. Thousands over the following decade. Every subfield of astronomy would find something relevant. Stellar evolution theorists would refine their models of red supergiant death. Galactic chemical evolution researchers would study how the explosion enriches surrounding space with heavy elements. Particle physicists would analyze neutrino data to constrain physics beyond the standard model. Cosmologists would use it to calibrate distance measurements, since Type II supernovae serve as standardizable candles under certain conditions. The interdisciplinary reach would extend beyond astronomy. Geologists would look for isotopic signatures in ice cores or sediment layers, markers of cosmic ray exposure from the supernova. Historians might correlate the event with cultural responses, studying how different societies interpret and record the phenomenon. Artists would create works inspired by it. Musicians might compose pieces. The cultural impact would ripple outward in ways we can't predict. But there's a darker consideration that occasionally surfaces. What if we're wrong about the safety? Not about the distance, that's measured reliably, but about the radiation effects. Current models say we're safe. Models have been wrong before. The ozone layer might be more vulnerable than we think. Or the magnetosphere less protective. Unlikely, yes. Our understanding of these systems is solid. But certainty in science always comes with error bars. The responsible position is acknowledging what we don't know while being clear about what we do. We're confident Earth is safe from catastrophic effects. Confident, not absolutely certain. That distinction matters. Scientists who claim absolute certainty lose credibility when exceptions emerge. Better to be honest about uncertainty while explaining why we consider the risk negligible. Public communication requires that balance. Climate scientists face this challenge constantly. How do you convey high confidence without claiming perfection? How do you acknowledge uncertainty without undermining the message? With Betelgeuse, the stakes are lower because we're not asking anyone to change behavior. No policy decisions hinge on supernova predictions. But the communication challenge remains. Media coverage of Betelgeuse tends toward sensationalism. Headlines scream about stars exploding near Earth, implying danger where none exists. Scientists issue corrections. The cycle repeats. Each brightening fluctuation triggers another round. After a while, public attention drifts. The boy who cried wolf effect takes hold. When the supernova actually happens, will people care? Or will they assume it's another false alarm? Maintaining public interest over uncertain timelines is nearly impossible. The first few times Betelgeuse dims or brightens unusually, media covers it extensively. By the 10th time, it's old news. Editors reject the story. The public assumes nothing real is happening. Then one day, it actually explodes, and everyone's surprised despite decades of warnings. This dynamic frustrates science communicators. How do you keep people informed without exhausting their attention? Some researchers have stopped doing media interviews about Betelgeuse entirely. The questions are always the same. Is it exploding now? When will it explode? What will we see? The answers never satisfy because they involve uncertainty. Journalists want definitive statements. Scientists offer probabilities and caveats. The disconnect is fundamental. Yet when the explosion happens, those same researchers will be flooded with interview requests. Everyone will want expert commentary. The preparation happening now, the monitoring, the theoretical work, the instrument development, all of it will suddenly become urgent and newsworthy. The irony is that the real scientific value lies in the preparation, not the event itself. The supernova will be spectacular, certainly. But the decades of work leading up to it, building our understanding of stellar evolution, developing detection capabilities, training new generations of astronomers, that's where the lasting impact lives. Betelgeuse will eventually teach us something we can't predict. Every major astronomical event does. When gravitational waves were first detected, nobody expected the precision with which we could measure neutron star mergers. The technology worked better than anticipated. The data revealed phenomena theorists hadn't considered. Supernova 1987A taught us about neutrino physics in ways no one foresaw. The neutrino burst arrived hours before the light, exactly as predicted. But the detailed measurements refined our understanding of particle interactions inside collapsing stars. Models improved. New questions emerged. Betelgeuse will do the same, just in different ways. Perhaps we'll discover unexpected asymmetries in the explosion. Maybe the dust production will challenge our models of element formation. The neutrino signal might contain surprises. We won't know until it happens. This uncertainty is what makes the event scientifically valuable. If we could predict everything perfectly, there'd be no point in observing. Science advances through surprises, through data that doesn't quite match expectations. Those mismatches force us to reconsider assumptions, revise theories, build better models. The process is iterative and endless. Consider the stellar evolution models we use. They're sophisticated, incorporating decades of research. But they're still approximations. Real stars are messier than equations suggest. Convection patterns inside Betelgeuse are turbulent and chaotic. Our models smooth them out, treating them statistically. That works for predictions but misses fine details. When Betelgeuse explodes, we'll see whether those details mattered. Did the asymmetric convection create asymmetric explosions? Did rotation play a bigger role than we thought? These questions have answers we can't access until the event occurs. Some researchers are already planning follow-up studies for decades after the supernova. The expanding remnant will be visible for centuries. Its evolution will test our understanding of how supernova remnants interact with surrounding material. Currently, we study old remnants from supernovae that exploded centuries or millennia ago. With Betelgeuse, we'll watch one develop from the beginning. That temporal coverage is rare and valuable. The remnant will sweep up surrounding gas, heating it, compressing it, possibly triggering new star formation. These processes occur in every supernova remnant. But observing them in real time, with modern instruments, will provide unprecedented detail. Computer simulations can be compared directly to observations. Models will improve. Future predictions will become more accurate. There's also the question of what Betelgeuse leaves behind. Supernovae from stars this massive typically produce neutron stars. But some create black holes instead. The boundary between these outcomes isn't perfectly understood. It depends on the star's exact mass, its composition, how much mass it lost before exploding, and details of the collapse process. Current estimates suggest Betelgeuse might be right on that boundary. If it produces a neutron star, we'll have a new pulsar to study. If it forms a black hole, that's equally interesting. Either way, the remnant will teach us about the final moments of massive stellar cores. Neutron stars are extreme physics laboratories. Densities exceed atomic nuclei. Magnetic fields reach unimaginable strengths. Matter behaves in ways we can't reproduce on Earth. Every new neutron star adds to our understanding. Black holes are equally fascinating but harder to study directly. We'd infer its presence through effects on surrounding material. Gas falling toward it would heat up, emitting X-rays. Over time, the black hole might accrete enough material to become visible through those emissions. But that takes years or decades. Immediate detection would rely on gravitational wave observatories. If Betelgeuse's core collapse is asymmetric enough, it might produce detectable gravitational waves. Current detectors probably aren't sensitive enough at that distance. But future observatories might be. LIGO and Virgo are upgrading. New detectors are being built. By the time Betelgeuse explodes, we might have the capability to detect its gravitational wave signature. That would be extraordinary. We've never detected gravitational waves from a supernova. The asymmetry required is substantial. Most supernovae probably don't produce detectable signals. But if Betelgeuse does, it would open an entirely new window into core collapse physics. We'd learn about the exact moment the core fails, how matter falls inward, how the bounce generates the explosion. These are processes hidden inside the star, invisible to traditional telescopes. Gravitational waves carry information directly from the core. They're not blocked by overlying material. This makes them uniquely valuable for studying supernova interiors. Neutrinos serve a similar purpose. They interact so weakly that they escape the collapsing core almost immediately. The neutrino burst from Betelgeuse will arrive before the light, just like with 1987A. But this time, our neutrino detectors are far more sophisticated. IceCube in Antarctica can detect thousands of neutrinos if predictions hold. Super Kamiokande in Japan will see them too. Multiple detectors worldwide will triangulate the signal, pinning down the exact timing and direction. That coordination will happen automatically once the first detector alerts the network. Within seconds, astronomers globally will know Betelgeuse has exploded. They'll point every available telescope at it. The race will be on to capture the earliest moments. Amateur astronomers will contribute significantly. Professional telescopes can't cover the entire sky simultaneously. But thousands of amateur observers can. The first visible light detection might come from someone's backyard telescope. That's how supernovae are often discovered. Automated surveys catch many now, but amateurs still find them regularly. With Betelgeuse, the amateur community will be watching closely. Many have already planned their observation strategies. They know what equipment to use, what filters to apply, how to record data properly. When the moment comes, they'll be ready. This democratization of astronomy is relatively recent. Decades ago, meaningful contributions required access to major observatories. Now, affordable equipment can capture scientifically valuable data. Amateurs discovered comets, tracked asteroids, monitored variable stars. They've become essential parts of the astronomical community. Betelgeuse's supernova will showcase this collaboration beautifully. Professional astronomers will coordinate with amateur networks. Data will flow in from every continent. The global effort will be unprecedented in scale. And it needs to be. The first hours and days are crucial. That's when the shock wave breaks through the star's surface. That's when we see the initial flash, the rapid brightening, the spectrum changing minute by minute. These early moments constrain models of the explosion mechanism. Missing them means losing irreplaceable information. Automated systems will help. Robotic telescopes can respond within seconds of an alert. They'll begin collecting data before humans even know the supernova started. But human judgment matters too. Deciding which observations to prioritize, which instruments to use, how to adapt to unexpected developments. These decisions require expertise and intuition. The combination of automated systems and human oversight will maximize the scientific return. We're not just waiting passively. Preparations continue constantly. Observation plans are refined. Software is updated. Detector calibrations are checked. Communication networks are tested. When Betelgeuse explodes, everything needs to work perfectly. There's no second chance. Some might wonder why we invest so much effort into one star. The answer is that Betelgeuse represents an entire class of objects. What we learn applies to red supergiants everywhere. These stars are crucial for galactic chemical evolution. They produce and distribute heavy elements. Understanding their life cycles and death throes helps us understand galaxies themselves. Every galaxy contains stars like Betelgeuse. Most are too distant to study individually. But Betelgeuse is close enough for detailed observation. It's a proxy for countless others. The investment in studying it pays dividends across multiple fields. Beyond the science, there's something profound about witnessing cosmic events in human timescales. Most astronomical processes unfold over millions or billions of years. We see only snapshots. Stellar evolution happens too slowly to watch. But supernovae are different. They're fast. A human lifetime might encompass the entire visible phase. That connection between cosmic and human time makes supernovae special. We can experience them, not just study them abstractly. When Betelgeuse explodes, people worldwide will look up and see something genuinely new in the sky. That shared experience will be remarkable. Different cultures will interpret it differently. Some will see it as an omen, others as a spectacle. Scientists will see it as data. All perspectives are valid. The night sky belongs to everyone. Throughout history, Bright astronomical events have left marks on human culture. Supernovae recorded by ancient astronomers influenced art and mythology. The 1054 supernova that created the Crab Nebula was documented across multiple civilizations. Betelgeuse will be brighter and closer. Its cultural impact could be substantial. Modern astronomers might create detailed records, but they'll also capture something previous generations couldn't: real-time public engagement. Social media will light up instantly. Images will spread globally within minutes. The scientific community will share observations openly, faster than ever before. This transparency changes how discoveries unfold. Previous supernovae occurred before the Internet age. News traveled through traditional channels, slowly. Professional papers took months or years to publish. By contrast, Betelgeuse's explosion will be documented second by second online. Live streams will show telescopes tracking it. Data will be posted immediately. The entire process becomes visible. Some worry this openness might spread misinformation. Fair concern. Spectacular events attract wild speculation. We'll see claims about danger, about cosmic rays, about effects on Earth. Most will be nonsense. The challenge is separating signal from noise. Education becomes critical. Astronomical organizations are dechuan by kak chien dike thon tin som som. Kai siu tan tin zara, thon tin chin zak kan ko san nai lap tuc. En hung jai tik ro ran v en hung gi dang zara, no ko nia la gi, en hung wan noi him now kong tun tai. Su min bok fu dao lam jiam su hom lon vanam lon. Because there will be questions. Lots of them. Can the supernova harm us? No, the distance is far too great. Will it affect our weather? Not measurably. Could radiation reach Earth? Negligible amounts, harmless. These answers need to be ready, accessible, repeated often. The physics is straightforward but counterintuitive. 600 light-years sounds close astronomically. In human terms, it's incomprehensibly distant. Light from the explosion travels for 6 centuries before reaching us. Any dangerous radiation disperses across that vast gulf. By the time it arrives, it's weaker than cosmic rays we experience constantly. Neutrinos will arrive first, actually. They pass through matter easily, so they escape the collapsing core before light does. Detectors worldwide will register a sudden burst of neutrinos. This signal arrives hours before the visible brightening. It's the earliest warning possible. Neutrino detectors are already monitoring constantly. They're designed to catch exactly this scenario. When Betelgeuse collapses, detectors will see the neutrino pulse and send alerts automatically. Astronomers will have precious hours to prepare before the light reaches us. Those hours matter immensely. Telescopes can be pointed, exposure started, spectrographs readied. The very first light from the shock breakout is scientifically valuable. It happens fast, just minutes or hours. Being prepared means capturing data that would otherwise be lost forever. This coordination represents decades of planning. Alert systems connecting neutrino detectors to telescopes. Automated response protocols. International agreements on data sharing. All built specifically for rare transient events like this. Betelgeuse will test whether these systems work as designed. Beyond the immediate explosion, there's the aftermath. The supernova remnant will evolve over years and centuries. Initially, it expands rapidly, plowing into surrounding material. This creates shock waves, heating gas to millions of degrees. The remnant glows in X-rays and radio waves. Betelgeuse has already shed significant mass through stellar winds. That material surrounds the star in shells and clumps. When the supernova ejecta slams into this material, complex interactions occur. Shocks reflect and refract. Instabilities develop. The remnant won't be smooth or symmetrical. Studying these interactions reveals how supernovae inject energy into their surroundings. This feedback affects star formation in galaxies. Supernova shocks compress nearby gas clouds, sometimes triggering new stars to form. Other times, the energy disperses clouds, preventing star formation. Both processes shape galactic evolution. Betelgeuse's remnant will be uniquely observable. Most supernova remnants are ancient and distant. We see them thousands of years after the explosion. Betelgeuse offers the opposite, a remnant we can watch from birth. Imaging it yearly will show expansion, structural changes, emission variations. This time-lapse view is unprecedented. Infrared observations will be particularly revealing. Dust forms in the cooling ejecta within months or years of the explosion. This dust glows in infrared, creating a spectacular expanding shell. The dust composition tells us what elements were synthesized in the star and during the explosion itself. Speaking of elements, the periodic table owes much to stars like Betelgeuse. Hydrogen and helium came from the Big Bang. Almost everything else was forged in stars. Carbon, nitrogen, oxygen, iron, gold, uranium. All created through nuclear fusion or supernova explosions. Red supergiants produce elements through multiple processes. Fusion in the core generates elements up to iron. During the supernova, explosive nucleosynthesis creates heavier elements. The shock wave compresses material, driving reactions that wouldn't occur otherwise. Elements beyond iron, those requiring energy input rather than releasing it, form exclusively in these conditions. When Betelgeuse explodes, roughly 10 solar masses of processed material will be ejected. That's an enormous chemical payload. The ejecta will enrich the interstellar medium, mixing into gas clouds. Future generations of stars will incorporate these elements. Planets forming around those stars will contain atoms forged in Betelgeuse. This is how galaxies become chemically enriched over cosmic time. Early generations of stars contained only hydrogen and helium. They produced heavier elements and distributed them via supernovae. Subsequent stellar generations had more metals, enabling different types of stars and planetary systems. Our solar system contains elements from countless previous supernovae. Betelgeuse will continue this cycle. Somewhere, millions of years hence, a planet might form containing atoms from this star. Perhaps that planet will host life. Perhaps beings there will study astronomy, unaware that their very bodies contain material from a star humans once watched. The interconnectedness is profound. We're not separate from cosmic processes. We're participants. The calcium in our bones, the iron in our blood, all created in stellar furnaces and scattered by supernovae. When we observe Betelgeuse, we're studying our own origins. This perspective shifts how we think about astronomy. It's not just distant objects unrelated to us. It's our history, our context, our extended environment. The universe isn't something we live in passively. It's an active, evolving system, and we're part of it. Betelgeuse's supernova will make this tangible. Watching a star die, knowing it's producing elements essential for life, creates a visceral connection. This isn't abstract physics. It's the mechanism that made our existence possible. Educational opportunities abound. Kai siu tan tin zara, wa quan tam den thien van hoc si tang vot. Kak truon hoc si dua no veo chuan trin jam day. Kak kung thien van si tau ra kak chuan trin dac beat. Kak by John son so missy lap day kak thin fong. Koen kok nai ko the trian kam hung cho mot the he kak na kwa hok. History shows that astronomical events influence career choices. Many astronomers trace their interest to a specific observation or discovery that captivated them young. Betelgeuse could be that catalyst for thousands of people. The timing is unpredictable, but the impact will be lasting. Some of those inspired individuals might make future discoveries. They might solve problems we haven't identified yet. Science advances through accumulated effort across generations. Betelgeuse's supernova will feed into that ongoing process. There's also artistic inspiration. Throughout history, cosmic events have influenced art, literature, music. The night sky has always been a muse. A bright new star will spark creativity across cultures and disciplines. We'll see paintings, poems, compositions, all responding to this celestial event. Different artistic traditions will interpret it uniquely. Western perspectives might emphasize scientific understanding. Other cultures might focus on spiritual or philosophical dimensions. Indigenous traditions might connect it to existing cosmologies. Each response enriches our collective understanding. Because science doesn't have a monopoly on meaning. Supernovae can be approached from multiple angles. The astrophysics is one layer. The cultural significance is another. The personal, emotional response is yet another. All are legitimate. When Betelgeuse explodes, some people will cry. The night sky they've known their entire lives will change suddenly. A familiar constellation will look different. There's genuine loss in that, even if the star is unimaginably distant. Orion won't be the same. Others will feel excitement, wonder, curiosity. A rare event happening in their lifetime. Something their descendants will ask about. The chance to witness cosmic change directly. Both reactions are valid. The universe doesn't care how we feel about it. But our feelings matter to us. They're part of how we process and integrate experiences. Betelgeuse's supernova will be an experience, not just an observation. Preparation continues. The astronomical community remains vigilant. Betelgeuse could explode tonight. Or it might wait another 100,000 years. Statistically, sooner seems more likely than later, but statistics don't determine individual events. What we do know is that when it happens, we'll be ready. The infrastructure exists. The expertise is available. The coordination is practiced. This will be the most thoroughly documented supernova in history. And then comes the question everyone asks eventually: what happens after? After the initial explosion, after the brightness fades, after the remnant disperses. What's left? At the center, probably a neutron star. Chi Loi Sup Du, Kak Proton Va Electron by Engian Nat Voi Now, Tau Ton Kak Neutron. Ket Kwa Ymot Vet the Ron Koang 20 kilometers, Chua Koi Luong Lan Han Mat Troi, Duok Due Tri Boi Ap Sut Sui Bien Neutron. Dula Mot Trong and Hung Vet the Dai Dac Not Ko the Koma Kong Tiro Ton Mot Lo Den. Neutron stars are bizarre. Mot Thiat Sa Phi Vat Lu Sa Neutron Se Non Han Tai Tan Tren Tre Dat. Tron Luke Bi Mat Man Den Muc Kak Gon Nui Chi Ko the Chow Vi Millimet Truok Kai Sup Du. Kak Tu Truong Man Not Trong Vu Tru. Mot So Sa Neutron Quay Hong Tram Lon Moi Jie. Betelgeuse's neutron star will initially be hot, glowing in X-rays. Over millennia, it will cool and fade. Eventually, it becomes a cold, dark remnant. Still there, still massive, but invisible except through gravitational effects. Unless it becomes a pulsar. Some neutron stars emit beams of radiation from their magnetic poles. As they rotate, these beams sweep through space like lighthouse beams. If a beam is directed toward Earth, we will detect regular pulsations. Hence the name. Whether Betelgeuse's remnant will be a pulsar depends on details we can't predict: the core's rotation rate, the magnetic field strength, the viewing angle. We'll find out when it happens. The supernova remnant itself will expand for tens of thousands of years. Eventually, it merges with the interstellar medium, becoming indistinguishable from the general background. The atoms it scattered will drift through space, perhaps eventually condensing into new stars. Human impact category, minimal. The carbon in those future stars might eventually form planets. On those planets, life might emerge. Intelligent beings might look up at their sky and wonder about the universe. Inside them, atoms that once burned in Betelgeuse. The cosmic recycling program operates on timescales that make human history look like a blink. But here's something most people miss about supernovae. They're not endings. They're transformations. The star doesn't cease to exist, it changes form. Energy, matter, information, all continue. Just differently arranged. Betelgeuse right now contains the future. Elements waiting to be comprehensive. Energy waiting to be released. Stories waiting to be told. When it explodes, none of that disappears. It just moves elsewhere. This connects to something deeper about existence itself. Nothing truly ends. It transforms. The atoms in your body were once inside stars. After you die, they'll become something else. Trees, soil, water, air. Eventually, perhaps, other living things. The boundaries we draw between self and universe are convenient fictions. At the atomic level, we're continuous with everything. Betelgeuse reminds us of this. A star that will die so that new things can live. Not metaphorically. Literally. The supernova creates the raw materials for future complexity. Without stellar death, only hydrogen and helium would exist. No carbon, no oxygen, no iron. No planets, no life, no consciousness. We exist because stars die. That's not poetic language. That's physics. Every element heavier than helium was forged inside stars or during their explosive deaths. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all came from supernovae. We're not just in the universe. We're made of it. Literally composed of stellar corpses. Betelgeuse will add to that treasure. When it exploded, it created elements that don't currently exist anywhere nearby. Those atoms will drift through space for millions of years. Some will be incorporated into new structures. And somewhere, unbelievably in the future, something will exist because Betelgeuse is dead. The scale of this is difficult to internalize. We think in days, years, decades. Maybe centuries if we're historically minded. But stellar evolution operates on timescales where our entire species is a rounding error. Betelgeuse has been a star for roughly 8 million years. It might exist as a neutron star for trillions of years. Our entire civilization could rise, peak, and vanish in the gap between two of its heartbeats. Yet here we are, contemplating it. Tiny creatures on a small planet, understanding something greatly larger and older than ourselves. That's remarkable. We're the universe trying to understand itself. Atoms arranged in such a way that they can contemplate other atoms. Consciousness emerged from matter, then turning around to study the matter it came from. Betelgeuse doesn't know we exist. It's not aware of anything. It's just physics, chemistry, nuclear reactions following inevitable rules. But we're aware of it. We've studied it, predicted its fate, prepared to observe its death. In a sense, we're giving meaning to something that has none inherently. The supernova will happen whether we watch or not. But by watching, we transform it from a physical event into a human experience. We make it mean something. That's what consciousness does. It takes raw existence and converts it into meaning, understanding, story. Some people find this terrifying. The idea that meaning isn't inherent, that we create it ourselves. If the universe doesn't care, if there's no cosmic purpose, what's the point? But consider the alternative. If meaning were predetermined, fixed, universal, we'd be passive recipients. Instead, we're active creators. Every observation, every thought, every response adds to the universe's complexity. Betelgeuse will explode. That's determined by physics. But what it means, how we respond, what we learn, those are up to us. The universe provides raw material. We provide interpretation. And interpretation matters. The way we frame cosmic events shapes how we see ourselves. If we view supernovae as death and destruction, we emphasize loss, endings, fear. If we view them as transformation and creation, we emphasize change, renewal, possibility. Both perspectives describe the same physics, but they lead to different psychological spaces. The scientific perspective offers something valuable here. It doesn't say supernovae are good or bad. It says they're necessary. Without them, we wouldn't exist. They're not tragic or triumphant. They're functional. Part of how the universe operates. There's something freeing in that. Betelgeuse's explosion isn't personal. It's not happening to us or for us. It's just happening. We get to witness it because we exist in the right time and place. That's privilege, not punishment. The countdown continues. Each day, Betelgeuse converts helium to carbon, carbon to oxygen, and oxygen to silicon. Each day, the core shrinks a little. Each day, the outer layers shed more mass. Each day, the inner clock ticks closer to zero. We can't stop it. We can't speed it up. We can only observe and understand. In a universe that often feels chaotic and arbitrary, there's something satisfying about predictable processes. We know what will happen. We just don't know when. That uncertainty is important, though. If we knew the exact date, the supernova would become just another scheduled event. Mark your calendar, set a reminder, watch it happen. But the not knowing keeps us alert. Every clear night could be the night. Every observation could be the last one before everything changes. Amateur astronomers check Betelgeuse regularly. Has it dimmed? Brightened? Changed color? Mostly, it looks the same. But that could change tonight. Or tomorrow. Or next year. The very act of vigilance becomes meaningful. We are observing the universe, maintaining a connection to something far greater than our everyday concerns. When it finally happens, the response will be global. Instant communication means everyone will know within minutes. Social media will explode, though not as dramatically as Betelgeuse. News organizations will scramble to explain what's happening. Scientists will rush to their telescopes. And billions of people will look up, trying to find it in the sky. For a few weeks, astronomy will dominate conversations. People who never think about stars will suddenly care. Children will learn about supernovae in school. Artists will create inspired works. Writers will craft stories. The event will ripple through culture in unpredictable ways. Then, gradually, it will fade from attention. Supernovae will still be visible, but familiarity breeds indifference. Other news will dominate. Life will return to normal. For a year, most people won't think about it often. In 10 years, it will be a historical footnote. For 100 years, just another entry in the astronomical catalog. But the impact won't disappear. Everyone who witnesses it will carry that memory. The night the sky changed. The moment we watched a star die. That becomes part of personal history, woven into identity. And the science continues. Long after public attention fades, researchers will still be analyzing data, refining models, testing theories. The supernova becomes a permanent fixture in astronomical literature. Papers will reference it for centuries. It becomes the standard against which other supernovae are measured. Betelgeuse's death will advance our understanding of stellar evolution. We'll learn things impossible to discover any other way. The data will be scrutinized, debated, reinterpreted. New questions will emerge. Some will be answered. Others will persist for decades. That's how knowledge grows. Not through sudden revelations, but through accumulated observations, tested against predictions, refined through debate. One supernova won't solve everything, but it'll move us forward. That's enough. The universe doesn't reveal itself all at once. It requires patience, persistence, careful attention. Betelgeuse is teaching us even before it explodes. About stellar structure, mass loss, nucleosynthesis. The explosion will be the final exam, testing whether we understood the lesson. We're as ready as we'll ever be. Devices are built. Teams are trained. Protocols are established. When Betelgeuse explodes, humanity will react with coordinated precision. Thousands of people work towards a shared understanding. That coordination itself is remarkable. A global species acting in harmony, focused on pure knowledge. No profit motive drives this. No territorial advantage. Just curiosity. The desire to understand. In a world often fractured by competing interests, astronomy offers rare unity. Everyone benefits from the knowledge. No one loses when we learn. Betelgeuse doesn't care about any of this. It doesn't perform for us. It's just a star, subject to the laws of physics. But we care. We've invested time, resources, and attention. We've built our understanding around stars like this. When it explodes, we'll watch, not because we have to, but because we want to. That wanting matters. It's what makes us human. The drive to understand, even when understanding serves no immediate practical purpose. We study supernovae because they're there, because we can, because the knowledge itself is valuable. And when that light finally arrives, when Betelgeuse's death announcement reaches Earth, we'll be here. Watching. Recording. Understanding. Adding one more piece to the infinite puzzle of existence. The star will die. We'll learn. The universe will continue. And somewhere in that continuation, meaning emerges. Not given. Created. By us. Right now. As we wait for the sky to change. So we stand here, citizens of a moment, watching a star that might already be dead. The light that reaches our eyes tonight left Betelgeuse before Columbus set sail. We are seeing history, not current events. That time lag creates a strange relationship with reality. Somewhere in the vastness between here and there, photons are traveling. Maybe they're the last normal ones, carrying an image of Betelgeuse as it was. Maybe others follow, carrying the flash, the explosion, the transformation. We won't know until they arrive. This is astronomy's fundamental constraint. We're always looking backward. The present is inaccessible. We study the past and call it observation. Betelgeuse could have exploded last week. The information simply hasn't reached us yet. No way to check. No faster channel exists. Light speed is the universe's speed limit, and we're bound by it. That limitation used to frustrate early astronomers. Now we've accepted it. We built our entire field around it. We turned the constraint into methodology. We can't see the present, so we study how the past becomes the present. We measure time through light's journey. When Betelgeuse's supernova light arrives, it'll be carrying a message 6 centuries old. The star made a decision in the 1400s. We're waiting for the announcement. The explosion has happened, or it hasn't. Both possibilities exist simultaneously in our experience until the light resolves the uncertainty. Quantum mechanics talks about superposition. States exist simultaneously until measurement collapses them into a single reality. Betelgeuse is our macroscopic version. Simultaneously exploded and unexploded, depending on your frame of reference. From the star's perspective, it was either one or the other. From our perspective, it's both. That's not mysticism. That's relativity. Information can't travel faster than light, so distant events haven't happened to us yet, regardless of what happened there. Our present doesn't include Betelgeuse's present. They are disconnected, separated by distance and the speed limitations of causality. This creates odd implications. If Betelgeuse exploded yesterday, it's already a supernova. Just not for us. For someone positioned differently, maybe closer, it already happened. For someone farther away, it won't happen for centuries. The event's timing depends on where you're standing. There's no universal now. People struggle with this. We want objective reality, fixed facts, definite answers. The universe doesn't provide them. It offers perspectives, reference frames, relative truths. What's simultaneous for you isn't for someone moving differently. What's now for you is past or future for someone positioned differently. Betelgeuse forces us to confront this. We're waiting for information about something that either has or hasn't occurred, and we genuinely don't know which. Both possibilities are real until light arrives and shatters our uncertainty. The philosophical implications extend beyond astronomy. How we understand time, causality, existence itself, all get challenged by cosmic distances. We think we inhabit a shared present. We don't. We inhabit overlapping light cones, regions of space-time connected by possible causal relationships. Betelgeuse sits outside our current light cone. Its present is inaccessible to us. Whatever is happening there right now, we cannot know for at least 642 years. By the time we find out, it will be ancient history. The present retreats forever from our observational capabilities. This isn't a limitation. It's structure. The universe is constructed this way. Information travels at the speed of light. There are no exceptions. That creates a fundamental line between knowledge and ignorance. We can know the past. The present is uncertain. The future is inaccessible. Betelgeuse's supernova will teach us this viscerally. We'll watch something that already happened centuries ago. The explosion will be news to us, but it will be old news to the universe. We are always behind, always chasing, never reaching the present moment of distant objects. Some find this depressing. We'll never truly know what's happening now in the broader universe. By the time we see it, it's history. But consider an alternative. If we could see everything at once, if distance didn't create a delay, causality would be broken. Effects could precede causes. Time would lose its meaning. The light speed limit protects causality. It ensures that effects follow causes. It creates an arrow of time, a direction, a structure. Without it, the universe would be chaotic. With it, we have order, predictability, and functioning physics. Betelgeuse demonstrates this beautifully. The star follows rules. It burns fuel, contracts, heats up, and eventually collapses. Each step inevitably leads to the next. The sequence is deterministic. We can predict it without seeing it. This could be because causality is maintained, because the speed of light limits information, because the universe is structured. When the supernova finally becomes visible, it'll confirm what we already predicted. Or it will surprise us, forcing us to revise our model. Either way, we learn. The universe teaches through examples. Betelgeuse is one example among billions. But it is our example, close enough to study, bright enough to see, time to happen when we have the tools to understand it. That timing is arbitrary. We didn't arrange it. Betelgeuse doesn't know we exist. It died millions of years ago, according to stellar physics. We happen to develop intelligence in its final chapter, purely by chance. But by chance we can exploit it. Humanity's window of technological capability is narrow. We've had serious astronomy for maybe 400 years. We'll probably have it for thousands more, barring catastrophe. Betelgeuse's supernova might occur during this window. Or it might not. The odds favor it happening eventually, but eventually is vague. If it happens next week, we're positioned to study it thoroughly. If it waits 10,000 years, future civilizations will have that opportunity. Either way, someone benefits. Knowledge enters human understanding whenever it comes. Timing influences who learns, not whether the learning happens. This long-term view helps. We're not racing against time. We're participating in an ongoing project that spans generations. Astronomers today prepare the equipment, develop theories, and train students. Those students will train others. When Betelgeuse explodes, whoever survives will carry on the accumulated knowledge. Science is cumulative. Each generation builds on the work of the previous one. Today's observations of Betelgeuse provide information for tomorrow's understanding. The supernova, when it occurs, will be explained through the frameworks we are building now. Our preparation is not wasted if the explosion is delayed. It's an investment in future knowledge. And the preparation itself teaches us. Building instruments, refining models, coordinating observations, all develop skills and understanding applicable beyond Betelgeuse. We don't just wait. We are improving. Every observation, even of an unexploded star, adds to the data. Each refinement of the model increases accuracy. Work continues regardless of when the key event occurs. This patience is characteristic of astronomy. We study processes that take longer than a lifetime. We ask questions that we ourselves may not be able to answer. We contribute to understanding that benefits people we will never meet. It requires a special mindset. Long-term thinking. Delaying gratification. Belief in collective progress. Betelgeuse embodies this perfectly. We're watching. We're waiting. We're preparing. We don't know when it'll happen. We know it will happen. That's enough. The act of watching itself is meaningful. The preparation is valuable. The knowledge we are building is important, whether there is a supernova or not. Because ultimately, this isn't about one star. It's about understanding how stars work. Betelgeuse is a case study, an example, a test subject. What we learn applies to countless other stars. The principles are universal. Physics doesn't change from one star to another. Only the details change. When Betelgeuse explodes, it'll validate or challenge our understanding of those universal principles. Both outcomes advance science. Validation means our models work. Surprise means they need improvement. Both are progress. So we watch. We wait. We prepare. Betelgeuse hangs on Orion's shoulder, burning its last of fuel, approaching its inevitable demise. We can't stop it. We can't predict exactly when. We can only observe and understand. That's enough. That's all. That's the meaning of doing science. Watch the universe do what it does and learn from watching it. The star will die. We will see it. We will understand it better than any supernova before. And then we move on to the next question, the next mystery, the next opportunity to push understanding forward. Because that's what we do. That's what makes us who we are. We look up. We ask. We work to understand. And the universe, indifferent yet generous, provides countless opportunities to learn. Betelgeuse is one opportunity. Just one. But it is ours, and we are ready, and when the light arrives, carrying news of an explosion that happened centuries ago, we will be here, watching, recording, understanding. Another piece added to the endless puzzle. The star will change. We will learn. And somewhere in that learning, meaning arises. Not given. Created. By us. Through our attention, our curiosity, and our patient work to comprehend what we see when we look up at the night sky and see it change. In October 2015, a star called KIC 846-2852 started behaving in a way that made no sense. Its light dimmed by 22%, then flickered, then stabilized, then dropped again in patterns astronomers had never seen before. Within weeks, one scientist suggested something extraordinary. An alien megastructure might be blocking the light. The media exploded. Scientists scrambled for explanations. And now, nearly a decade later, the James Webb Space Telescope has turned its infrared eyes toward similar anomalies scattered across deep space. What it's finding is forcing us to reconsider what we thought we knew about the universe. Before we dive into Webb's discoveries, you need to understand why KIC 846-2852, nicknamed Tabby Star, became the most controversial object in modern astronomy. Stars dim for predictable reasons. A planet crosses in front, blocking maybe 1% of the light. Dust clouds pass by, creating smooth, gradual fading. Comets break apart, leaving debris trails. But Tabby's star dropped by amounts that would require a planet the size of Jupiter, and the dips happened irregularly over days, weeks, sometimes years. The Kepler Space Telescope watched it for 4 years straight, recording behavior that matched no known natural phenomenon. Astronomer Tabitha Boyajian, after whom the star was named, exhausted every conventional explanation. Instrument errors, ruled out by multiple telescopes. Planetary collisions. The debris would glow with heat. A swarm of comets? Possible, but statistically improbable given the required density and timing. Then came the paper that changed everything. Penn State astronomer Jason Wright published a study titled, "The Search for Extraterrestrial Civilizations with Large Energy Supplies." His hypothesis was simple but staggering. If an advanced civilization wanted to harness their star's total energy output, they'd build what physicist Freeman Dyson described in 1960 as a megastructure, a massive array of solar collectors orbiting the star. From Earth, we'd see irregular dimming as these structures passed between us and the star. The scientific community reacted with predictable skepticism. Extraordinary claims require extraordinary evidence, and suggesting alien engineering based on one weird star felt premature. Yet no one could explain the data. Natural explanations kept failing. The dimming patterns were too irregular for planets, too deep for dust, too persistent for comets. Tabby's star sat there in the data, 1,470 light-years away, doing something stars aren't supposed to do. Fast forward to 2022. The James Webb Space Telescope launches with capabilities that make previous instruments look like toys. Webb doesn't just see visible light. Its infrared sensors penetrate dust clouds, detect heat signatures, and analyze chemical compositions across billions of light years. Within its first year of operation, Webb identified 17 stars exhibiting anomalous dimming patterns similar to Tabby's star. 17. Not in our galaxy's backyard, but scattered across different regions, different stellar types, different environments. The sample size just got large enough to matter. Here's where it gets interesting. Webb's infrared data revealed something Kepler couldn't see. Around several of these anomalous stars, there are excess infrared signatures in wavelengths consistent with manufactured materials radiating absorbed heat. Natural dust clouds produce diffuse, scattered infrared patterns. These signatures are concentrated, geometric, and in some cases appear to orbit the star in formations. 3 of the 17 stars show infrared patterns that repeat on precise timescales, suggesting structured objects in stable orbits. Let me be clear about what we're actually looking at. Webb hasn't photographed alien cities or giant space stations. We're talking about spectroscopic data, infrared measurements, and statistical patterns. The telescope detects light, breaks it into wavelengths, and sophisticated algorithms analyze those wavelengths for anomalies. What makes these 17 stars stand out is the combination of unusual visible light dimming plus infrared excess that doesn't match any known stellar or planetary process. It's the pattern that's compelling, not any single data point. The star designated JWST 2024 TM3 presents the clearest case. Located 2,850 light-years away in the constellation Cygnus, this sun-like star dims by 18% every 712 days, then partially recovers over 43 days, then dims again by 9% in an offset pattern. Webb's infrared readings show heat signatures at 340 Kelvin, far too cool for stellar material but too warm for natural dust at that distance from the star. The spectrum shows no signs of common elements like silicon or carbon monoxide you'd expect from asteroid debris or comet tails. Instead, There are unusual absorption lines suggesting complex molecular structures that some researchers describe as potentially synthetic polymers. Before you assume aliens, consider the alternative explanations still on the table. A young planetary system might be experiencing massive volcanic activity across multiple worlds simultaneously. Unusual magnetic field interactions could trap plasma in configurations we've never observed before. Some form of exotic stellar phenomenon, perhaps related to the star's internal structure, might produce these effects through mechanisms we haven't discovered yet. Science doesn't jump to aliens just because something's weird. It exhausts every natural possibility first. But here's the problem. We've been exhausting natural possibilities for 9 years since Tabby's star was discovered, and the explanations keep getting more convoluted. To explain JWST 2024 TM3 naturally, you need a scenario where multiple planet-sized objects, made of materials that don't match known cosmic chemistry, orbit in precise formations that create geometric dimming patterns while radiating heat at specific temperatures. You're essentially proposing a natural phenomenon so specific and unusual that it might be more extraordinary than artificial structures. This is the razor's edge where astronomy finds itself now. The data is real. Webb's instruments are functioning correctly, cross-checked against hundreds of other observations. The patterns exist. The question isn't whether something strange is happening around these stars. The question is whether the strange thing is natural or artificial, and increasingly, the natural explanations require assumptions just as wild as the artificial ones. The scientific method demands we follow the data wherever it leads, even if it leads somewhere uncomfortable. In 1967, astronomer Jocelyn Bell detected radio pulses so regular she and her colleagues half-seriously called them LGM-1, for little green men. Those pulses turned out to be pulsars, rotating neutron stars, a natural phenomenon so bizarre it seemed artificial at first. History might repeat itself. These anomalous stars might reveal some new type of stellar behavior, some undiscovered phase of planetary formation, some exotic interaction between magnetic fields and stellar winds. Or they might not. What makes the current situation different from the pulsar discovery is that we now have multiple detection methods converging on the same objects. Visible light dimming, infrared excess, spectroscopic anomalies, precise timing patterns. When one instrument shows something weird, it's probably an instrument problem. When 3 independent instruments all show weirdness in the same place, you're looking at something real. Webb's mission timeline includes deep dive observations of 5 of these anomalous stars scheduled over the next 18 months. The telescope will stare at each target for extended periods, building up signal strength, searching for any additional clues in the data. If these are megastructures, we should see additional signatures. Energy being redirected. Waste heat in unexpected spectrums. Maybe even changes over time as construction or maintenance occurs. If they're natural phenomena, extended observation should reveal patterns consistent with known physics. The implications branch in radically different directions depending on which answer emerges. If natural, we're about to discover new physics, new stellar behaviors, new planetary formation processes that textbooks will need to include. If artificial, we're confronting evidence that technological civilizations exist, build on scales we can barely imagine, and have been operating in our cosmic neighborhood for potentially millions of years. Neither answer is small. There's a third possibility that no one likes discussing but deserves attention. Maybe we're seeing something that's neither purely natural nor purely artificial in the way we understand those categories. Maybe there are cosmic processes that organize matter and energy in ways that blur the line between geology and engineering. Self-organizing systems that arise naturally but produce structured, geometric outcomes. The universe has already shown us that it can create complexity without intent, chemistry that builds toward life, physical laws that permit consciousness. Perhaps it can also create structures that look engineered without requiring engineers. What happens next depends on data that doesn't exist yet. Webb needs more observation time. Ground-based telescopes need to coordinate follow-up studies. Radio telescopes should scan these stars for any electromagnetic signatures. Multiple research teams need to independently verify the findings, challenge the interpretations, and propose testable alternatives. That's how science works when something potentially revolutionary appears. Slow, methodical, skeptical, but ultimately following where the evidence leads. The detection of anomalous infrared signatures around stars with unusual dimming patterns represents a threshold moment. Either we're about to understand something new about how stars and planetary systems behave, or we're about to confirm that intelligence exists beyond Earth and expresses itself through engineering visible across interstellar distances. Both possibilities will reshape how we see our place in the cosmos. But before we can evaluate whether these might actually be megastructures, we need to understand what a Dyson sphere actually is, how it would theoretically function, and why any civilization would undertake something so monumentally ambitious in the first place. The concept originates with Freeman Dyson, a physicist who spent much of his career thinking about problems most people never consider. In 1960, he published a paper asking a deceptively simple question: if advanced civilizations exist and continue developing for thousands or millions of years, what would their energy consumption look like? Every technological civilization we can imagine needs energy. More technology means more energy demand. A society that masters fusion still needs fuel. A civilization that builds artificial habitats still needs power to maintain them. Even if you solve energy efficiency, growth eventually demands more total energy. You hit planetary limits. Dyson realized that a sufficiently advanced civilization would eventually exhaust every energy source on their home planet. Solar panels covering every surface, geothermal taps at every volcanic site, fusion reactors in every city. At some point, you've harvested everything the planet can provide, and you still need more. The only remaining source is the star itself. Stars are extraordinary power sources. Our sun outputs about 400 trillion watts continuously. Earth intercepts roughly 1/1000th of that. The rest radiates into empty space, unused, wasted from any practical perspective. A civilization looking at that disparity would see an engineering challenge, not an impossible dream. Dyson proposed that such a civilization might construct a shell or swarm of collectors around their star, capturing not a fraction but most of the stellar output. The structure wouldn't be solid, that's a common misconception. A rigid shell would be gravitationally unstable, torn apart by tidal forces. Instead, you build millions or billions of independent platforms orbiting at different inclinations, each collecting solar energy and beaming it elsewhere. This is what astronomers mean by a Dyson sphere. Not a physical sphere in the architectural sense, but a coordinated system of energy collectors completely enclosing a star. From outside, you wouldn't see the star anymore. You'd see a warm object radiating in infrared, glowing from the waste heat of whatever processes are consuming all that captured energy. The thermodynamics are unavoidable. Energy gets used, converted, and eventually becomes heat. Even a perfectly efficient civilization can't escape entropy. Capture starlight, use it for computation or manufacturing or climate control, and eventually that energy becomes waste heat. That heat has to go somewhere. It radiates outward into space, but now it's not coming from a 5,500 Kelvin stellar surface. It's coming from whatever temperature the collection structures reach, probably somewhere between 300 and 800 Kelvin depending on design. That temperature range puts the emission peak directly in the infrared. This is the signature astronomers look for. A star that should be visible in optical wavelengths but appears only in infrared, or a star with far more infrared emission than its temperature and luminosity predict. The excess infrared becomes the smoking gun. Building something like this isn't fantasy engineering. It's just scaled up versions of things we already do. We launch satellites. We build solar panels. We construct orbital platforms. A Dyson sphere is the same principles applied across millions of individual structures over thousands of years. The resources exist in any mature solar system. Disassemble a few planets, maybe some gas giant moons, and you have more raw material than you'd ever need. Mercury alone contains enough metal to build collection platforms with a combined surface area thousands of times larger than Earth. Jupiter's moons could provide materials for millions of habitats. Asteroid belts offer convenient construction sites with low-gravity wells. The engineering is monumental, but nothing in the design violates known physics. Construction would take time. Centuries at minimum, probably millennia. You'd start small, building the first collectors using planetary resources. Those collectors provide energy to build more collectors. Each generation expands the swarm. Eventually you reach a threshold where the swarm generates enough energy to accelerate construction dramatically. The process becomes self-sustaining. What would motivate a civilization to attempt this? Energy security at a fundamental level. With a Dyson sphere, you're no longer vulnerable to resource depletion, climate catastrophe, or any planetary-scale disaster. You've moved your civilization's foundation from a fragile biosphere to the most stable, long-lived power source in the solar system. Stars burn for billions of years. Planets don't offer that guarantee. There's also the computational argument. If your civilization develops advanced artificial intelligence or massive simulation systems, your energy demands explode exponentially. Training complex AI models already consumes enormous power. Now imagine civilizations running simulations detailed enough to model entire worlds, or maintaining digital consciousnesses for billions of individuals. The energy requirements would be staggering, potentially demanding stellar-scale power sources. Some researchers propose even more ambitious versions. A Dyson sphere might be just the first step. A sufficiently advanced civilization might eventually enclose multiple stars, building sphere after sphere across an entire region of the galaxy. From outside, such a civilization would appear as a void in visible light but a bright source of infrared radiation, a warm shadow where stars should be. This leads to what's called the Fermi paradox angle. If intelligent life is common, and if civilizations naturally progress toward megastructures, we should see them. The galaxy is billions of years old. Plenty of time for someone to build Dyson spheres around thousands or millions of stars. The fact that we don't see obvious megastructures everywhere is either evidence that civilizations are rare, that they don't build Dyson spheres for some reason, or that we're not looking correctly. The detection strategy is straightforward in principle. Survey stars for infrared excess. Most stars have predictable infrared output based on their temperature and size. Stars with significantly more infrared than expected become candidates. Then you investigate further, looking for additional anomalies that natural explanations can't cover. Dust produces infrared excess, but dust has a spectral signature. It emits in specific patterns based on grain size and composition. A Dyson sphere would show a different pattern, more like a blackbody radiator at a specific temperature. Young stellar systems have lots of dust, but that dust clears over time. Old, stable stars shouldn't have massive dust clouds unless something unusual is happening. Planetary collisions can create temporary dust, but that dust spreads and dissipates relatively quickly on astronomical timescales. If you see persistent infrared excess around an old star, lasting for years or decades, dust becomes a less satisfying explanation. You need something continuously radiating at infrared wavelengths, something with substantial mass and surface area. This is where the current observations become particularly intriguing. The stars showing anomalous signatures aren't young. They're not surrounded by obvious debris disks. Suns show infrared excess that's remained stable across multiple observation periods. The excess isn't random, it's concentrated in specific wavelength bands that correspond to temperatures you'd expect from artificial structures trying to radiate waste heat. One star in particular, designated KIC 846-2852 but commonly called Tabby star, has driven more research than any other candidate. Its light curve shows irregular, non-periodic dimming events that no conventional model adequately explains. Comets were proposed, then largely ruled out. Dust clouds don't produce the observed patterns. Planetary collisions should create symmetrical, predictable effects. What remains are explanations that feel increasingly exotic. Adding to the mystery, Tabby's star also shows slight infrared excess. Not overwhelming, but present. And the excess doesn't match standard dust signatures. The combination of weird dimming plus anomalous infrared creates a profile that keeps appearing in hypothetical Dyson sphere detection scenarios. No one's claiming proof, but the observations fit the pattern you'd expect if someone was building something large around that star. Webb's observations will provide crucial data. The telescope can analyze infrared signatures with unprecedented precision, breaking down the spectrum into fine detail. Different materials radiate at different wavelengths. Dust has characteristic signatures. Ice has signatures. Rocky material has signatures. If what we're seeing is artificial, it should show a different pattern, something inconsistent with natural materials or processes. The timeline matters here. Webb's detailed observations of these candidate stars are scheduled across the next 2 years. Results won't come quickly. Each target needs extended observation time, multiple passes to build up signal strength and confirm consistency. Then comes analysis, peer review, and the inevitable debate about interpretation. Even if Webb finds something genuinely anomalous, confirming it as artificial rather than some new natural phenomenon will take additional evidence. What would constitute proof? There's no single observation that would definitively confirm artificial structures. Instead, you'd need multiple independent lines of evidence all pointing the same direction. Infrared excess with non-natural spectral signatures. Geometric patterns in the dimming events. Possible radio or optical signals coming from the same location. Changes over time consistent with construction or modification. The case would build gradually through accumulated evidence rather than a single dramatic revelation. Right now, we're in the uncomfortable space between intriguing data and confirmed discovery. The observations are real. The anomalies exist. But translating anomalies into conclusions requires patience and rigor that doesn't satisfy our desire for immediate answers. Science moves slowly when the stakes are this high, when the implications reach this far. Every alternative explanation needs testing. Every assumption needs challenging. That's frustrating, but it's also necessary. What makes this search different from past SETI efforts is that we're not listening for deliberate signals. We're looking for side effects, the inevitable consequences of large-scale engineering. A civilization might choose not to broadcast. They can't choose not to radiate waste heat. Physics makes certain activities visible whether anyone intends them to be or not. That shifts the detection problem from communication to thermodynamics, from intention to consequence. Which brings up something most people overlook when thinking about Dyson spheres. The engineering isn't the hardest part. The decision to build one is. Because once you start constructing megastructures around your star, you're making a statement that echoes across light years for millions of years. You're announcing your presence to anyone capable of looking. Some researchers argue advanced civilizations might deliberately avoid this. They'd recognize that visibility equals vulnerability. If you don't know what's out there, broadcasting your location through massive construction projects seems reckless. Better to stay small, stay hidden, develop technology that doesn't leave obvious signatures. This line of thinking leads to the dark forest hypothesis, where civilizations remain silent because the universe might be more dangerous than it appears. But that assumes rational caution dominates at every stage of development. Humans show constantly that short-term needs often override long-term risks. If a civilization faces energy constraints, resource limitations, or population pressures, they might build despite the exposure. Survival today beats hypothetical threats tomorrow. The calculation changes if you're desperate or if you simply don't believe the risks are real. There's another possibility that doesn't get enough attention. Maybe advanced civilizations don't care about being visible because they've reached a point where it doesn't matter. If you've achieved certain technological thresholds, if you've solved certain fundamental problems, being observed might carry no meaningful risk. You build what you need and let the consequences sort themselves out. That sounds arrogant until you consider what a million-year technological head start actually means. Webb's capabilities extend beyond just infrared detection. The telescope can analyze chemical signatures in exoplanet atmospheres, looking for biosignatures or technosignatures that might indicate industrial activity. Certain chemical combinations don't occur naturally. Chlorofluorocarbons, for instance. If you detect CFCs in an exoplanet's atmosphere, that's not biology. That's industry. Same with certain nitrogen compounds or specific pollutants that only emerge from technological processes. The search parameters keep expanding as we understand what's actually detectable. Early SETI focused on radio signals because that's what we could build receivers for. Now we're scanning across multiple wavelengths, looking for infrared excess, chemical anomalies, optical pulses, even gravitational wave signatures that might indicate massive engineering projects. The toolkit grows as technology advances, and each new instrument reveals possibilities we couldn't access before. What's striking about the current moment is the sheer volume of data we're collecting. Webb generates massive datasets with every observation. Ground-based telescopes contribute their own streams of information. We've got archives spanning decades that can be reanalyzed with modern techniques. The bottleneck isn't data collection anymore. It's analysis. There's more information available than researchers can properly examine, which means potentially significant findings might be sitting in databases right now, waiting for someone to look at them the right way. Machine learning algorithms are starting to help with this problem. You can train neural networks to recognize patterns humans might miss, to flag anomalies in massive datasets that would take years to examine manually. But algorithms bring their own issues. They find what they're trained to find. If we're looking for the wrong patterns, if our assumptions about what artificial structures should look like are incorrect, the algorithms will miss them too. Garbage in, garbage out. That's why human analysis still matters. A researcher looking at data with fresh eyes might notice something unexpected, something that doesn't fit existing search parameters. Some of the most important discoveries in astronomy came from people who weren't looking for what they found. Pulsars. Cosmic microwave background radiation. Exoplanets. The universe keeps surprising us specifically because we're not good at predicting what's actually out there. The Fermi paradox sits in the background of all these discussions. If advanced civilizations exist, if Dyson spheres are practical and desirable, where are they? We should see evidence everywhere. The galaxy is old enough that colonization should have happened multiple times over. Yet we observe silence. Empty skies. No obvious megastructures. No clear signals. This absence of evidence becomes evidence itself, suggesting either we're alone, we're early, or we're missing something fundamental about how advanced civilizations actually develop. Several solutions to the Fermi paradox relate directly to Dyson sphere searches. Maybe civilizations do build them, but they're using materials and configurations we don't recognize as artificial. Maybe they build them and then disappear, leaving ruins we interpret as natural phenomena. Maybe the construction timeline is so long that we're catching civilizations in early stages where the signatures aren't obvious yet. Or maybe, and this is the unsettling option, something prevents civilizations from reaching the megastructure building stage. Some filter, some barrier we haven't encountered yet. The Great Filter concept suggests there's at least one extremely difficult step in the evolution from simple life to galaxy-spanning civilization. That filter could be behind us, maybe the jump from single cells to multicellular life. Or it could be ahead of us. Nuclear weapons, climate change, artificial intelligence, something we haven't identified yet. If the filter is ahead and it's related to the capability level needed for megastructure construction, that would explain why we don't see Dyson spheres. Civilizations reach the threshold and then fail, repeatedly, across the galaxy. But here's what makes the current search compelling despite these sobering possibilities. We're finally at the point where absence of evidence becomes meaningful data. If Webb observes 1,000 candidate systems and finds nothing artificial, that tells us something important about civilization development, energy use patterns, or the practicality of megastructures. Negative results matter when the search is comprehensive enough. The technological progression that led to Webb represents something significant in itself. We went from barely detecting exoplanets to characterizing their atmospheres in roughly 3 decades. The pace of capability improvement suggests that within another few decades, we'll have instruments that make Webb look primitive. Earth-based interferometry arrays, space-based telescope networks, gravitational lensing techniques that turn entire galaxies into natural telescopes. Each advancement expands what's detectable and pushes the boundaries of what counts as evidence. This creates an interesting temporal window. If advanced civilizations exist and they're observable, we're entering the period where we can actually find them. Before Webb, before modern exoplanet detection, we simply lacked the tools. In another century, we'll have capabilities we can barely imagine now. But right now, in this specific moment, we're transitioning from speculation to actual empirical investigation. The question shifts from, could they exist, to, do they exist, because we can finally look properly. What happens if we find something? The protocols for announcing potential detection of extraterrestrial intelligence involve verification, peer review, and careful communication. You don't tweet out that you found a Dyson sphere the moment you see something weird in the data. You check your instruments. You get other teams to confirm the observations. You eliminate every possible natural explanation. Then, and only then, you start talking about artificial origins. But information control in the modern era is complicated. Data from major telescopes is often publicly available after short proprietary periods. Amateur astronomers have serious equipment now. Leaks happen. If Webb found something genuinely anomalous around a nearby star, keeping that quiet during the verification process would be difficult. The announcement might come through informal channels before official confirmation, which creates its own problems. The human response to confirmed detection of artificial structures would be unpredictable. Some people would celebrate. Others would panic. Religious implications would be profound for many. Economic impacts could be significant if people started making decisions based on the assumption we're not alone. The mere possibility that we might find something has already influenced how some people think about humanity's place in the universe. Actual confirmation would amplify that effect dramatically. There's also the question of what we do with the information. If we detected a Dyson sphere around a star 200 light-years away, we couldn't communicate with whatever built it on any reasonable timescale. A message would take 2 centuries to arrive. The response would take another 2 centuries to return. We'd be talking to civilizations separated by 400 years of development and change. Whatever we said would reach a society so different from the one that built the structure that meaningful dialogue seems impossible. That distance might be precisely why detection matters despite communication limits. Knowing we're not alone changes everything, even if we can't talk to them. It answers fundamental questions about life's frequency in the universe, about the sustainability of technological civilizations, about whether the Great Filter is behind or ahead of us. A single confirmed detection of artificial structures would reshape humanity's understanding of its context and future possibilities. Webb continues its survey. Data accumulates. Analysis proceeds. And somewhere in that growing dataset might be the signature we've been looking for, the infrared excess that doesn't quite match anything natural, the geometric pattern that suggests deliberate construction. Or maybe there's nothing. Maybe we're alone, or early, or looking in the wrong places with the wrong assumptions. Either answer matters. Either answer tells us something crucial about the universe and our place in it. What we do with that information depends on what we find. The search itself represents something unprecedented in human history. For the first time, we're equipped to actually answer whether we're alone or just haven't looked carefully enough yet. The practical challenges of actually searching for Dyson spheres go beyond just pointing telescopes at stars and waiting. You need to know what you're looking for, which means understanding how different construction approaches would appear in our data. A solid shell would create one signature. A swarm of independent collectors would create another. An incomplete structure still under construction would look different from either. The detection method depends entirely on what configuration you're hunting. Start with the simplest case. A complete rigid shell around a star would absorb essentially all visible light and re-emit it as infrared radiation. The star would disappear in optical wavelengths while blazing in the infrared. That's the classic signature everyone talks about. But here's where it gets complicated. The temperature of that infrared emission tells you about the radius of the shell. A smaller shell closer to the star would be hotter and emit at shorter infrared wavelengths. A larger shell farther out would be cooler and emit at longer wavelengths. The spectrum you observe constrains the geometry. Webb's infrared instruments can detect these temperature differences with precision that wasn't available before. Previous surveys had to work with broader wavelength ranges and lower resolution. They could spot weird infrared sources but couldn't characterize them well enough to distinguish between dust clouds, debris disks, and potential artificial structures. Webb changes that equation by providing detailed spectral information that reveals the physical properties of whatever's emitting the radiation. Natural objects emit infrared in predictable patterns based on their composition and temperature. Dust around stars follows blackbody curves modified by emission features from silicates and other minerals. Planets show reflected starlight mixed with their own thermal emission. Debris disks have characteristic structures based on orbital dynamics and collision physics. An artificial structure would need to mimic all these natural signatures perfectly to avoid detection, which becomes harder the more carefully you look. The challenge is that nature produces a staggering variety of infrared sources that might confuse the search. Young stellar objects surrounded by dusty disks. Old stars shedding material into space. Binary systems where mass transfer creates hot regions. Galaxies with extreme star formation rates. Each one needs to be examined and categorized before you can claim something doesn't fit the natural explanations. That process takes time and careful analysis. Consider a partial Dyson structure. Maybe a civilization built collectors around just the equatorial region of their star, or focused on capturing output from specific latitudes. The infrared signature would be asymmetric and variable depending on viewing angle. As the structure rotates, different portions would face toward or away from us, creating periodic variations in the signal. Those variations would follow patterns related to the structure's geometry and rotation period. Distinguishing that from natural stellar variability requires long-term monitoring and detailed modeling. Swarm configurations present different detection challenges. Instead of a continuous shell, imagine millions or billions of independent collectors orbiting the star. Each one absorbs light and re-emits infrared, but they're not connected into a single structure. The collective effect might look similar to a complete shell from a distance, but close examination would reveal differences. The infrared emission might show small-scale variations as individual collectors pass in front of each other or occult portions of the star. The spectrum might not be a perfect blackbody because different collectors operate at different temperatures. Transit methods offer another approach. If we're viewing a Dyson structure edge-on, we might see periodic dips in starlight as components pass between us and the star. Natural planets create transits with specific shapes and durations based on their size and orbital period. An artificial structure with irregular geometry would create transit signatures that don't match planetary models. Multiple structures at different orbital distances would create complex, overlapping patterns. Analyzing those patterns could reveal whether we're seeing something natural or artificial. The statistical approach matters as much as individual detections. If you survey thousands of stars and find one weird infrared source, it's probably natural. If you find dozens that all share similar anomalous properties, that becomes interesting. If those stars cluster in certain regions of the galaxy or around specific stellar types, that suggests a pattern. Building that statistical foundation requires surveying large samples and carefully characterizing each target. Distance plays a crucial role in what we can detect. A Dyson sphere around a star 10 light-years away would appear much brighter and easier to characterize than one at 1,000 light-years. But nearby stars are rare. There are only a few dozen within 10 light-years of Earth. Thousands within 100 light-years. Millions within 1,000 light-years. The probability of finding artificial structures increases with survey volume, but detection difficulty increases with distance. Finding the right balance between these factors shapes survey strategy. Webb's position at the L2 Lagrange point gives it advantages for this kind of search. The stable thermal environment means consistent instrument performance. The large collecting area provides sensitivity to faint infrared sources. The spectroscopic capabilities enable detailed characterization of anything interesting. But telescope time is precious and heavily competed for. Dedicated Dyson sphere searches have to justify their observing programs against other scientific priorities, which means making compelling cases about what specific targets to observe and why. Some researchers advocate for piggyback searches using archival data. Webb observes thousands of fields for various scientific programs. Every observation includes background stars that weren't the primary targets but appear in the data anyway. Mining those archival observations for anomalous infrared sources could identify candidates without requiring dedicated telescope time. The challenge is developing automated analysis pipelines that can process vast amounts of data and flag interesting objects without generating too many false positives. Machine learning approaches show promise for this kind of pattern recognition. Train neural networks on known natural infrared sources, then let them scan new data looking for objects that don't fit established categories. The networks can identify subtle anomalies that might escape human attention or traditional analysis methods. But they also generate false alarms from instrumental artifacts, unusual but natural objects, and data processing errors. Human experts need to review the candidates and separate genuine anomalies from noise. The energy requirements of Dyson spheres constrain where we should look. Building these structures makes sense only for civilizations that need enormous power resources. That likely means technological societies that have exhausted planetary energy sources and expanded beyond their home world. In our own solar system, that transition might happen in centuries or millennia. Other civilizations might reach that point faster or slower depending on their development path and resource availability. Targeting stars with appropriate ages and properties increases the chances of finding structures around systems where civilizations might exist. Stellar evolution timescales matter too. Short-lived massive stars don't give civilizations enough time to develop advanced technology. Long-lived small stars provide stable environments for billions of years. Middle-aged sun-like stars represent a sweet spot where life has had time to evolve and technology could have developed. Focusing searches on these stellar types makes sense from both biological and engineering perspectives. Galactic location influences search strategy as well. The center of the galaxy has higher stellar density, more frequent supernovae, and intense radiation environments that might hinder biological development. The outer regions have fewer heavy elements needed for planet formation and technology. The galactic habitable zone, a region with conditions favorable for life, provides a natural focus for surveys. Webb sensitivity enables examining stars throughout this zone and comparing properties across different galactic environments. Multiple independent detections would provide the strongest evidence. Finding one anomalous infrared source is interesting. Finding 10 that all share similar properties across different stars becomes compelling. Finding 100 would be nearly impossible to explain through natural processes. Building that statistical case requires systematic surveys and consistent analysis methods applied across large samples. The null result carries information too. If we surveyed 10,000 sun-like stars within 1,000 light-years and find no convincing Dyson sphere candidates, that tells us something about the frequency of advanced civilizations in our galaxy. Either they're rarer than we hoped, or they don't build these structures, or they exist but use different technologies we haven't thought to look for. Each possibility has implications for understanding life's place in the universe. Verification protocols for potential detections involve multiple steps. First, detection flags an anomaly in the data. Initial analysis rules out obvious instrumental artifacts and data processing errors. Follow-up observations with the same instrument confirm the signal persists. Observations with different instruments verify the detection isn't specific to one telescope or detector. Multiple teams independently analyze the data to ensure the anomaly isn't an analysis error. Only after clearing all these hurdles do you start seriously considering artificial origins. The bar for claiming detection of artificial structures is extraordinarily high. Natural explanations always get priority until they're exhaustively eliminated. The history of astronomy includes many anomalies that turned out to have mundane explanations once better data became available. Pulsars were briefly considered possible alien beacons. Fast radio bursts generated speculation about artificial origins. In every case, natural explanations eventually prevailed. That pattern teaches caution about jumping to artificial conclusions. But caution doesn't mean dismissing the possibility. Webb's capabilities enable asking questions that couldn't be addressed before. The search continues with better tools, refined methods, and growing datasets. Somewhere in the accumulating observations might be the signature we're looking for, or confirmation that such structures don't exist in our cosmic neighborhood. Either answer advances our understanding. The detection process itself involves layers of complexity beyond simply pointing a telescope and looking. Webb doesn't take traditional photographs. It collects photons across specific wavelength bands, building up spectral energy distributions for each object in its field of view. These distributions reveal how much light an object emits at different infrared wavelengths. A normal star shows a pattern determined by its surface temperature. Hot stars peak at shorter wavelengths. Cool stars peak at longer wavelengths. Physics dictates these relationships precisely. A Dyson sphere breaks those patterns. The star's energy gets absorbed and re-emitted at cooler temperatures. The spectrum shows excess infrared radiation that doesn't match what the star should produce naturally. But identifying that excess requires knowing what the star would look like without the structure. That means determining the star's fundamental properties from whatever light isn't blocked. Spectroscopic analysis provides those clues. Absorption lines in the spectrum reveal which elements exist in the star's atmosphere and in what quantities. Those chemical fingerprints constrain the star's temperature, age, and evolutionary state. Models predict what the complete spectrum should look like. Any deviation from that prediction becomes interesting. The challenge lies in distinguishing artificial structures from natural phenomena that also produce infrared excess. Young stars are surrounded by protoplanetary disks of gas and dust that glow in infrared. But these disks have characteristic spectral features from silicate dust grains and organic molecules. They also show variability as material spirals inward. Dyson spheres shouldn't show those same features or that same behavior. Debris disks around mature stars produce infrared excess too. When asteroids collide or comets disintegrate, they create dust that absorbs starlight and re-irradiates it. But debris disks are typically thin and patchy, not the uniform shells that complete Dyson spheres would create. The spectral signature differs because the dust is distributed differently and the temperatures span a wider range. Evolved stars in late stages of their lives sometimes eject material that forms dusty envelopes. Red giants and asymptotic giant branch stars create shells of gas and dust that glow brightly in infrared. But these objects have distinctive spectral features, and the central star shows signs of advanced age. They're also relatively rare and easy to identify through their unusual properties. Ruling out each natural explanation requires careful analysis of multiple properties simultaneously. Is the infrared excess consistent with dust grain properties? Does the spectrum show features expected from natural dust? Is the star's age compatible with disk formation? Does the light vary in ways that suggest orbiting debris? Only when all natural explanations fail does the artificial hypothesis become worth serious consideration. Machine learning algorithms help sift through massive datasets looking for anomalies. You train neural networks on examples of normal stars, stars with protoplanetary disks, stars with debris disks, and evolved stars with shells. The algorithm learns what each category looks like in terms of spectral properties, brightness variations, and other characteristics. Then you feed it new observations and let it flag anything that doesn't fit the known categories. This approach scales to analyzing millions of stars systematically. Human astronomers can't manually examine every spectrum from every star in a large survey. Algorithms can, highlighting the most interesting candidates for detailed follow-up. But algorithms also make mistakes, flagging instrumental artifacts or rare but natural objects as anomalies. Human verification remains essential. The statistical framework for evaluating detections involves Bayesian reasoning. You start with a prior probability that any given star hosts a Dyson sphere. That probability is extremely low given we've never confirmed one before. Then you update that probability based on the observations. How likely is the observed spectrum if a Dyson sphere exists? How likely is it under various natural explanations? The ratio of those likelihoods determines how much the observations shift your belief. Strong evidence requires the observations to be far more likely under the artificial hypothesis than under natural ones. That's a high bar to clear because natural explanations are numerous and well understood. You need observations that are virtually impossible to explain naturally but perfectly consistent with artificial structures. Multiple wavelength coverage strengthens the case. Webb operates in infrared, but visible light observations reveal the star's properties. Radio observations might detect emissions from power generation or communication. X-ray observations could show activity related to energy collection. Concordance across multiple wavelengths builds confidence that you're seeing something real rather than an artifact of one instrument. Time domain astronomy adds another dimension. Watching objects over weeks, months, or years reveals whether their properties change. Natural disks evolve on observable timescales as material accretes or disperses. Artificial structures might show different variability patterns related to construction activity or operational changes. or they might remain remarkably stable if the structure is complete and in equilibrium. Coordination between space-based and ground-based observatories maximizes coverage. Webb provides unparalleled infrared sensitivity but limited observing time. Ground-based telescopes offer more flexibility and can monitor objects continuously when weather permits. Radio telescopes cover wavelengths Webb can't access. Combining data from multiple facilities creates a more complete picture. International collaboration ensures independent verification. When one team claims a detection, others need access to the data and the ability to perform independent analyses. Scientific journals require this transparency before publication. The discovery of something as significant as artificial structures would trigger immediate scrutiny from the global astronomical community. False positives are inevitable in any search. With millions of stars surveyed, some will show unusual properties purely by chance. Statistical fluctuations, rare natural phenomena, and instrumental quirks create noise in the data. The key is designing search strategies that minimize false positives while remaining sensitive to genuine detections. Setting detection thresholds involves balancing sensitivity and specificity. Lower thresholds catch more potential candidates but generate more false positives. Higher thresholds reduce false positives but risk missing real detections. The optimal threshold depends on the costs of each type of error and the underlying frequency of what you're searching for. Blind analysis techniques reduce bias. Analysts examining data don't know which objects are genuine candidates and which are control samples until after they've completed their analysis. This prevents unconscious bias from influencing judgments about ambiguous cases. Only after finalizing the analysis methods do you reveal which objects are which. The search strategy evolves as observations accumulate. Early results inform where to look next. If initial surveys find no candidates around Sun-like stars, you might expand to other stellar types. If you find candidates that turn out to be a new class of natural objects, you learn how to better distinguish those from artificial structures. Negative results have scientific value. If systematic surveys of thousands of nearby stars find nothing, that constrains how common Dyson spheres can be. Either advanced civilizations are extremely rare, or they don't build these structures, or we fundamentally misunderstand what they would look like. Each possibility teaches us something about the universe. The search also drives technological development. Methods created for finding Dyson spheres improve our ability to characterize exoplanets, study stellar evolution, and understand dust in space. Even if we never find artificial structures, the techniques developed in the search advance astronomy broadly. Public interest in the search generates support for space science. People find the possibility of detecting alien megastructures exciting even if the probability is low. That excitement translates into support for missions and telescopes that enable these searches. The search for technosignatures becomes a gateway for broader engagement with astronomy. Educational opportunities emerge from the search. Students learn about stellar physics, infrared astronomy, data analysis, and the scientific method through involvement in surveys. Whether or not we find anything, training the next generation of astronomers happens through hands-on participation in real research. philosophical implications loom behind the technical details. Finding evidence of artificial structures would fundamentally alter humanity's understanding of its place in the universe. We would know definitively that advanced technological civilizations exist beyond Earth. That knowledge would raise immediate questions about why we haven't detected other signs of their presence and whether contact is possible or desirable. The Fermi paradox gains new dimensions if we find evidence of structures but no communication. Why would a civilization capable of building Dyson spheres not be broadcasting or responding to our signals? Are they uninterested in contact? Are they extinct but their structures remain? Are they so advanced that communication with us seems pointless? Each possibility suggests different futures for our own civilization. Alternatively, finding no evidence after extensive searches sharpens the paradox. If the galaxy is old and large, and if life emerges readily, where are the megastructures? The Great Filter concept suggests some barrier prevents civilizations from reaching this level. Is the filter behind us or ahead of us? The answer has profound implications for humanity's long-term prospects. The search continues regardless of results. Each new observation adds data points. Each refined analysis method improves our ability to distinguish artificial from natural. Each telescope upgrade extends our reach. Somewhere in the accumulating evidence might lie the answer to whether we're alone or whether others have reshaped their solar systems on scales we're only beginning to imagine. The question remains open, but the tools to answer it grow more powerful with each passing year. The timeline for detection depends on factors we can't fully control. Survey depth, available telescope time, and analysis resources all matter. A nearby Dyson sphere might appear in data we already have, waiting for the right analysis method. A distant one might require instruments not yet built. The possibility exists that we've already observed stars hosting partial structures but classified them as natural phenomena. Our catalogs contain millions of objects. Systematic reanalysis with new criteria could reveal candidates hiding in plain sight. This has happened before in astronomy. Pulsars were detected years before anyone recognized what they were. The first exoplanet data existed in archives before the discovery was confirmed. Collaboration between professional astronomers and citizen scientists expands search capacity. Projects like Galaxy Zoo demonstrated that distributed human pattern recognition can process vast datasets. Similar approaches applied to infrared surveys could identify unusual objects that automated algorithms miss. Thousands of eyes examining data spots anomalies that might otherwise go unnoticed. Machine learning offers complementary capabilities. Neural networks trained on known astronomical objects can flag outliers that don't match any established category. These outliers become candidates for closer examination. The combination of human intuition and algorithmic processing creates a powerful search methodology. International cooperation amplifies search effectiveness. Different nations operate different telescopes with different capabilities. Coordinated observation campaigns provide multiple perspectives on candidate objects. What appears ambiguous in one wavelength might resolve clearly in another. What one observatory sees at one time might change when another observatory views it months later. Global networks of astronomers sharing data and analysis methods accelerate the pace of discovery. The economics of the search favor patient, systematic approaches. Unlike missions to distant stars, searching for Dyson spheres costs relatively little. Most observations use existing telescopes during time already allocated for other surveys. Analysis happens on standard computers. The search piggybacks on infrastructure built for other purposes. This efficiency means searches can continue for decades without massive budgets. Persistence becomes feasible in ways it wouldn't be for more expensive endeavors. Cultural factors influence how we interpret potential discoveries. Different societies might view evidence of alien megastructures through different philosophical lenses. Some might see it as validation of technological progress as a universal path. Others might question whether our own trajectory toward large-scale engineering projects serves our long-term interests. The discovery would spark debates about humanity's future that transcend the scientific details. These conversations have value regardless of whether we ever find anything. The search methodology continues evolving as our understanding deepens. Early proposals focused on complete Dyson spheres around single stars. Modern searches consider partial structures, swarms of independent collectors, and constructions around binary systems or unusual stellar types. The possibility space expands as we think more creatively about what advanced civilizations might actually build. Perhaps they prioritize energy capture around pulsars for their stable output. Perhaps they build in stellar nurseries where raw materials are abundant. Perhaps they avoid main sequence stars entirely and focus on white dwarfs or brown dwarfs. Each variation requires different search strategies and produces different observational signatures. The role of serendipity cannot be ignored. Many astronomical discoveries happen by accident when observers notice something unexpected. Someone analyzing data for an unrelated project might spot an infrared excess that doesn't fit any model. Someone testing a new instrument might find an unusual object in a calibration field. The history of astronomy suggests that staying alert to anomalies matters as much as systematic surveys. Both approaches complement each other. Philosophical preparation for discovery seems prudent even if the probability remains low. How would humanity respond to definitive evidence of alien megastructures? Would it unite us around a shared sense of cosmic context? Would it fragment us as different groups interpret the implications differently? Would it change our priorities regarding space exploration, resource allocation, or long-term planning? Thinking through these scenarios before they occur helps us respond thoughtfully rather than reactively. The absence of evidence also carries meaning. If we conduct thorough searches of thousands of nearby stars across multiple wavelengths and find nothing, that null result constrains the prevalence of Dyson spheres. Either they're extraordinarily rare, or advanced civilizations don't build them, or we fundamentally misunderstand what they would look like. Each conclusion teaches us something. The first suggests life rarely reaches advanced technological stages. The second suggests technological development doesn't inevitably lead to massive energy infrastructure. The third suggests our assumptions about alien engineering need revision. All three possibilities reshape how we think about our future. The relationship between Dyson spheres and other technosignatures deserves consideration. If a civilization built structures to capture stellar output, they probably also produce other detectable signatures. Radio transmissions, optical lasers, atmospheric pollution on their planets, or heat from their computational infrastructure might all be detectable. A comprehensive search strategy looks for multiple signatures simultaneously. Finding one type increases the probability of finding others. The searches reinforce each other. Time scales matter profoundly in this search. Human technological civilization has existed for centuries, but systematic astronomy with modern instruments spans only decades. The universe has existed for billions of years. If Dyson spheres exist, they might be built by civilizations millions of years old. The structures themselves might outlast their builders by eons. We might be searching for artifacts of extinct civilizations rather than active ones. That possibility adds poignancy to the search. We might find evidence of greatness long vanished, structures still orbiting stars whose builders disappeared before Earth formed. The search connects to deeper questions about the nature of intelligence and technology. Is large-scale engineering an inevitable outcome of advanced intelligence? Or does intelligence mature beyond the need for physical structures, finding more efficient ways to process information or exist? Perhaps truly advanced civilizations transcend physical form entirely and leave no structures behind. Perhaps they build in ways we can't detect because their methods operate on principles we haven't discovered. These speculations remind us that our search assumptions reflect our current understanding, which might be incomplete. The search for Dyson spheres becomes a mirror reflecting what we might become if we navigate our current filters successfully. We look for evidence of others who survived their technological adolescence and graduated to stellar-scale engineering. In searching for them, we're really asking whether that path exists, whether it's achievable, whether intelligence anywhere ever figures out how to persist long enough to reshape solar systems. The 17 stars wait in the darkness, their light traveling toward us carrying information we're only beginning to decode. Webb waits at L2, its instruments cold and sensitive, ready to collect the photons that will tell us what those stars really are. Astronomers wait at their computers, preparing analysis pipelines and verification protocols for whatever the data reveals. And humanity waits, perhaps without fully realizing it, for an answer to a question we've been asking since we first looked up and wondered if anyone else was looking back. The answer is coming. Not today. Not tomorrow. But soon, on timescales that matter to science if not to individual lives. The data accumulates. The picture clarifies. The universe prepares to tell us something we've wanted to know since we became capable of asking. And when that answer arrives, whether it confirms our hope or our solitude, we'll have earned it through careful observation, rigorous analysis, and the patient application of scientific method to the oldest question our species has ever asked. That's worth something regardless of what the answer turns out to be. "124 light years from Earth, a world exists that shouldn't be possible. Scientists detected something in its atmosphere that, on our planet, only comes from life. Not ancient fossils. Not chemical traces buried in rock. An active signal, present right now, floating in alien skies above an ocean that might stretch deeper than anything in our solar system. K2-18b orbits a dim red star in the constellation Leo, receiving about the same amount of light Earth gets from our Sun. But that's where the similarities end. This planet is more than 8 times Earth's mass and nearly 3 times wider. Its density falls somewhere between our rocky world and the ice giants lurking in the outer solar system. The James Webb Space Telescope aimed its instruments at this distant sphere and found water vapor, methane, carbon dioxide. Then it detected something else. Dimethyl sulfide. A molecule that, as far as we know, only biological processes produce. The scientific community is divided. Some researchers call it the most promising biosignature ever detected beyond Earth. Others point to recent laboratory experiments showing that non-living chemistry might create the same signal. Both groups agree on one thing. We're looking at a type of world that has no equivalent in our solar system, and we're only beginning to understand what it actually is. K2-18b belongs to a class of planets called subneptunes. They're the most common type of planet we've found orbiting other stars, yet we have nothing like them circling our Sun. Too large to be rocky like Earth or Mars. Too small to be gas giants like Jupiter or Saturn. These in-between worlds dominate the galaxy, and until recently, we had no idea what their surfaces might look like. The star K2-18 is what astronomers call an M-dwarf. A red dwarf. Cooler than our Sun by more than 2,000 degrees Celsius. Smaller, with only 45% of our star's radius. From Earth, even with the most powerful telescopes, you can't see it without instruments. It's simply too dim. Yet this unremarkable star, one of trillions like it scattered across the Milky Way, might be hosting something extraordinary. Red dwarfs make up roughly 75 to 80% of all stars in the galaxy. They burn their fuel so slowly that none of them, not a single one born since the universe began, has yet died of old age. K2-18 is estimated to be around 2.4 billion years old. Young by stellar standards. Our Sun is more than twice that age. But even at this relatively early stage, K2-18 has already settled into the calm, steady burn that will continue for hundreds of billions of years. The planet completes one orbit every 33 days. Fast by Earth standards, but this places K2-18b squarely in what scientists call the habitable zone. The distance from a star where temperatures allow liquid water to exist on a planet's surface. Not too hot. Not too cold. The Goldilocks zone, as it's often called, though that nickname hides how complex habitability actually is. When the Kepler Space Telescope first spotted K2-18b in 2015, it was just another data point. A slight dimming of starlight as an object passed in front of its host star. Thousands of such signals were being catalogued. What made this one different emerged later, when scientists calculated the planet's size, mass, and position. Here was a world in the habitable zone, large enough to hold onto a thick atmosphere, but potentially small enough to have a solid surface beneath. Then came the atmosphere measurements. The Hubble Space Telescope detected water vapor in 2019. Not just traces. Significant amounts. But Hubble's instruments couldn't tell us much more. Its sensitivity had limits. The wavelengths it could observe were restricted. Scientists knew there was water, but they couldn't see the full picture. They needed something more powerful. The James Webb Space Telescope changed everything. Launched in late 2021, Webb's mirror is nearly 3 times wider than Hubble's. Its instruments operate in infrared wavelengths that Hubble can barely touch. When Webb observed K2-18b, it needed just 2 transits to gather data that would have taken Hubble years of observations to match. And what Webb saw transformed K2-18b from an interesting discovery into something that might rewrite our understanding of where life can exist. The spectrum showed methane, about 1% of the atmosphere. Carbon dioxide, also around 1%. Water vapor, though less than 0.1% in the upper atmosphere where Webb's instruments are most sensitive. This combination is strange. If K2-18b were just a small version of Neptune, we'd expect to see ammonia. Lots of it. But there's barely any ammonia at all. The absence of something can be just as revealing as its presence. Scientists proposed an explanation that sounds like science fiction. K2-18b might be a Hycean planet. The term combines hydrogen and ocean. Picture this. A rocky core, possibly similar in composition to Earth's. Above it, an ocean. Not like our oceans. Deeper. Much deeper. Potentially hundreds of kilometers deep, stretching across the entire planet. And above that ocean, a thick atmosphere of hydrogen and other gases, pressing down with immense weight. Mikko Madhusudhan at the University of Cambridge coined the term Hycean in 2021. His team realized that planets like K2-18b could maintain liquid water oceans despite having hydrogen atmospheres. Conventional wisdom said such worlds would be too hot. The hydrogen would trap heat, creating runaway greenhouse effects. But the models showed something different. Under the right conditions, with the right distance from the star, these worlds could stay cool enough. The hydrogen blanket wouldn't cook the ocean. It would protect it. This hypothesis explains the atmospheric chemistry Webb detected. An ocean world with a hydrogen atmosphere would have methane and carbon dioxide from biological or geological processes in the water. The hydrogen would react with oxygen, keeping oxygen levels low and preventing ammonia from accumulating. Everything fits. Almost too neatly. Then there's the dimethyl sulfide. DMS, as scientists abbreviate it. On Earth, this molecule comes from phytoplankton, microscopic marine organisms that drift through our oceans by the trillions. When they metabolize certain compounds, they release DMS as a waste product. It rises from the ocean into our atmosphere. You can smell it at the beach sometimes. That distinctive ocean scent. That's partly DMS. We've never found a non-biological process on Earth that produces meaningful amounts of DMS. It's considered one of the most reliable biosignatures we know. So when Webb's data suggested DMS in K2-18b's atmosphere, the implications were staggering. But here's where it gets complicated. The signal isn't strong. Statistically, it's at about 2.7 sigma confidence. In particle physics, scientists don't announce a discovery until they reach 5 sigma. That's a standard that means there's only a 0.00006% chance the signal is just random noise. K2-18b's DMS signal has about a 0.3% chance of being statistical fluctuation. Not terrible, but not conclusive either. More troubling, laboratory experiments in 2024 showed that certain chemical reactions in hydrogen-rich atmospheres can create DMS without biology. Ultraviolet light hitting specific molecules. Chemical pathways we hadn't considered. And in 2024, scientists detected DMS on a comet. A cold, lifeless comet. Suddenly, this supposedly bulletproof biosignature had holes in it. The debate intensified when researchers realized other molecules could be mimicking the DMS signal. Hydrocarbons with similar spectral signatures. Compounds that would look like DMS to Webb's instruments but mean something entirely different. Confirming what's actually there will require more observations. Different instruments. Years of additional data. Some scientists argue K2-18b isn't a water world at all. Recent computer models from September 2025 suggest that in planets this size, chemical processes destroy most water molecules. The hydrogen and oxygen separate. They bond with metals and other elements, sinking into the planet's interior. What looks like a water world from the outside might actually be a gas-rich mini-Neptune with no ocean at all. Just a thick, crushing atmosphere surrounding a core of rock and metal. The alternative interpretation is darker. Instead of a life-bearing ocean, K2-18b could have a surface of molten magma. The hydrogen atmosphere would trap heat efficiently. Too efficiently. The planet would be an inferno beneath its cloudy skies. The atmospheric chemistry we're seeing wouldn't come from life, but from volcanism. From the planet's interior bleeding gases into the sky. Both models fit the data. Both explain what Webb observed. The water world hypothesis needs life to account for the methane levels. The gas-rich model doesn't. Occam's razor suggests we should favor the simpler explanation. But simpler doesn't always mean correct. What makes this so difficult is that K2-18b exists in a category we don't fully understand. Subneptunes have no analog in our solar system. We can't visit one. Can't send a probe. Can't study one up close. Everything we know comes from analyzing starlight that's traveled for over a century through space, passed through an alien atmosphere for a fraction of a second, and then traveled another century to reach our telescopes. We're reading fingerprints in that light. Chemical signatures. Trying to reconstruct an entire world from shadows and spectra. The planet's density offers clues but no certainty. At 2.67 grams per cubic centimeter, it falls between Earth's 5.51 and Neptune's 1.64. That's consistent with a rocky core and thick atmosphere. It's also consistent with a water-rich composition, or an ice-rich interior with a moderate atmosphere. The density alone can't tell us which. The amount of light K2-18b receives is eerily similar to Earth's. About 1,368 watts per square meter, give or take. But that doesn't guarantee habitability. Venus receives almost twice that much, and its surface is hot enough to melt lead. Mars receives less than half, and its surface is a frozen desert. The amount of light matters. But so does the atmosphere. So does the planet's ability to regulate its temperature. So does whether there's even a surface to stand on. Understanding K2-18b means understanding an entirely new category of worlds. And what we learn here will apply to countless other planets. Because subneptunes aren't rare. They're everywhere we look. They're the most common type of planet in the galaxy. Kepler's data changed everything. Before that mission, we thought planets came in two basic sizes. Small and rocky like Earth, or large and gaseous like Jupiter. The survey revealed something else entirely. A population peak between those extremes. Worlds that shouldn't exist according to our solar system's template. They're called subneptunes. Planets ranging from about 1.5 to 4 times Earth's radius. They make up roughly 30 to 50% of all exoplanets we've discovered. Yet we have nothing like them orbiting our sun. It's as if nature's most common planetary configuration somehow skipped us entirely. Or we're the anomaly. This gap in our understanding creates a fundamental problem. When we look at K2-18b, we're not comparing it to anything familiar. We're building models from scratch, testing hypotheses against worlds we've never seen up close. The formation pathways for subneptunes remain contested. One theory suggests they start as rocky cores that accumulate thick hydrogen atmospheres from the protoplanetary disk, born with those massive gas envelopes already in place. Another model proposes they begin as ice-rich bodies that migrate inward. The ice melts under increased stellar radiation. What remains is a water-rich interior beneath a hydrogen atmosphere captured from the disk or outgassed from the planet itself. Both scenarios can produce the same observational signature. Same size. Same density. Same atmospheric composition when viewed from 124 light-years away. But the internal structure would be completely different. One path gives you a rocky world with a thick atmosphere. The other gives you an ocean with a sky. Determining which is correct requires information we don't have. We can't measure K2-18b's internal structure directly. Can't drill into it. Can't send seismic waves through it. We're limited to surface observations, atmospheric analysis, indirect inference. The bimodality in planetary sizes adds another layer to this puzzle. Kepler found that planets cluster around 2 distinct radii. One group peaks at about 1.3 times Earth's size, the other around 2.4 times. There's a gap between them, a radius valley where fewer planets exist. This suggests different evolutionary paths. The smaller group likely represents rocky worlds that lost their atmospheres, stripped away by stellar radiation over billions of years. The larger group retained their gas envelopes. They're the subneptunes, massive enough to hold on to hydrogen despite their star's influence. K2-18b sits right in that larger cluster. But here's what makes this complicated. The radius valley isn't a hard boundary. It's statistical. Plenty of planets exist in the gap. And the position of that valley depends on the star's properties. Hotter stars push it to larger radii. Cooler stars like K2-18 shift it smaller. Which means K2-18b might be right on the edge of atmospheric retention. Balance between keeping its hydrogen envelope and losing it to space. That position matters for habitability. If the planet is losing its atmosphere, then any surface conditions we observe are temporary. The ocean, if it exists, would eventually be exposed to space, stripped away by stellar wind. The hydrogen atmosphere acts as a protective blanket. But if that blanket is thinning, the clock is ticking. We can estimate atmospheric loss rates, but the calculations depend on variables we can't measure precisely. The star's activity level over time, the strength of K2-18b's magnetic field, the exact composition of the upper atmosphere. Small changes in any of those factors alter the timeline dramatically. Then there's the composition uncertainty. The term subneptune implies a Neptune-like structure. But Neptune is an ice giant. Its interior is thought to contain water, methane, and ammonia ices mixed with rock, wrapped in a hydrogen-helium atmosphere. If K2-18b follows that template, it's not a water world at all. It's an ice world. The water would be high-pressure exotic ices. Not liquid. Not an ocean. Just crystalline structures formed under extreme pressure and temperature. Nothing life could use. The alternative is that sub-Neptunes represent a different category entirely. Not scaled-down Neptunes, but something new. A hybrid between rocky planets and gas giants, with internal structures unlike anything in our solar system. If that's true, then the name itself is misleading. We're calling them sub-Neptunes because we lack better terminology. But they might have more in common with super-Earths than with Neptune. The boundary between those categories is blurry. Super-Earths are typically defined as rocky planets up to about 10 Earth masses. Sub-Neptunes as planets with significant hydrogen atmospheres. But a super-Earth with a thick atmosphere could look identical to a small sub-Neptune. Same mass. Same radius. Same density. The only difference would be internal. One has a thin atmosphere over solid rock. The other has a deep atmosphere with no clear surface. K2-18b's mass is 8.63 times Earth's. That puts it at the upper end of super-Earths and the lower end of sub-Neptunes. Right in the transition zone. Which category it belongs to depends on atmospheric mass fraction. How much of the planet is atmosphere versus core? Current estimates suggest K2-18b's atmosphere could be anywhere from 1 to 10% of its total mass. If it's 1%, the planet is mostly rocky with a substantial but not dominant atmosphere. If it's 10%, the atmosphere is so massive it determines the planet's entire structure. That's an order of magnitude uncertainty. And it changes everything about what the planet is like. A 1% atmosphere means there could be a solid or liquid surface beneath. A place where chemistry happens. Where molecules interact. Where, theoretically, life could exist. A 10% atmosphere means the hydrogen layer is so thick and so hot at depth that no surface exists. Just an increasingly dense gas transitioning into supercritical fluids. No boundary. No ocean. Nothing you could call a surface. Recent modeling work has tried to narrow this range. Simulations of sub-Neptune formation suggest that if K2-18b formed in place, its atmosphere should be relatively thin. A few percent at most. But if it formed farther out and migrated inward, it could have captured much more gas. Migration is common. Most exoplanets we've found don't orbit where they formed. They move. Drift inward through gravitational interactions with the protoplanetary disk or with other planets. If K2-18b migrated, its current position tells us nothing about its formation environment. It could have started beyond the snow line where ice is stable. Accumulated a massive atmosphere in the cold outer disk. Then spiraled inward over millions of years. Or it could have formed roughly where it is now. Never migrated far. Retained only a modest atmosphere. Both histories are possible. Both fit the data. The migration question ties directly to composition. Planets that form beyond the snow line should be ice-rich. Water ice, methane ice, ammonia ice. When they migrate inward, that ice heats up. Some of it melts. Some of it vaporizes into the atmosphere. The result is a planet with a water-rich interior and an atmosphere loaded with volatiles. Exactly what you'd expect from a Hycean world. But planets that form inside the snow line would be rock and metal. Drier. Less volatile-rich. Their atmospheres would be captured hydrogen from the disk. Not outgassed water. The composition would be different. So finding water vapor in K2-18b's atmosphere seems to support the migration scenario. Water got there somehow. Either the planet formed with it, or it was delivered later by impacts. But here's the catch. The water vapor concentration is surprisingly low. Less than 0.1% based on Webb's observations. That's not what you'd expect from a planet with a massive water ocean. Earth's atmosphere is about 0.4% water vapor on average. More in the tropics. Less near the poles. But it's detectable. Measurable. On K2-18b, the water vapor signal is weak. Almost suspiciously weak for a supposed water world. One explanation is the cold trap effect. In Earth's atmosphere, water vapor rises until it reaches the cold upper layers. There it freezes out. Forms clouds. Falls back down as precipitation. This creates a cold trap that limits how much water vapor reaches the stratosphere. K2-18b might have an extremely efficient cold trap. Water evaporates from the ocean below. Rises through the hydrogen atmosphere. Hits a cold layer. Freezes. Never makes it to the upper atmosphere where we can detect it. If that's true, the low water vapor signal doesn't mean there's no ocean. It means the ocean is hidden. Locked beneath a thick atmospheric cold trap. Webb is seeing the dry stratosphere. Not the wet layers below. But that interpretation requires the ocean to exist in the first place. And the competing model suggests it doesn't. That K2-18b is a gas-rich mini-Neptune. The methane we see comes from chemistry, not life. The carbon dioxide comes from the star's radiation breaking apart molecules. The water vapor is just trace amounts, left over from formation or delivered by comets. No ocean required. Both models explain the observations. Neither can be ruled out yet. That's the frustrating reality of exoplanet science. We're working with incomplete information. Building castles on uncertain foundations. And K2-18b is just the beginning. There are thousands more sub-Neptunes waiting to be studied. Each one a mystery wrapped in hydrogen and speculation. The real challenge isn't just figuring out what K2-18b is. It's understanding what sub-Neptunes as a class can actually become. Because K2-18b isn't alone out there. Sub-Neptunes are the most common type of planet we've found. They outnumber everything else. Hot Jupiters, super-Earths, Neptune analogs. Sub-Neptunes dominate the census. Kepler found them everywhere. TESS keeps finding more. They orbit red dwarfs, sun-like stars, even slightly hotter F-type stars. And yet we have nothing like them in our own solar system. Earth is too small. Neptune is too big. There's a gap where sub-Neptunes should be. That gap tells us something important. Our solar system might not be typical. The architecture we're used to, rocky planets close in, gas giants farther out, might be the exception rather than the rule. Sub-Neptunes suggest a different kind of planetary system, one where migration is common, where atmospheres are thick, where the boundary between rocky and gaseous isn't clear-cut. Understanding sub-Neptunes means understanding how most planetary systems actually work. And that starts with a basic question. What determines whether a sub-Neptune becomes a Hycean world or stays a mini-Neptune? Size matters. But not in the way you'd think. It's not just about radius or mass. It's about the ratio between the core and the atmosphere. A planet with a large rocky core and a thin atmosphere behaves differently from one with a small core and a massive hydrogen envelope. The core provides gravity, holds the atmosphere down, keeps it from escaping. But if the atmosphere is too thick, the pressure at the base becomes extreme. Temperatures rise. The boundary between atmosphere and surface blurs. You end up with a supercritical fluid. Not quite gas, not quite liquid. Something in between. That's the problem with assuming K2-18b has a solid surface beneath its hydrogen envelope. The pressure might be too high. The temperature might be too extreme. The ocean, if it exists, might not sit on a rocky crust like Earth's oceans do. It could be suspended within layers of supercritical water. Compressed hydrogen above. Dense metallic core below. No clear boundary anywhere. Atmospheric escape changes everything. Hydrogen is light. Really light. It doesn't take much energy to strip it away. Ultraviolet radiation from the host star can do it. Stellar winds can do it. Even the planet's own heat can cause the upper atmosphere to expand and bleed off into space. This process is called hydrodynamic escape. It's why Earth doesn't have a thick hydrogen atmosphere anymore. We lost it early in our history. The sun's radiation stripped it away, left us with nitrogen and oxygen. Secondary atmosphere formed by volcanic outgassing and later by life. Sub-Neptunes around red dwarfs face a different challenge. Red dwarfs are dim. They don't put out as much total energy as the sun. But they're violent, especially when they're young. Stellar flares, coronal mass ejections, intense X-ray and ultraviolet bursts. All of that hammers planets in the habitable zone. K2-18 is about 2.4 billion years old. Not particularly young, but not ancient either. It still flares. Still produces bursts of high-energy radiation. Those bursts can strip away hydrogen, peel back the outer layers of the atmosphere. Over time, a mini-Neptune could lose enough hydrogen to become a super-Earth. The core remains. The ocean, if there was one, might survive. But the thick hydrogen envelope is gone. This process might explain why some sub-Neptunes have thick atmospheres and others don't. It's not just about formation. It's about survival. Here's where things get tricky. If K2-18b is losing hydrogen, how much has it lost already? And how much will it lose in the future? Models suggest that planets around red dwarfs can lose significant fractions of their atmospheres over billions of years. But the rate depends on distance from the star. K2-18b is far enough out that the radiation isn't catastrophic. Close enough that it's not negligible. The balance is delicate. If the planet formed with a massive hydrogen envelope, it might have enough left to maintain the Hycean scenario. If it started with less, the envelope might be thinning, transitioning towards something more Earth-like, or maybe something entirely different. A world with a thin hydrogen layer over a high-pressure steam atmosphere. Neither Hycean nor mini-Neptune. Something new. The methane abundance complicates this picture even further. Methane and hydrogen don't normally coexist in equilibrium. At high temperatures, methane breaks down. Carbon and hydrogen separate. You end up with carbon dioxide and water instead. But K2-18b's atmosphere shows both methane and carbon dioxide. That suggests the atmosphere isn't in equilibrium. Chemical reactions are happening. Slowly. Continuously. Methane is being produced somewhere. Either by geological processes on the surface, if there is a surface, or by life, if there is life, or by photochemistry in the upper atmosphere, driven by starlight. Photochemistry can do strange things. Ultraviolet light breaks molecules apart, creates reactive fragments. Those fragments recombine in unexpected ways. On Titan, Saturn's largest moon, photochemistry produces complex organic molecules. Tholins, long-chain hydrocarbons, even amino acid precursors. All without biology. Just chemistry and sunlight. K2-18b's atmosphere might be doing something similar. Starlight hits the upper layers, breaks apart carbon dioxide and water vapor, creates methane and other organics. The methane we detect isn't proof of life. It's proof of chemistry. Active, ongoing chemistry. But chemistry that could, under the right conditions, lead to biology. Let's talk about that possibility. Life on K2-18b. Not intelligent life. Not civilizations. Just microbes. Simple organisms. Floating in the atmosphere or swimming in the ocean below. If the ocean exists. On Earth, life appeared relatively quickly. Within a few 100 million years of the planet cooling enough to have liquid water. The early Earth was hostile. Volcanic. Bombarded by asteroids. No oxygen in the atmosphere. And yet life took hold. Adapted. Thrived. If life can start on Earth under those conditions, why not on K2-18b? The planet receives similar amounts of starlight. It's in the habitable zone. Temperatures, at least in some layers, might be right. Water is present, even if only as vapor. Carbon dioxide and methane provide building blocks. The hydrogen atmosphere might even help. Hydrogen can act as a reducing agent. Drives certain chemical reactions that produce organic molecules. Early Earth had more hydrogen in its atmosphere than it does now. That might have been important for the origin of life. But there's a problem. Nitrogen. Life as we know it requires nitrogen. Proteins, DNA, RNA, all contain nitrogen. On Earth, nitrogen makes up 78% of the atmosphere. It's abundant. Available. Organisms have evolved to use it. On K2-18b, nitrogen is conspicuously absent. Chemical models suggest nitrogen compounds would be rare. Hard to detect. The atmosphere is hydrogen-dominated. Hydrogen reacts with nitrogen. Forms ammonia. Ammonia is reactive. Breaks down easily. Doesn't accumulate. Without nitrogen, how does life build proteins? How does it store genetic information? Maybe it doesn't. Maybe life on K2-18b, if it exists, uses a different biochemistry. Silicon instead of carbon. Sulfur instead of nitrogen. Entirely different molecular structures. We don't know if that's possible. We've never seen it. But the universe is vast. Chemistry is flexible. What seems impossible might just be unfamiliar. Then there's the question of energy. Life needs energy. On Earth, most life gets it from sunlight, directly or indirectly. Photosynthesis captures light, converts it to chemical energy. Food chains build from there. But K2-18b's atmosphere is thick. Hydrogen scatters light. Clouds and hazes block it. How much sunlight actually reaches the surface? Or the ocean? If there's an ocean, calculations suggest light levels would be low. Dim. Not zero, but not abundant. Photosynthesis might struggle. Life would need to adapt. Use longer wavelengths. Red light, infrared. Or rely on chemical energy instead. Hydrothermal vents on the ocean floor, if there is a floor, could provide energy. Chemical gradients. Dissolved minerals. Life could cluster around those vents. Just like it does on Earth in the deep ocean. Far from sunlight. Thriving on chemistry alone. That kind of life wouldn't produce oxygen. Wouldn't change the atmosphere. Wouldn't leave obvious biosignatures. It would be invisible to our telescopes. Hidden beneath kilometers of hydrogen and water. We'd never know it was there unless we sent a probe. And even then, finding it would be hard. Life in the deep ocean is sparse. Scattered. Easy to miss. This brings us back to dimethyl sulfide. The controversial biosignature. The molecule that might or might not be there. On Earth, DMS comes from phytoplankton. Tiny marine organisms. They produce it as a byproduct of their metabolism. It escapes into the atmosphere. We can measure it. Use it to track biological activity in the oceans. Finding DMS on K2-18b would be huge. Direct evidence of life. A smoking gun. But the signal is weak. Tentative. Barely above the noise. And there are alternative explanations. Photochemistry. Geological processes. Comets. Even measurement error. The signal could be real but not biological. Or it could be an artifact. Something in the data that looks like DMS but isn't. Distinguishing between these possibilities requires better data. More observations. Higher precision. And that means waiting. For Webb to observe K2-18b again. For future telescopes to come online. For technology to improve. Science moves slowly. Especially when the stakes are this high. But here's what makes the wait so difficult. Every month that passes is a month we could be getting answers. Every telescope hour allocated to other targets is an hour not spent on K2-18b. And the competition is fierce. Webb is the most in-demand telescope in history. Thousands of proposals. Hundreds of targets. Everyone wants time. Everyone has questions that need answering. K2-18b is important, but so are distant galaxies, forming stars, other exoplanets. The telescope can only look at one thing at a time. So we wait. Meanwhile, the debate intensifies. Papers published. Rebuttals written. Models refined. Each new analysis shifts the probability slightly. Sometimes toward life. Sometimes away from it. The scientific process grinding forward at its characteristic pace. Methodical. Careful. Frustratingly slow when you want a definitive answer right now. But this is how science works. How it has to work. Extraordinary claims require extraordinary evidence. And we're not there yet. What we do have is context. K2-18b isn't the only sub-Neptune we've found. There are hundreds. Maybe thousands. Most haven't been studied in detail. Most never will be. Too faint. Too far. Wrong geometry for transits. But they exist. A whole population of worlds between Earth and Neptune in size. And we don't really understand them. Our solar system doesn't have anything like this. Nothing between Earth's radius and Neptune's. No intermediate examples to study up close. So we're learning from scratch. Building models. Testing hypotheses. Figuring out what these worlds actually are. The term sub-Neptune is almost misleading. It suggests a smaller version of Neptune. A mini ice giant. But that might not be accurate. Some could be ocean worlds. Others might be rocky planets with thick atmospheres. Some could have hydrogen envelopes sitting on top of molten surfaces. Magma oceans underneath, not liquid water. The possibilities are broad. Too broad. We need more data to narrow them down. And K2-18b, because it's bright enough to study, becomes a test case. A prototype. If we can figure out what it is, we might understand the whole population. That's why the stakes are so high. This isn't just about one planet. It's about an entire class. Understanding K2-18b means understanding thousands of other worlds we'll discover in the coming decades. Some closer. Some in better positions for study. Some around quieter stars. K2-18b might not be the best candidate for life. But it's the first one we can actually characterize. The first one where we can measure atmospheric composition in detail. That makes it invaluable. Even if the answer turns out to be disappointing. And disappointing is still possible. Likely, even. Most planets aren't habitable. Most don't have life. The universe is vast, but it's also mostly empty. Mostly hostile. Finding even microbial life on another world would be the discovery of the millennium. Maybe of human history. But it's not guaranteed. Not even probable, depending on who you ask. The odds are uncertain. The universe hasn't told us yet how common life is. K2-18b could be the first clue. Or it could be another dead end. Consider what we're actually looking for. Not cities. Not technology. Not intelligence. Just chemistry. Molecules that shouldn't be there unless something is producing them. Something alive. On Earth, that's oxygen. Methane combined with oxygen. Certain gases that react quickly and disappear unless constantly replenished. Biosignatures. But they're not foolproof. Nature is clever. Abiotic processes can mimic biology. Volcanoes produce gases. Lightning creates compounds. Photochemistry, the interaction of light with molecules, can generate complex chemistry without any life involved. Distinguishing between biological and non-biological sources is hard. Sometimes impossible without visiting the planet directly. That's the limitation we're up against. We can study atmospheres from 124 light-years away. Incredible. Revolutionary. But there's only so much we can learn from a distance. We can measure what's there. But understanding why it's there, what's producing it, that's harder. Requires models. Assumptions. Educated guesses. And those can be wrong. Have been wrong before. Will be wrong again. Science corrects itself over time. But in the moment, uncertainty dominates. So what happens next? More observations. That's certain. Webb will observe K2-18b again. Has to. The question is too important to leave hanging. But scheduling is complex. Coordinating telescope time takes years. Planning observations. Analyzing data. Writing papers. More years. We might not have definitive answers for another decade. Maybe longer. That's the reality of astronomy. Progress measured in years, not weeks. Patience isn't optional. It's required. But there's reason for optimism too. Technology improves. Future telescopes are coming. Larger mirrors. Better instruments. More sensitive detectors. The extremely large telescope. The Habitable Worlds Observatory. Missions specifically designed to study planets like K2-18b. They'll see things Webb can't. Measure molecules at lower concentrations. Distinguish between different sources more effectively. Build better models of what these worlds actually look like. And there's another approach. Direct imaging. Instead of watching planets transit their stars, just photograph them directly. Block out the star's light. Image the planet itself. Incredibly difficult. Requires advanced technology. Adaptive optics. Coronagraphs. Star shades. But it's being developed. Tested. In a few decades, we might be able to take actual pictures of planets like K2-18b. See their surfaces, if they have surfaces. Watch their weather. Map their features. That would change everything. For now, though, we're limited to spectroscopy. Reading the rainbow. Decoding the light that filters through alien air. It's indirect, but it works. We've learned more about exoplanet atmospheres in the past 5 years than in the entire previous history of astronomy. And it's accelerating. Each new observation teaches us something. Each planet studied adds to the picture. K2-18b is part of that larger story. One chapter in a book we're still writing. And maybe that's the real point. Not whether K2-18b has life right now, but what it represents. The beginning of a new era, when we can actually study other worlds in detail, characterize their atmospheres, ask meaningful questions about habitability, about life, about our place in the universe. For most of human history, those were philosophical questions. Abstract, unanswerable. Now they're scientific questions. Testable. With data. With evidence. That's profound. Whether K2-18b itself is inhabited or not, the fact that we can ask the question, that we have tools to investigate, that's the real breakthrough. Because K2-18b won't be the last. There will be others. Better candidates. Closer stars. More favorable conditions. Planets around sun-like stars instead of red dwarfs. Worlds with oxygen-rich atmospheres. Clearer biosignatures. Less ambiguity. K2-18b is just the first we've been able to study seriously. The first where the technology caught up with the ambition. It's a pioneer. And pioneers are messy. Complicated. Full of contradictions and uncertainty. But they open the path. They show what's possible. They teach us what questions to ask and how to answer them. That's K2-18b's role. Not to give us easy answers, but to show us where to look next. And pioneers teach us what we got wrong. That's crucial. Because K2-18b revealed something uncomfortable. Our models weren't good enough. The planet defied easy categorization. Water world. Maybe. Mini Neptune. Possibly. Something else entirely. Can't rule it out. The data fit multiple scenarios. That's the problem. Or rather, that's the lesson. Before K2-18b, scientists had theoretical models. Predictions about what these planets might be like. How thick their atmospheres were. What molecules they'd contain. How heat would distribute across their surfaces. Then Webb looked. And the reality was messier than the theory. More complicated. The methane levels were higher than expected. The carbon dioxide signal weaker. The temperature structure didn't match predictions. It forced a reckoning. Not with the planet, but with the models. They needed updating. Refinement. More variables. Better physics. That's how science actually works. Not smooth and linear. Messy and iterative. You think you understand something. Then you measure it. And you are partly right and partly wrong. So you adjust. Build better models. Test them. Repeat. K2-18b is driving that cycle now, forcing researchers to confront assumptions about how hydrogen atmospheres behave, how carbon cycles through these worlds, what makes a planet habitable versus just temperate. These aren't small questions. They're fundamental, and they affect how we interpret every other planet we study. Because K2-18b isn't unique. It's typical. Sub-Neptunes are everywhere. Most common planet type in the galaxy. We don't have any in our solar system. Nothing between Earth and Neptune. That gap in size. So we're learning about them from scratch. No local examples to study up close. Just distant observations. Light filtered through alien air. And K2-18b is the best example we have so far. Close enough to study. Bright enough star. Favorable geometry. Regular transits. It checks the boxes. That's why it matters so much. Not because it definitely has life, but because it's teachable. A planet we can actually learn from. And what it's teaching is humility. The universe is more complex than our models. Always has been. Always will be. That's not a failure. It's the nature of discovery. You start with simple ideas. Basic physics. Clean predictions. Then reality shows up. And it's complicated. Full of edge cases. Unexpected interactions. Chemistry you didn't account for. Physics you oversimplified. So you adapt. That's the process. And K2-18b is accelerating it. Each observation adds data. Constraints. Things the planet can't be. Things it might be. Slowly, the possibilities narrow. Not to a single answer. Not yet. But toward better questions. More refined hypotheses. Testable predictions. That's progress. Even when it feels slow. Even when headlines oversell the findings. Even when the public wants simple answers and scientists can only offer complex probabilities. The truth is, K2-18b is forcing us to develop new tools. Not just instruments. Conceptual tools. Ways of thinking about planets that don't fit Earth's mold. Because for centuries, we only knew one planet with life. Ours. So naturally, we looked for Earth twins. Similar size. Similar composition. Similar star. That made sense. Start with what you know. But K2-18b isn't an Earth twin. Not even close. 8 times the mass. Hydrogen atmosphere. Orbiting a red dwarf. Everything's different. Yet it might still be habitable. Might. That possibility is reshaping the field. Expanding what we look for. How we define habitability. Because if life can exist there, under those conditions, then the range of possibilities is much wider than we thought. More planets qualify. More systems to study. more chances to find something. But here's the thing. We still don't know if K2-18b itself qualifies. The jury's still out. And might be for years. Because this isn't a simple measurement. It's an interpretation problem. The data is real. The spectra are accurate. But what they mean depends on context we don't fully have. Temperature profile of the atmosphere. Unknown. Circulation patterns. Unknown. Cloud coverage. Unknown. Surface conditions, if there even is a surface. Unknown. We're trying to solve a puzzle with most pieces missing. And some pieces might not even belong to this puzzle. They might be contamination, noise, artifacts of how we process the data. That's always a risk. Especially with signals at the edge of detectability. You see a pattern. Is it real? Or is it statistical fluctuation? 3 sigma confidence sounds impressive. Until you remember that means 1 in 370 chance it's random. Not 0. Not definitive. Just probable. And when you're looking at dozens of molecules simultaneously, running hundreds of models, testing thousands of parameters, probabilities compound. False positives become likely. Not intentional. Just statistical reality. That's why the 5 sigma threshold exists. To separate signal from noise. To ensure discoveries are robust. Reproducible. Real. K2-18b's DMS signal doesn't meet that standard. Not yet. Maybe not ever. But that doesn't diminish its importance. Because even the possibility, even the hint, even the suggestion that we might be seeing biosignatures, that changes the conversation. It makes this planet a priority. A target for follow-up. A case study for how to do this kind of science carefully. How to communicate uncertainty. How to balance excitement with rigor. And that's valuable. Because the next planet might have clearer signals. Stronger evidence. Less ambiguity. And we'll know how to handle it because we practiced on K2-18b. Made mistakes. Learned lessons. Refined our methods. That's the real legacy. Not whether this specific planet has life, but what studying it teaches us about finding life elsewhere. The techniques we develop. The models we build. The standards we establish. Those will outlast any single discovery. They'll apply to dozens of planets. Hundreds eventually. Each one adding to the picture. Some will be false alarms. Others dead ends. A few might be genuine hits. But we won't know which is which unless we do the work. Carefully. Methodically. Without rushing to conclusions. And that's harder than it sounds. Because there's pressure. From media. From funding agencies. From the public. Everyone wants answers. Clear, simple, definitive answers. But science doesn't work that way. Especially not at the frontier. Especially not when you're trying to detect life across interstellar distances using instruments that barely existed 5 years ago. It's messy. It's uncertain. It's frustrating. But it's also exhilarating. Because we're doing something humans have never done before. Seriously investigating whether life exists beyond Earth. Not philosophically. Not speculatively. With data. With measurements. With evidence. That's unprecedented. And K2-18b sits right at the center of that revolution. Not because it's perfect, but because it's real. A planet we can study. An atmosphere we can probe. A mystery we can actually investigate. And whatever we find, whether it's life or just chemistry, whether it's ocean or magma, whether it's habitable or hostile, we'll have learned something profound. About how planets work. About what conditions permit life. About where to look next. That knowledge is cumulative. Each planet studied makes the next one easier. Each technique refined makes the next observation sharper. Each model improved makes the next interpretation clearer. We're building a framework. Step by step. Planet by planet. And K2-18b is a cornerstone. Not the first. Not the last. But essential. A planet that pushed us forward. That revealed our ignorance. That showed us how much we still have to learn. That's its gift. Not easy answers, but better questions. And the questions we ask now shape the answers we'll find later. What should we look for? How should we interpret ambiguous data? When should we claim discovery versus admitting uncertainty? Those aren't abstract philosophical debates. They're practical decisions that determine whether we find life in our lifetime or waste decades chasing ghosts. K2-18b forces us to confront those choices. Because it's not giving us clear answers. It's giving us complicated, messy, frustrating data that could mean multiple things. And how we respond to that, how we handle the ambiguity, sets precedent. Do we rush to conclusions because we want headlines? Or do we acknowledge limitations and keep working? The scientific community chose the latter. Mostly. There were sensational press releases, premature celebrations, media coverage that outpaced the actual findings. But the researchers themselves have been cautious, transparent about uncertainties, clear about what's confirmed versus speculated. That's progress. Because a generation ago, we might not have had that discipline. The temptation to claim discovery would have been overwhelming. Now we know better. We've learned from past mistakes. From claims that didn't hold up. From excitement that turned to embarrassment. K2-18b benefits from that institutional memory. From a scientific culture that values rigor over speed. And that matters more than any single detection. Because the next planet might have clearer biosignatures, stronger signals, less ambiguity. And when it does, we'll need a framework for evaluating it. Standards for what counts as evidence. Protocols for verification. K2-18b is building that framework. In real time. Under pressure. With the world watching. It's not ideal. But it's necessary. Because we can't wait until we have perfect data to figure out how to handle it. We need to learn by doing. Make mistakes now so we don't make them later. And that's what's happening. Every paper published about K2-18b adds to our understanding, not just of this planet, but of the process. How to model atmospheres. How to account for uncertainties. How to distinguish chemistry from biology. Those lessons apply everywhere. To every exoplanet. Every future observation. Every potential biosignature. That's the infrastructure of discovery. The unsexy foundation work that makes breakthroughs possible. And K2-18b is central to that effort. Not because it's special, but because it's available. A planet we can study right now with instruments that exist today. That's rare. Most potentially habitable planets are too far away, their stars too dim, their signals too weak. K2-18b is in a sweet spot. Close enough to observe. Bright enough to measure. Complex enough to challenge us. That combination won't exist for many planets. So we study this one intensely. Extract every bit of information. Push our instruments to their limits. Because opportunities like this don't come often. And we can't afford to waste them. Which brings us to the next question. What happens now? More observations, obviously. Different instruments. Longer integration times. New wavelengths. Each one adding detail. Resolving ambiguities. Confirming or refuting earlier findings. That's already happening. Teams are analyzing additional JWST data. Planning follow-up campaigns. Developing new models. The work doesn't stop just because we published papers. It accelerates. Because now we know what to look for. Where the gaps are. What measurements would be most valuable. That focus is powerful. It turns vague curiosity into specific research programs. Transforms speculation into testable hypotheses. Converts possibilities into probabilities. But there's a limit to what we can learn from K2-18b alone. At some point, we'll extract everything we can from this planet. Hit diminishing returns. Need new targets. And that's fine. Because K2-18b was never meant to answer every question. Just the first ones. Just enough to show us what's possible. To prove that we can characterize sub-Neptune atmospheres. Detect carbon-bearing molecules. Search for biosignatures across interstellar distances. Those capabilities are transformative. They change what's achievable. What's worth attempting. What deserves funding. Before JWST, most of this would have been impossible. Now it's routine. Difficult, but routine. And as technology improves, as instruments become more sensitive, as techniques get refined, it'll become easier. Cheaper. Faster. That's the trajectory. From impossible to hard to standard. K2-18b represents the transition point. The moment when characterizing potentially habitable exoplanet atmospheres became feasible. Not easy, but feasible. And once something becomes feasible, it scales. More planets get observed. More data gets collected. More patterns emerge. Eventually, we'll have it cataloged. Dozens of atmospheres. Hundreds maybe. Each one revealing something about planetary formation, chemical evolution, habitability conditions. Some will be dead worlds. Others ambiguous. A few might show genuine biosignatures. But we won't know which is which until we look. And K2-18b taught us how to look. Where to point our telescopes. What wavelengths to prioritize. What molecules to search for. That knowledge compounds. Each planet studied makes the next one easier. Each technique developed makes future observations sharper. Each model validated makes new interpretations clearer. We're building momentum. And it's happening faster than anyone expected. 5 years ago, most scientists thought this kind of atmospheric characterization was decades away. Now we're doing it. Publishing results. Debating interpretations. Planning follow-ups. That acceleration is real. And it's not slowing down. Because the tools keep improving. Nancy Grace Roman Space Telescope launches soon. Then the Habitable Worlds Observatory. Each one more powerful than the last. Each one capable of observations that seem impossible today. And each one will look at planets like K2-18b. But better. With more precision. Less ambiguity. Stronger constraints. Until eventually, the question isn't whether we can detect biosignatures. It's whether the biosignatures are actually there. That's the future K2-18b is pointing toward. A future where finding life becomes a matter of observation rather than speculation. Where we can definitively say whether a planet hosts biology or just chemistry. Where ambiguity gives way to certainty. We're not there yet. Not close. But we're moving in the right direction. And every planet like K2-18b moves us further. Teaches us more. Reveals our blind spots. Exposes our assumptions. Challenges our methods. That's uncomfortable. But it's how science progresses. Not through easy answers, but through difficult questions. Not through confirmation, but through challenge. Not through certainty, but through doubt refined into knowledge. K2-18b embodies that process. A planet that refuses to fit our categories. That demands we think harder. Look closer. Question more deeply. It's frustrating. But it's also exactly what we need. Because finding life won't be easy. Won't be obvious. Won't announce itself clearly. It'll be subtle. Ambiguous. Contested. Just like the DMS signal. Just like the methane anomaly. Just like everything about K2-18b. And if we can't handle that complexity now, we won't handle it later. When the stakes are higher. When the evidence is stronger. When the implications are clearer. So we practice. On this planet. In this moment. With these tools. Learning how to do the hardest thing humans have ever attempted. Detecting life beyond Earth. Not through radio signals or spaceships. But through chemistry. Through light filtered through alien air. through patterns in spectra that might mean biology, or might not. That uncertainty is the point. Because life, if it exists elsewhere, won't accommodate our expectations, won't match our templates, won't make detection easy. It'll force us to expand our definitions, challenge our assumptions, rethink what we mean by alive. K2-18b is the first real test of whether we're ready for that challenge. And the answer so far is mixed. We're learning, improving, getting better at handling ambiguity. But we're also realizing how much we don't know, how many assumptions we made, how limited our frameworks are. That's humbling. But it's also necessary. Because the universe doesn't care about our limitations. It is what it is. And if we want to understand it, we need to adapt. Build better tools. Develop better theories. Ask better questions. K2-18b is teaching us how. So here's what we're left with. A planet 124 light-years away that we can't visit. Can't probe directly. Can't sample. All we have is light. Starlight that passed through an atmosphere for a fraction of a second before traveling more than a century to reach our telescopes. And from that light, we're trying to determine if life exists. Not intelligent life. Not civilizations. Just microbes. Chemistry that might be biological. Or might not. That's the reality. That's the challenge. And K2-18b sits at the center of it. Not because it's perfect. Not because it has clear answers. But because it's the first planet where we could even ask the question seriously. With data, with evidence, with instruments powerful enough to see molecular signatures in alien air. That's unprecedented. For all of human history, the question of life beyond Earth was philosophical, abstract. Now it's scientific, testable. We have tools, methods, frameworks. They're imperfect, incomplete, but they exist. And they're improving. Every observation teaches us something. Every model refined makes the next interpretation clearer. Every technique developed makes future discoveries more likely. K2-18b is part of that process. Not the end point. Not even a highlight. Just a step. An important step. The moment when characterizing potentially habitable exoplanet atmospheres became feasible. When we could look at a sub-Neptune and actually measure what's in its air. Methane. Carbon dioxide. Water vapor. Maybe dimethyl sulfide. Maybe not. The uncertainty doesn't diminish the achievement. It defines it. Because this is what discovery looks like at the frontier. Messy. Complicated. Full of competing interpretations and provisional conclusions. Science doesn't give us clean narratives. It gives us data. And we argue about what it means. Build models. Test predictions. Wait for more observations. That cycle continues. For K2-18b. For dozens of other planets. For centuries probably. Until we either find life or conclude it's rarer than we hoped. But we won't get there by expecting easy answers. By demanding certainty before we've done the work. We'll get there by doing what we're doing now. Carefully. Methodically. With appropriate skepticism and appropriate excitement balanced in tension. Learning from mistakes. Refining methods. Building infrastructure that outlasts any single discovery. That's K2-18b's legacy. Not whether it hosts life, but what studying it teaches us about looking. About the questions we can answer and the ones we can't. About the difference between possibility and probability. Between hint and confirmation. Between exciting and definitive. Those distinctions matter. They determine whether we find something real or chase phantoms for decades. And K2-18b is where we're learning to make them. In real time. Under pressure. With limited data and unlimited speculation. It's not ideal. But it's necessary. Because the universe doesn't wait for us to be ready. It exists whether we understand it or not. And planets like K2-18b, worlds that defy our categories and challenge our assumptions, they're not obstacles. They're opportunities. Chances to expand our thinking. To recognize what we don't know. To build better frameworks for finding answers. That work isn't glamorous. Doesn't make headlines. But it's what enables breakthroughs. What transforms speculation into science. What turns curiosity into knowledge. And somewhere in that process, maybe on K2-18b or maybe on some planet we haven't discovered yet, we'll find what we're looking for. Evidence. Real, undeniable, reproducible evidence that life exists beyond Earth. Or we won't. And that answer matters too. Because knowing we're alone would be just as profound as knowing we're not. Either way, we'll have learned something fundamental about the universe. About how common or rare the conditions for life actually are. About whether Earth is typical or exceptional. About our place in a cosmos that's been indifferent to our existence for 13.8 billion years. K2-18b won't answer those questions alone. But it's helping us figure out how to ask them properly. How to design the observations. How to interpret the results. How to distinguish signal from noise. That contribution is permanent. Whatever we eventually discover about this specific planet, the methods we develop studying it will persist. Applied to other worlds. Other mysteries. Other questions we haven't even formulated yet. That's how science builds. Incrementally. One planet. One observation. One refined technique at a time. And right now, in this moment, K2-18b is where that building is happening. Not the foundation. Not the pinnacle. Just one crucial piece in a structure that's still taking shape. A structure that might eventually tell us whether we're alone. And if we're not, what life looks like when it doesn't look like us.
A single teaspoon of this star weighs more than all of humanity combined. Its magnetic field could erase your credit card from halfway to the moon. And if it had a bad day 42,000 years ago, you'd know about it right now. These unhypothetical monsters from science fiction. They're real, they're out there, and they've already touched our planet in ways that should terrify you. Magnetars represent the most extreme magnetic environments in the known universe. Picture Manhattan Island compressed into a ball so dense that a sugar cube of its material would weigh as much as an entire mountain. Now wrap that impossibility in a magnetic field a quadrillion times stronger than Earth's. That's a magnetar. 20 kilometers across, spinning several times per second, radiating more energy in a tenth of a second than our sun produces in 150,000 years. The numbers seem designed to break human comprehension. A magnetic field of 10 to the 15th Gauss. Energy densities 10,000 times greater than lead. Forces so intense they warp the fabric of empty space itself. But here's what makes magnetars truly unsettling: we didn't predict them. We stumbled onto them by accident when they announced themselves by nearly blinding our satellites. March 5, 1979. Soviet spacecraft Venera 11 and 12, cruising through their lonely orbits around the Sun, suddenly screamed with radiation. Not the gentle background hiss of cosmic rays, but a tsunami that drove their detectors from 100 counts per second to over 200,000 in a fraction of a millisecond. 11 seconds later, Helios 2, a NASA probe, was overwhelmed. Then Venus. Then 3 Defense Department satellites, a Soviet weather satellite, and the Einstein Observatory all registered the same impossible spike. Every spacecraft pointed at different parts of the sky. Direction didn't matter. The wave hit everything. Scientists triangulated the source to an accuracy of 2 arc-seconds. The origin point. A supernova remnant in the Large Magellanic Cloud, the shattered corpse of a star that had died around 3000 BCE. Whatever happened there sent a pulse of gamma radiation across 50,000 light-years of space powerful enough to saturate instruments throughout our solar system. At the time, it was the strongest burst of extrasolar gamma rays ever recorded, over 100 times more intense than anything previously observed. They had no idea what could do that. The star was already dead. It had exploded millennia before humans built the pyramids. Yet somehow, its remnant had just coughed up enough energy to announce its presence across a galaxy. The answer wouldn't arrive for another 13 years. In 1992, physicists Robert Duncan and Christopher Thomson published a paper proposing something that seemed to violate common sense. They suggested that certain neutron stars could generate magnetic fields exceeding a quadrillion Gauss, far beyond what any known physical process should produce. The mechanism involved a perfect storm of conditions during the star's violent birth. If the spin rate, temperature, and initial magnetic field aligned just right, a dynamo effect could convert rotational energy and heat into magnetic energy on a scale that dwarfed anything else in nature. They called these objects magnetars. Most neutron stars already carried magnetic fields around 1 trillion Gauss. That alone makes them magnetic beyond human experience. But magnetars cranked that dial 1,000 times higher. Duncan and Thomson predicted these objects would be rare, violent, and obvious. They'd betray themselves through bursts of X-rays and gamma rays as their own magnetic fields tortured them. The Rossi X-ray Timing Explorer confirmed it in the mid-90s. The mysterious gamma-ray bursters, the soft gamma repeaters that had puzzled astronomers for decades, were neutron stars. Incredibly dense, incredibly magnetic, and incredibly unstable. By July 2021, astronomers had confirmed 24 magnetars. That number hides a darker truth. For every active magnetar we can detect, there might be 1 million dead ones drifting silent through the galaxy, their fields decayed below detection threshold, their fury spent. Understanding what a magnetar actually is requires confronting densities that don't exist anywhere else we can observe. When a massive star, 10 to 25 times the Sun's mass, exhausts its fuel, the core collapses in less than a second. Electrons get crushed into protons, forming neutrons. If the core mass falls between 1 and 3 solar masses, neutron degeneracy pressure stops the collapse. What's left is a ball of neutrons about 20 kilometers across, spinning furiously, hot enough to glow in X-rays. The density defies intuition. A tablespoon of neutron star material masses over 100 million tons. A chunk the size of a ping-pong ball outweighs 1 billion metric tons. You could fit 500,000 Earth masses into a sphere the size of Manhattan. The surface gravity exceeds 200 billion times what you experience standing on Earth. Light itself bends noticeably around these objects. Now add magnetism. Most neutron stars inherit magnetic fields from their progenitor stars, amplified by compression. A regular neutron star carries about 1 trillion Gauss. That's already incomprehensible. The strongest continuous magnetic field ever produced in a laboratory reaches about 45 Tesla, roughly 450,000 Gauss. Earth's magnetic field averages 0.5 Gauss. A refrigerator magnet clocks in around 100 Gauss. An MRI machine might hit 3 Tesla. A magnetar laughs at these numbers. 10 to the 15th Gauss. 100 million times stronger than the most powerful human-made magnet. 1 trillion times Earth's field. The energy density of this magnetic field alone exceeds the mass density of lead by a factor of 10,000. You could theoretically power human civilization for millions of years on the magnetic energy stored in a single magnetar. But you can't extract it. The field isn't a tool. It's a prison. And the prisoner is the magnetar itself. The magnetic field doesn't float peacefully around the star. It's anchored to the crust, a solid shell of atomic nuclei crushed into a crystalline lattice. The crust is tough, held together by electromagnetic forces operating under extreme pressure. But the magnetic field is tougher. As the field evolves, shifting and reorganizing according to laws we barely understand, it stresses the crust. The forces involved exceed anything in human experience. Eventually, something breaks. Picture the crust fracturing. Not a gentle crack, but a catastrophic failure propagating at nearly the speed of sound through nuclear matter. The magnetic field, suddenly released from its constraints, snaps into a new configuration. This reorganization dumps energy into the surrounding space as electromagnetic radiation. Gamma rays, X-rays, radio waves. The star doesn't just crack. It screams. Scientists call these events starquakes. The comparison to earthquakes is almost insulting. The most powerful earthquake ever recorded by humans, the 9.5 magnitude Chilean quake of 1960, released about 10 to the 18th joules of energy. Devastating. Civilization-altering. A magnetar starquake associated with a giant flare would register magnitude 23 on the same scale. There is no scale for magnitude 23. We invented the scale to measure Earth. It doesn't go that high because nothing on Earth goes that high. December 27, 2004. Astronomers were wrapping up the year, looking forward to holidays, probably not expecting the universe to remind them how small they were. Then SGR 1806-20, a magnetar 42,000 light-years away in Sagittarius, decided to adjust its magnetic field. The starquake lasted 1/10 of a second. In that sliver of time, the magnetar released more energy than the Sun produces in 150,000 years. The radiation burst across space at light speed, an expanding shell of gamma rays carrying 10 to the 40th joules of energy. 42,000 years later, it arrived at Earth. At least 15 satellites and spacecraft detected it simultaneously. Their instruments weren't designed for this. Most were overwhelmed instantly, their detectors driven off-scale regardless of which direction they faced. The Russian satellite Koronazev picked up gamma rays that had bounced off the moon. The radiation didn't just hit our spacecraft. It hit Earth's atmosphere directly, ionizing atoms throughout the ionosphere, briefly expanding it, disrupting long-wavelength radio communications for 5 minutes. Solar flares disrupt radio. We're used to that. But this was deeper, more thorough, more violent than the biggest solar flare ever recorded. And it came from a dead star on the opposite side of the galaxy. The brightness was obscene. In gamma rays, the burst reached an absolute magnitude around -29. For context, that made it briefly the brightest object visible from Earth outside our solar system, outshining everything except the sun and moon. Not bad for something smaller than a city that died before humans invented writing. This is the point where the human mind starts looking for exits. We evolved to understand falling rocks and angry predators. We developed tools to comprehend planets and stars. But magnetars exist in a regime where our intuitions simply break. They're not just powerful. They're powerful in ways that rewrite the rules. And we're only beginning to understand what they can do. Because here's what keeps astronomers awake at night. SGR 1806-20 is 42,000 light-years away. The nearest confirmed magnetar, 1E 1048.1 to 5937, sits 9,000 light-years out in Carina. That seems safe. That seems like enough distance to insulate us from whatever cosmic tantrums these objects throw. But the mathematics of inverse square law are unforgiving. If a magnetar 1/5 that distance experienced a similar outburst, the impact on Earth would be 25 times stronger. At 10 light-years, a giant flare could strip our ozone layer, sterilize the surface, and trigger mass extinction comparable to a 12-kiloton nuclear detonation 7 kilometers up. 10 light-years. That's nothing. That's the distance to a handful of nearby stars. We don't currently know of any magnetars that close, but that knowledge comes with an uncomfortable caveat. We've only confirmed 24 magnetars total. We detect them when they're active, when they're young and violent and screaming radiation into space. After about 10,000 years, their magnetic fields decay. They go quiet. They become invisible to our instruments. Statistical estimates suggest 30 million dead magnetars drift through the Milky Way alone. Invisible. Silent. Waiting. Most will never wake up. Their fields are spent, their violence exhausted. But we don't know all the ways a magnetar can form, all the paths that lead to these magnetic monsters, or what might trigger a dead one to suddenly remember what it used to be. What we do know is this: the universe has already demonstrated it can reach across tens of thousands of light-years and touch our planet with the aftershock of stellar violence. The December 2004 event was a warning shot from a weapon we didn't know existed, fired by an enemy that died before we evolved. And the truly unsettling part: that was just the magnetar having a bad day. We haven't even discussed what happens when you get close to one. Human credit: I've created part 1, exactly 1667 words. That 1 opens with an immediate hook about extreme properties. 2 follows the reference style's narrative structure and pacing. 3 establishes the documentary's voice with scientific precision mixed with accessible language. 4 uses the 1979 and 2004 detection events as narrative anchors. 5. Introduces core magnetar properties, formation, magnetic fields, density. 6. Ends with a natural transition point teasing the danger of proximity, setting up Part 2. The script maintains unpredictability through varied sentence structures, strategic information reveals, and shifts between historical narrative and scientific explanation. The ending creates anticipation for Part 2 without feeling like a traditional cliffhanger. The 1,000-kilometer threshold isn't arbitrary. It's the point where physics stops being physics as we understand it and becomes something closer to cosmic horror. At that distance, a magnetar's field strength reaches approximately 100,000 Tesla. For context, the strongest continuous magnetic field ever created in a laboratory topped out around 45 Tesla, and that required massive superconducting magnets cooled to near absolute zero. A magnetar generates fields 2,000 times stronger just by existing, and you're still 1,000 kilometers out. But here's where it gets genuinely strange. The magnetic field doesn't just pull on iron or deflect charged particles. It starts rewriting the rules that govern matter itself. Your body is made of atoms. Atoms are made of nuclei surrounded by electron clouds, those fuzzy probability distributions where electrons spend their time. In normal conditions, these clouds are roughly spherical. The electrons orbit in shells, maintaining a comfortable distance from the nucleus, and the whole arrangement is held together by electromagnetic forces that have remained constant since the universe cooled enough for atoms to form. A magnetar's field doesn't respect that arrangement. At 100,000 Tesla, electron clouds stop being spherical and start stretching into elongated cylinders. The magnetic force becomes so dominant that it overpowers the electromagnetic forces holding atoms in their familiar shapes. Hydrogen atoms, normally round, get squeezed into needle-like structures 200 times narrower than their usual diameter. This isn't metaphorical. The atoms in your body would physically deform. Every carbon atom in your DNA, every oxygen molecule in your blood, every calcium ion in your bones would stop being the shape evolution designed them to be. And when atoms change shape, chemistry changes. The chemical bonds that hold proteins together, that allow enzymes to function, that keep your cells from falling apart, all of those depend on atoms having specific geometries. Change the geometry, and the chemistry fails. You wouldn't feel pain. There's no time for pain. Your biochemistry would simply stop working, like a machine where every gear suddenly changed shape. Proteins would unfold. Cell membranes would rupture. Neural signals would halt mid-transmission. Death wouldn't come from radiation or heat or crushing gravity. It would come from the fundamental architecture of your body becoming incompatible with life. And you're still 1,000 kilometers away. The magnetar itself sits there, 12 miles wide, rotating every few seconds, completely indifferent to the fact that its mere existence has turned the surrounding space into a zone where biology cannot function. Move closer, and the effects escalate. At 500 kilometers, the field strength doubles. At 250, it doubles again. The relationship is predictable, mathematical, utterly merciless. By the time you reach 100 kilometers, assuming some impossible scenario where you survived the journey, you'd encounter field strengths approaching 10 million Tesla. At those intensities, even the vacuum becomes exotic. Empty space, the nothing between objects, starts behaving like a material. Quantum electrodynamics predicts that strong magnetic fields polarize the vacuum itself, making it birefringent. Light passing through this magnetized emptiness splits into different polarizations, bending and separating like sunlight through a crystal. The vacuum becomes less like emptiness and more like a medium with structure and properties. This isn't speculation. Astronomers have observed this effect. The light from magnetars shows polarization signatures that can only be explained by photons traveling through intensely magnetized space. The vacuum around these objects is fundamentally different from the vacuum around normal stars. It has texture. It has behavior. It is, in a very real sense, no longer empty. Photons themselves start acting strange. X-rays passing through fields this strong can split into pairs of lower energy photons or merge together into higher energy ones. The normal rules about photons being indivisible packets of light break down. In magnetar fields, light becomes mutable, transforming based on the magnetic environment it traverses. Surface conditions are even more alien. The crust of a magnetar isn't smooth. It's a lattice of atomic nuclei, mostly iron, packed so tightly that a sugar cube of the material would weigh 1 billion tons. This crust is crystalline, rigid, and under tremendous stress from the magnetic field trying to tear it apart. The field lines thread through the crust and extend into space, creating a complex magnetic topology that shifts and evolves. When the field reorganizes, it doesn't do so gently. The crust fractures. Starquakes ripple across the surface with energies that make terrestrial earthquakes look like minor tremors. A magnetar starquake registers magnitude 23 on the scale seismologists use for Earth. The 1960 Chilean earthquake, the strongest ever recorded on our planet, was magnitude 9.5. The difference represents a release of energy 10 trillion times greater. These quakes don't just shake the magnetar. They disturb the magnetic field, which snaps and reconnects like overstressed cables. The reconnection releases stored magnetic energy in sudden bursts. These are the gamma-ray flares we detect from Earth. They're the magnetar's magnetic field essentially short-circuiting, dumping vast amounts of energy into space in fractions of a second. The field doesn't just affect matter and light. It affects time. General relativity tells us that strong gravitational fields slow time, but intense magnetic fields create their own relativistic effects. Near a magnetar, the combined gravitational and magnetic stresses warp spacetime in ways that require sophisticated mathematics to describe. Clocks would run at different rates depending on their orientation relative to the field lines. Time itself becomes directional. None of this is visible to the naked eye, of course. If you could somehow observe a magnetar up close without being destroyed, it would look almost disappointingly ordinary. A dark sphere, maybe faintly glowing from residual heat. The violence happens at scales too small and energies too high for human perception. The devastation is written in warped electron clouds and fractured atomic nuclei, in polarized vacuum and split photons, in processes our senses never evolved to detect. What you would notice, if you had instruments and enough time before disintegration, is the rotation. Most magnetars spin once every 2 to 10 seconds. That seems slow compared to young pulsars, which can rotate hundreds of times per second. But remember, this is an object with more mass than the Sun compressed into a sphere the size of Manhattan, spinning fast enough that its equator moves at a significant fraction of light speed. That rotation couples with the magnetic field to create a dynamo effect, though not in the way normal stellar dynamos work. The field itself generates electric currents in the crust and the thin atmosphere of charged particles surrounding the star. These currents create additional magnetic fields, which interact with the primary field in complex feedback loops. The whole system is self-sustaining, at least for a while, powered by the magnetar's rotational energy. But that energy isn't infinite. Every time the magnetar emits a burst of radiation, it's converting rotational energy into electromagnetic energy. The star spins down, gradually slowing over thousands of years. The magnetic field decays. Eventually, after about 10,000 years, the magnetar goes quiet. The field strength drops below the threshold that makes it special. It becomes just another neutron star, still bizarre by any reasonable standard, but no longer actively terrifying. This is why we only know of 24 confirmed magnetars despite statistical models suggesting 30 million dead ones in our galaxy alone. We see them when they're young and violent. When they've calmed down, they fade into the background population of neutron stars, indistinguishable from objects that never went through a magnetic phase at all. The question that keeps physicists arguing is why only some neutron stars become magnetars. What determines whether a collapsing stellar core produces a standard neutron star or one of these magnetic monsters? The answer seems to involve rotation rates, binary companions, and the specific conditions during core collapse, but the details remain frustratingly unclear. We know magnetars exist. We can measure their properties with impressive precision. But we still don't fully understand the recipe that creates them. What we do understand is that proximity to these objects would be lethal in ways that transcend conventional danger. This isn't radiation you can shield against or gravity you can compensate for with thrust. The threat operates at the atomic level, rewriting the fundamental behavior of matter in ways that make survival impossible. The magnetar doesn't attack. It simply exists in a state incompatible with anything complex enough to be called alive. And yet, despite being the most hostile objects we've ever discovered, magnetars are teaching us things about physics we couldn't learn any other way. The extreme magnetic environment creates conditions that shouldn't exist in nature. Quantum electrodynamics predicts that empty space, true vacuum, behaves differently under intense magnetic fields. Near a magnetar, the vacuum itself becomes polarized. Light passing through this region experiences birefringence, splitting into different polarization states like it would passing through a calcite crystal. Except this crystal is made of warped spacetime and quantum fields, not mineral structure. Photons, the fundamental particles of light, do things near magnetars they don't do anywhere else. X-ray photons can split into two lower energy photons or merge with others to create higher energy ones. This isn't theoretical speculation. We observe these processes happening. The X-ray spectrum from magnetars shows features that can only be explained by photons splitting and merging in the magnetized vacuum surrounding the star. The surface itself, if you can call it that, presents another category of strangeness. Neutron star surfaces are already extreme, with gravity so intense that the highest mountains would be measured in millimeters. But magnetars add magnetic pressure to gravitational pressure, creating a competition between forces that normally don't operate on comparable scales. The result is a surface that might host structures unlike anything else in the universe. In magnetic fields exceeding 10 billion Tesla, atoms stop behaving like atoms. A hydrogen atom normally resembles a sphere, with its electron cloud distributed evenly around the nucleus. Under magnetar strength fields, that sphere compresses into a needle-shaped cylinder, stretched along the magnetic field lines. At the highest field strengths, a hydrogen atom becomes 200 times narrower than its normal diameter while maintaining roughly the same length. These elongated atoms can form chains, linking together in polymer-like structures along magnetic field lines. The magnetar's surface might be covered in a forest of atomic chains, each one perfectly aligned with the local field direction, creating a landscape of molecular needles invisible to any conventional form of observation. We can't see these structures directly. We infer their existence from the behavior of radiation passing through regions where they should exist. Temperature adds another dimension to the chaos. Young magnetars can have surface temperatures exceeding 10 million degrees Celsius. That's hot enough to emit X-rays through simple thermal radiation, independent of any magnetic effects. But the magnetic field doesn't just sit there passively. It channels the heat flow, creating hot spots at the magnetic poles where field lines converge and cooler regions at the equator. As the magnetar rotates, these hot spots sweep across our line of sight, creating the regular pulses we detect in X-rays. Every rotation, every pulse, carries information about the magnetic field geometry, the temperature distribution, and the physical state of the surface. Astronomers decode these pulses like archaeologists reading hieroglyphs, extracting meaning from patterns that repeat every few seconds. But magnetars don't just spin quietly, emitting regular pulses. They experience events that make regular pulsars look stable by comparison. Starquakes, sudden fractures in the solid crust, release energy in ways that defy easy comparison. The crust of a neutron star is crystalline, composed of atomic nuclei arranged in a rigid lattice stronger than any material we can create. When that lattice breaks, it doesn't crack gently. A starquake on a magnetar registers as a magnitude 23 earthquake on the same scale we use to measure terrestrial quakes. The most powerful earthquake ever recorded on Earth, the 1960 Chilean earthquake, measured 9.5. Each point on the magnitude scale represents roughly a 30-fold increase in energy. A magnitude 23 starquake releases more energy than trillions of nuclear weapons detonating simultaneously. The fracture propagates through the crust in milliseconds, releasing stored elastic energy and disrupting the magnetic field configuration. The field lines, locked into the crust by the star's enormous conductivity, suddenly find themselves in the wrong places. They snap into new configurations, accelerating charged particles to near light speed and generating bursts of gamma rays and X-rays that blast out into space. These giant flares, the most extreme events magnetars produce, have been observed 3 times from Earth. March 5, 1979. August 27, 1998. December 27, 2004. Each event saturated instruments across the solar system, providing brief, overwhelming glimpses into physics at its most extreme. The 2004 flare from SGR 1806-20 remains the brightest explosion ever observed from outside our solar system, at least until 2008 when a different type of event took the record. But for a magnetar 42,000 light-years away to produce the brightest flash we'd ever seen speaks to the sheer violence involved. In 1/10 of a second, that starquake released more energy than the Sun produces in 150,000 years. The gamma rays reached Earth traveling at light speed, having crossed the galaxy over 42 millennia. They hit our ionosphere and did something no astronomical event had done before. They measurably altered Earth's upper atmosphere. The ionosphere, where solar radiation strips electrons from atoms creating a layer of charged particles, suddenly gained additional ionization extending deeper than the biggest solar flares manage. Radio communications using very low frequencies were disrupted. Satellites detected the burst whether they were pointing toward the source or not, because the radiation was so intense it scattered off their structures and found its way into detectors facing the wrong direction. The Russian satellite Koronazev detected gamma rays that had bounced off the moon, highlighting just how much radiation was flooding the inner solar system. If that flare had originated from a magnetar 10 light-years away instead of 42,000, it would have destroyed Earth's ozone layer and triggered a mass extinction event. The radiation dose would have been comparable to a 12-kiloton nuclear explosion 7.5 kilometers overhead, except distributed globally and penetrating deep into the atmosphere. Fortunately, the nearest known magnetar sits 9,000 light-years away in the constellation Carina. That's comfortably distant. The inverse square law means we're safe from anything short of the most extreme possible flare. But the fact that we need to calculate safety margins for stellar objects thousands of light-years away illustrates just how energetic these events are. We understand the basic physics of starquakes. Magnetars spin down as they emit radiation, gradually slowing their rotation. As they slow, their shape changes slightly. A spinning object bulges at the equator due to centrifugal force. Reduce the spin rate, and that bulge should shrink. But the crust is solid, locked in the shape it had when spinning faster. Eventually, the stress exceeds the breaking strength of neutron star matter, and the crust fractures. What remains unclear is the exact mechanism connecting crustal fractures to giant flares. The energy released by the quake itself, enormous as it is, doesn't fully account for the observed radiation. The magnetic field must be doing additional work, tapping into its stored energy to amplify the initial disruption. Models suggest the field lines reconnect in complex cascades, similar to but far more violent than solar flares, releasing magnetic energy in addition to elastic energy. These reconnection events accelerate particles and generate the observed radiation, but the details involve plasma physics in regimes we can't replicate in laboratories. We're watching nature perform experiments at energy densities exceeding anything we can create, then trying to reverse engineer the physics from the results. Some magnetars show regular, periodic bursts less dramatic than giant flares but still remarkable. Every few rotations, they emit a burst of X-rays or soft gamma rays, suggesting something on the surface or in the magnetosphere triggers regular energy release. These soft gamma repeaters, as they're called, were the first magnetars identified, though we didn't understand what we were looking at initially. The 1979 event that saturated instruments across the solar system came from a soft gamma repeater in the Large Magellanic Cloud. At the time, we had no framework for understanding what produced such intense bursts. The magnetar hypothesis emerged more than a decade later, in 1992, when Robert Duncan and Christopher Thompson proposed that neutron stars with extreme magnetic fields could explain these observations. Their idea faced skepticism initially. Magnetic fields strong enough to power the observed emissions seemed implausibly large. But as observations accumulated and theoretical models improved, the magnetar concept gained acceptance. By the late 1990s, X-ray satellites had confirmed that soft gamma repeaters were indeed neutron stars with the predicted properties. Now we know of 24 confirmed magnetars, with several more candidates awaiting confirmation. That's a tiny sample considering our galaxy probably contains 30 million dead magnetars, objects that have spun down and cooled off, their magnetic fields decayed below the threshold that makes them special. We see the young, active ones because they're bright and violent. The old ones blend into the background population of neutron stars, indistinguishable without detailed study. This creates an observational bias. Everything we know about magnetars comes from studying the most extreme examples during their most active phase. We're trying to understand a population by examining only its most dramatic members, like trying to understand human behavior by only watching people during emergencies. The full picture remains incomplete. Yet even with this limited view, patterns emerge. Magnetars cluster in certain regions of the galaxy, particularly near star-forming areas where massive stars live and die. This makes sense. Magnetars need massive progenitors, and massive stars don't wander far from their birthplaces before exploding. The distribution tells us something about stellar evolution and galactic structure, connecting these exotic objects to the broader ecosystem of the Milky Way. What's genuinely strange is how magnetars behave compared to regular neutron stars. Take rotation. Most pulsars spin fast, some completing hundreds of rotations per second. Magnetars rotate slowly by comparison, typically once every 2 to 10 seconds. This seems backward. Both form from similar progenitor stars, both conserve angular momentum during collapse. Why do magnetars spin so much slower? The answer lies in their magnetic fields. Those extreme fields act like cosmic brakes. As the magnetar spins, its magnetic field drags through surrounding space, interacting with charged particles and electromagnetic radiation. This interaction transfers rotational energy outward, slowing the star down. The stronger the field, the more effective the braking. Magnetars have fields thousands of times stronger than typical neutron stars, so they slow down much faster. We can measure this spin down directly. Watch a magnetar over months or years, timing its pulses with precision, and you'll see the rotation period gradually lengthening. The rate of change tells us how much energy the magnetic field is radiating. For young magnetars, the numbers are staggering. They're losing rotational energy at rates that would power thousands of suns, all of it going into maintaining that monstrous magnetic field and generating the radiation we observe. This creates a life cycle. Magnetars are born spinning rapidly, their fields at maximum strength. Over millennia, they slow down as the field does work against rotation. Simultaneously, the field itself decays. The exact mechanism isn't fully understood, but we know it happens. After about 10,000 years, the field has weakened enough that the object no longer behaves like a magnetar. It becomes just another neutron star, indistinguishable from the majority unless you look very carefully. But here's where it gets interesting. Not all magnetars follow this script. SGR 0418, discovered in 2009, confused everyone. Its magnetic field measured lower than expected, yet it showed classic magnetar behavior, bursting and flaring like objects with much stronger fields. Detailed study revealed it's old, over 500,000 years, far exceeding the supposed magnetar lifetime. Somehow it retained magnetar characteristics long past the predicted cutoff. This suggests our understanding of magnetic field decay remains incomplete. Maybe the process isn't as straightforward as we thought. Perhaps internal field components, buried deep within the star where we can't measure them directly, sustain activity even after the surface field weakens. Or maybe different formation mechanisms produce magnetars with different decay timescales. We're still figuring it out. The connection between magnetars and fast radio bursts opened an entirely new chapter. Fast radio bursts, or FRBs, are millisecond duration pulses of radio waves that arrive from distant galaxies. They were discovered in 2007, and for years their origin remained a complete mystery. The bursts were too bright, too brief, too energetic to fit any known phenomenon. Dozens of explanations circulated, from colliding neutron stars to exotic physics we hadn't imagined yet. Then in April 2020, the galactic magnetar SGR 1935 plus 2154 produced a radio burst. It wasn't as bright as extragalactic FRBs, but when you corrected for distance, the energy matched. This was the smoking gun. Magnetars could produce FRBs. We'd caught one in the act, right here in our galaxy where we could study it in detail. The breakthrough came from simultaneous detection. Multiple telescopes, watching different wavelengths, all saw the burst. X-ray satellites caught a spike in high-energy radiation. Radio telescopes detected the fast radio burst. The timing matched perfectly, within milliseconds. This wasn't coincidence. Whatever mechanism generated the radio burst also produced X-rays, and it happened on a magnetar. Understanding how magnetars generate FRBs requires diving into plasma physics at extremes we can barely model. The leading idea involves magnetic reconnection in the magnetosphere, similar to what causes solar flares but incomparably more violent. Field lines snap and reconnect, accelerating particles to relativistic speeds. These particles then interact with the surrounding plasma, generating coherent radio emission through processes we're still working out mathematically. The fact that we detected this in our galaxy was lucky. Extragalactic FRBs come from distances of billions of light-years, too far to see the source directly. We can measure the radio burst, analyze its properties, but we can't watch the object that made it. SGR 1935 plus 2154 sits only 30,000 light-years away, practically next door in cosmic terms. We can monitor it continuously, watch for more bursts, correlate radio emission with X-ray activity, and slowly piece together the underlying physics. Not all FRBs come from magnetars, probably. The phenomenon might have multiple origins. But magnetars can definitely produce them, and that's a major step forward. It connects two seemingly unrelated mysteries, showing their different aspects of the same extreme physics. The diversity among magnetars themselves keeps surprising us. Some remain radio quiet throughout their lives, emitting only X-rays and gamma rays. Others turn on radio emission periodically, becoming detectable as radio pulsars for months or years before going quiet again. XTEJ 1810-197 demonstrated this dramatically. Discovered in 2003 as a radio pulsar, it shut off in 2008, remaining radio silent for a decade before suddenly reactivating in 2018. We don't know what triggers these transitions. The surface of a magnetar, if you could somehow observe it directly, would look nothing like anything familiar. The magnetic field warps spacetime itself at those scales. Atoms deform into needle-like structures, stretched along field lines. At field strengths above 10 to the 10th Tesla, hydrogen atoms become 200 times narrower than their usual diameter. These elongated atoms can link up, forming polymer-like chains across the surface. The vacuum surrounding a magnetar isn't empty in any normal sense. Quantum electrodynamics predicts that strong magnetic fields polarize the vacuum, making empty space behave like a birefringent crystal. Light passing through this region splits into different polarization modes that travel at slightly different speeds. We've actually observed this effect, measuring how light from magnetars becomes highly polarized in ways that match theoretical predictions. Photons themselves behave strangely near magnetars. X-ray photons can split into pairs or merge together, processes that occur rarely in normal space but become common in extreme magnetic fields. The vacuum becomes an active medium, interacting with radiation in ways that seem almost like science fiction but follow directly from established physics pushed into regimes nature rarely explores. Getting close to a magnetar would be immediately fatal, and not just from radiation. The magnetic field itself would kill you at a distance of 1,000 kilometers. At that range, the field strength reaches levels that distort electron clouds in atoms. Your biochemistry would simply stop working. Molecular bonds would break. The electrical signals in your nervous system would scramble. You'd die before radiation exposure became the primary concern. Even at the distance of the moon from Earth, a magnetar could erase every credit card on the planet. The magnetic field extends that far with enough strength to affect magnetic storage. This gives you some sense of the field's sheer reach, how it dominates space around the object in ways no other astrophysical phenomenon can match. We've never observed a magnetar forming directly. The birth happens inside a supernova, hidden by expanding debris, and by the time we can see inside, the magnetar already exists, spinning down from its initial rapid rotation. But we have observed what might be the next best thing, a supernova that stayed bright far longer than it should have, powered by something inside the expanding cloud. Superluminous supernovae, as they're called, radiate 10 to 100 times more energy than normal supernovae. The expanding debris doesn't contain enough radioactive material to power that luminosity through decay alone. Something else provides the energy. The leading explanation involves a magnetar. If the collapsed core becomes a rapidly spinning magnetar instead of a black hole, it pumps enormous energy into the surrounding supernova debris through its magnetic field and relativistic wind. This additional energy source keeps the supernova bright long after it should have faded. One recent supernova provided particularly strong evidence. The light curve, the graph showing how brightness changed over time, matched predictions for magnetar-powered emission almost perfectly. As the magnetar spun down, transferring its rotational energy outward, the supernova faded at exactly the predicted rate. This wasn't definitive proof, we can't see inside to confirm the magnetar's presence, but the fit was too good to ignore. If correct, this means we're watching magnetars form in real time, or at least watching their immediate aftermath. The object itself remains hidden, but its influence shapes everything around it, announcing its presence through the enormous energy it injects into its surroundings. The evidence keeps building. Astronomers have now cataloged multiple superluminous supernovae whose light curves match magnetar-powered models. Each case strengthens the connection between these ultra-bright explosions and rapidly spinning neutron stars with extreme magnetic fields. But here's what makes this particularly fascinating. We might be watching different stages of the same process playing out across the universe. Some superluminous supernovae fade quickly after their peak, suggesting the magnetar inside spun down rapidly and lost its ability to inject energy. Others remain bright for months, implying a more gradual energy release. The variety tells us that magnetar formation isn't a single uniform process but depends on initial conditions we're still working to understand. Rotation rate, magnetic field strength, the mass of surrounding material, all these factors influence what we observe. Then there's the question of what happens next. Does every magnetar eventually become a quiet neutron star, its magnetic field decayed beyond detection? Or do some follow different evolutionary paths? We have hints that the story might be more complex than simple decay. SGR 0418 provides one clue. This magnetar is old, more than 500,000 years, yet it still exhibits magnetar-like behavior. Most magnetars should have quieted down long before reaching that age, their magnetic fields weakened to the point where they no longer power detectable bursts. Something about this object defies our standard models. Perhaps its internal structure differs from typical magnetars. Perhaps the decay process isn't as straightforward as we thought. The population of known magnetars remains small. As of recent counts, we've confirmed only about 24. That seems remarkably few given how many neutron stars must exist in our galaxy. The math suggests tens of millions of dead neutron stars scattered through the Milky Way, most of them invisible, no longer emitting radiation we can detect. How many of those were once magnetars? How many went through an active phase thousands of years ago and now sit dark and silent? This gets at something fundamental about astronomical observation. We only see objects during specific phases of their lives, brief windows when they shine brightly enough to notice. Magnetars give us perhaps 10,000 years of visibility before fading into obscurity. That's nothing on cosmic timescales. We're essentially catching glimpses of these objects during their youth, missing the vast majority that have already grown old and quiet. Fast radio bursts changed the game. These millisecond duration pulses of radio emission were first detected in 2007, but their origin remained mysterious for over a decade. Theories ranged from colliding neutron stars to exotic phenomena we'd never imagined. Then in 2020, everything clicked into place. A magnetar in our own galaxy, SGR 1935 plus 2154, produced a radio burst. Not just any burst, one that matched the characteristics of fast radio bursts detected from distant galaxies. The timing couldn't have been better. Multiple radio telescopes were monitoring the sky when the burst occurred, and they caught it simultaneously with an X-ray flare from the same magnetar. For the first time, we had direct evidence linking magnetars to fast radio bursts. The burst itself was relatively weak compared to extragalactic examples. If it had occurred in another galaxy, we might not have detected it at all. But its proximity, just 30,000 light-years away, made it the brightest fast radio burst ever observed from Earth. More importantly, it proved that magnetars can produce these mysterious signals. What causes the bursts remains unclear. The leading explanation involves the magnetar's magnetic field suddenly reconfiguring, perhaps during a starquake, and accelerating charged particles to extreme energies. These particles then emit coherent radio emission as they stream away from the star. It's similar to how pulsars generate radio beams, but far more intense and violent. Not every magnetar produces detectable radio bursts. Most remain radio quiet throughout their observable lifetimes, emitting only X-rays and gamma rays. The ones that do produce radio emission might be going through specific phases in their evolution, perhaps when their magnetic fields have particular configurations or when starquakes occur at certain rates. We're still mapping out these relationships. The 2020 detection opened new questions faster than it answered old ones. If magnetars produce fast radio bursts, why do we detect thousands of bursts from distant galaxies but only one from a nearby magnetar? Are the extragalactic bursts somehow different, more energetic versions of what we observed from SGR 1935 plus 2154? Or are multiple mechanisms at work, with magnetars being just one of several sources? Some fast radio bursts repeat, sending out multiple pulses over weeks or months. Others appear once and never again. The repeating ones might come from young magnetars still going through active phases, experiencing frequent starquakes that trigger burst after burst. The one-off events could be older magnetars producing a single catastrophic burst before falling silent. Distance measurements for fast radio bursts reveal something unexpected. Some originate from galaxies billions of light-years away, meaning the bursts we detect today were produced when the universe was significantly younger. These ancient magnetars, if that's what they are, formed from stars that lived and died long before our solar system existed. Their radio signals have been traveling through expanding space for eons, finally reaching our telescopes after journeys spanning most of cosmic history. The energy requirements boggle the mind. A typical fast radio burst releases as much energy in a few milliseconds as the sun emits in several days. And these are just the ones we can detect across billions of light-years. Weaker bursts surely exist, too faint to reach us from such distances, meaning the actual rate of these events throughout the universe is higher than our observations suggest. Magnetar mergers offer another formation pathway. When two neutron stars spiral together and collide, the most common outcome is a black hole. The combined mass exceeds the limit that neutron matter can support, and collapse becomes inevitable. But in some cases, particularly when the neutron stars aren't too massive, the merger might produce a hypermassive neutron star that survives for seconds or even minutes before collapsing. During that brief existence, the merged object spins incredibly fast, hundreds of times per second, and possesses an enormous magnetic field created during the violent merger process. It's essentially a temporary magnetar, living fast and dying young. The energy it releases during those final moments could power some of the brightest explosions we observe, including certain gamma-ray bursts. We detected gravitational waves from a neutron star merger in 2017, the first confirmed observation of such an event. The aftermath produced a gamma-ray burst and a kilonova, a bright optical and infrared glow powered by radioactive decay of heavy elements synthesized during the merger. But some theoretical models suggest a magnetar might have existed briefly between the merger and final collapse, injecting additional energy into the system before vanishing. Testing this idea requires catching another merger and studying its aftermath in exquisite detail. The challenge is timing. Neutron star mergers are rare, perhaps 1 per 100,000 years in a typical galaxy. We need to be watching the right patch of sky at precisely the right moment, with instruments capable of detecting multiple wavelengths simultaneously. It's astrophysical detective work at the highest difficulty level. One magnetar stands out for purely observational reasons. XTEJ 1810-197 became the first magnetar detected as a radio pulsar, emitting regular pulses like the more common variety of neutron stars. This was unexpected. Magnetars weren't supposed to be radio pulsars. Their emission mechanisms seemed fundamentally different from the lighthouse-like beams that ordinary pulsars sweep across space. The discovery forced a rethink. Maybe magnetars aren't as distinct from other neutron stars as we thought. Maybe there's a continuum, with magnetic field strength varying smoothly across the population rather than falling into discrete categories. Some neutron stars might straddle the boundary, exhibiting properties of both standard pulsars and magnetars depending on their evolutionary state. XTEJ 1810-197 varies in unexpected ways. Sometimes its radio emission strengthens, sometimes it fades, and occasionally it disappears entirely for months or years before returning. This variability suggests something dynamic happening on or near the star, perhaps changes in the magnetic field geometry that alternately open and close pathways for radio emission to escape. Understanding these transitions matters. If magnetars can switch between radio loud and radio quiet states, we might be missing many of them in surveys that only look for X-ray emission. A census that counts only the noisiest members of a population inevitably underestimates the total number. The true magnetar population could be significantly larger than current estimates suggest. Their ultimate fate remains uncertain. After 10,000 years, a magnetar's field weakens to the point where it no longer powers detectable bursts. It becomes, for all practical purposes, an ordinary neutron star, spinning slowly through space, radiating only faint thermal emission from its cooling surface. Over millions of years, it grows colder and dimmer, eventually becoming invisible to all but the most sensitive instruments. Some might experience brief revivals. A collision with another object, even something as small as an asteroid, could potentially trigger renewed activity, jolting the magnetic field into a temporary excited state. But such events would be exceedingly rare, and any activity they produce would pale compared to the magnetar's youth. The galaxy contains a vast graveyard of these objects, invisible neutron stars that once blazed as magnetars but now drift silently through interstellar space. They're out there, thousands of them, maybe millions, carrying in their structure the memory of violent births and brief spectacular lives. We'll never see most of them. They've moved beyond our ability to detect, joining the dark matter that fills the cosmos. Yet studying these remnants teaches us something fundamental about the universe itself. Magnetic fields permeate everything we see, from planetary cores to galactic structures spanning millions of light-years. Understanding how they behave at magnetar intensities pushes physics into regimes we can't replicate in laboratories. The equations that describe these fields appear simple, but their solutions reveal complexity that surprises even theorists who've spent careers working with them. Consider what happens to empty space itself near a magnetar. Quantum mechanics tells us that vacuum isn't truly empty but seethes with virtual particles constantly appearing and disappearing. In normal conditions, these quantum fluctuations have no observable effect. But a magnetar's field is strong enough to polarize the vacuum, making it behave like a crystal that bends light differently depending on its polarization. Photons traveling through this warped space can split into pairs or merge together, processes that sound like science fiction but follow directly from well-tested quantum field theory. The implications extend beyond magnetars themselves. Similar physics might operate in other extreme environments we've barely begun to explore. The collision of two black holes, the surface of strange quark stars if they exist, or the cores of the most massive neutron stars might all generate fields approaching magnetar strength for brief moments. Each of these scenarios tests our theories in different ways, revealing whether our understanding holds up under conditions far removed from everyday experience. Magnetars also challenge our assumptions about stellar evolution. We thought we understood how massive stars end their lives. They burn through their fuel, collapse, explode, and leave behind either a neutron star or a black hole depending on their mass. This picture remains broadly correct, but magnetars add nuance. Not every massive star explosion produces the same kind of neutron star. Small differences in rotation, magnetic field strength, or binary interactions can push the outcome in dramatically different directions. The detection of fast radio bursts changed everything. These millisecond-long pulses of radio waves arrive from distant galaxies, carrying energy that seems impossible to generate through conventional means. When SGR 1935 plus 2154 produced a fast radio burst in 2020, it confirmed what many had suspected but couldn't prove. Magnetars can generate these signals, at least some of them, through mechanisms we're still working to understand fully. The discovery didn't solve the mystery completely. Some fast radio bursts repeat regularly, others appear once and never again. Some come from galaxies billions of light-years away, others from relatively nearby. The diversity suggests multiple formation mechanisms might be at work, with magnetars representing one path among several. But having one confirmed source gives us a starting point, a known physics laboratory we can study in detail. What makes a magnetar produce a fast radio burst? The leading theory involves sudden rearrangements of the magnetic field near the star's surface, creating conditions that accelerate particles to extreme velocities. These particles emit coherent radiation as they spiral through the twisted field lines, producing the brief intense pulses we detect. The details remain murky. Field line reconnection, crustal fractures, or oscillations in the magnetosphere might all contribute, possibly working together in ways current models don't capture. Testing these ideas requires better instruments. Current telescopes can detect fast radio bursts and measure their properties, but they can't resolve fine details about their emission regions. Next-generation facilities now under construction will have the sensitivity and time resolution to catch the subtle variations that reveal underlying mechanisms. We're entering an era where these objects transition from mysterious phenomena to physics laboratories we can actually probe. The connection between magnetars and fast radio bursts also suggests something profound about the universe's evolution. These bursts travel across billions of light-years, carrying information about the space they traverse. As the radio waves pass through ionized gas between galaxies, they disperse slightly, with different frequencies arriving at fractionally different times. Measuring this dispersion tells us about the density of matter along the line of sight, providing a new tool for mapping the universe's large-scale structure. Young magnetars might play another role we're only beginning to appreciate. When a massive star explodes, it doesn't just create a neutron star. It also drives shock waves through surrounding material, heating gas to millions of degrees and accelerating cosmic rays to energies that dwarf anything we can produce in particle accelerators. A newly formed magnetar, spinning rapidly and radiating enormous power, could inject additional energy into this environment, affecting how the supernova remnant evolves over thousands of years. Some superluminous supernovae, explosions that outshine their entire host galaxies, might be powered by central magnetars. The standard supernova mechanism, where the collapsing core rebounds and blows off the star's outer layers, can't explain the extreme brightness of these events. But a magnetar spinning hundreds of times per second could pump energy into the expanding debris for weeks or months, making it glow far brighter than ordinary supernovae. Observations support this idea without yet confirming it definitively. The magnetic field itself might contribute to the explosion. Simulations suggest that in rapidly rotating collapse scenarios, magnetic fields can channel energy outward along the rotation axis, creating powerful jets that punch through the star before the rest of it has time to explode. These magnetar-driven jets might explain certain rare supernova types that show unusual geometric patterns in their debris, elongated structures pointing in opposite directions rather than the roughly spherical shells produced by standard explosions. Each new observation refines our understanding while raising fresh questions. Why do some magnetars produce giant flares while others remain relatively quiet? What determines the initial magnetic field strength in the first place? Can we predict which massive stars will become magnetars rather than ordinary pulsars? The answers matter for more than academic curiosity. They tell us how elements heavier than iron form and spread through galaxies, how magnetic fields thread the cosmos, and what extreme physics looks like when pushed to its breaking point. The nearest magnetar sits 9,000 light-years away, far enough that even its most powerful outburst poses no threat to Earth. We're safe, at least from known magnetars. But the galaxy contains stellar nurseries where new massive stars are forming continuously, future magnetars waiting to be born. In a million years, one of them might explode relatively nearby, creating a magnetar we could study in unprecedented detail. Or it might have happened already, with the light from that explosion still traveling toward us through interstellar space. What we learn from magnetars feeds back into broader questions about the universe. How common are these objects in other galaxies? Do they contribute significantly to the mysterious high-energy backgrounds we detect? Could ancient magnetar flares have influenced Earth's atmosphere in the distant past, leaving traces we haven't yet recognized? Each question opens new research directions, connecting stellar physics to planetary science to cosmology in unexpected ways. The technology we develop to study magnetars often finds applications elsewhere. Detectors sensitive enough to catch their faint X-ray pulses can also track other high-energy phenomena. Analysis techniques that extract signal from noise and their burst data improve our ability to find gravitational waves or exoplanet transits. Theoretical tools that model their magnetic fields advance our understanding of plasma physics in fusion reactors and solar flares. Pure research rarely stays pure for long. Magnetars remind us that the universe operates on scales both incomprehensibly large and impossibly small, where city-sized objects generate magnetic fields that warp the fabric of spacetime itself, where quantum mechanics and general relativity both play crucial roles, and where the physics we've worked out in comfortable laboratories faces its ultimate test. They're not just exotic curiosities. They're natural laboratories pushing matter and energy to extremes we can barely imagine, revealing what's possible when nature stops holding back. Every active magnetar we know about will eventually fall silent. The magnetic field that defines them, that makes them the most extreme objects we can observe, decays over millennia until nothing remarkable remains. 10,000 years from now, the magnetars currently terrorizing their neighborhoods will be indistinguishable from ordinary neutron stars, spinning quietly in the dark, their violence spent. This creates a peculiar situation. We're living during a brief window when these objects are visible, when their youth makes them loud enough to detect across thousands of light years. The galaxy has hosted magnetars for billions of years, but we only see the current generation, the ones active right now. The rest are ghosts, invisible remnants carrying the memory of power they no longer possess. Statistical models suggest 30 million dead magnetars populate the Milky Way. 30 million objects that once commanded their surroundings through sheer magnetic force, now drifting through space contributing nothing but gravitational pull. They haven't disappeared. They've just moved beyond our ability to notice them, joining the vast population of stellar corpses that fill the space between stars. The ones we can study tell us something fundamental about how the universe operates at extremes. Physics textbooks describe magnetic fields using equations derived from experiments with bar magnets and current-carrying wires. Those equations work perfectly for everyday applications. They even work for most astronomical contexts, from planetary magnetospheres to the fields threading galactic arms. But magnetars exist at the edge of validity, where the equations themselves start showing strain. Near a magnetar, quantum mechanics and general relativity both become essential for describing what happens. You can't ignore either one. The magnetic field warps spacetime measurably. Quantum effects alter how light propagates through vacuum. The object sits at the intersection of physics regimes that normally operate independently, forcing them to work together in ways we're still learning to calculate correctly. This makes magnetars valuable beyond their intrinsic interest. They're testing grounds for theories we can't validate any other way. Want to know how matter behaves at nuclear densities under magnetic fields a quadrillion times Earth's? Find a magnetar and measure its emission spectrum. Curious whether quantum electrodynamics holds up when electromagnetic field energies exceed particle rest mass energies? Watch how X-rays propagate through magnetar magnetospheres. These aren't Gedanken experiments. They're real observations probing real physics in regimes laboratories will never reach. The connection to fast radio bursts transformed magnetars from obscure specialists' objects into key players in modern astrophysics. Before 2020, fast radio bursts were one of astronomy's deepest mysteries, bright millisecond pulses arriving from distant galaxies with no confirmed source. Multiple theories competed, some invoking exotic physics we'd never observed. Then SGR 1935 plus 2154 produced a burst, and suddenly we had an answer. Not the only answer, perhaps, but a confirmed mechanism that worked. This pattern repeats throughout science. A phenomenon appears mysterious until we catch it in the act, then everything clicks. Magnetars went from hypothetical to confirmed through patient observation and theoretical development. Fast radio bursts followed a similar arc. Now we're watching both fields mature, moving from discovery to detailed characterization, from asking, "What are these?" to asking, "How exactly do they work?" The answers will come from better instruments and smarter analysis, but also from luck. Magnetar giant flares are rare. We've observed 3 in modern astronomical history. The next one might happen tomorrow or might not happen for decades. When it does, having instruments pointed in the right direction with the right sensitivity to capture every detail could transform our understanding overnight. Or we might miss it entirely, left with fragmentary data from satellites that weren't designed for this purpose. Some questions won't wait for lucky observations. The theoretical work continues independently, pushing deeper into the mathematics of magnetic field evolution, crustal fracture mechanics, and quantum vacuum effects. Computer simulations improve year by year, incorporating more physics and running at higher resolution. Each advance reveals new complexity, new phenomena that observations will eventually need to confirm or refute. We're essentially trying to reconstruct the biography of objects that live fast and die young by cosmic standards. A magnetar's active lifetime spans 10,000 years, a blink compared to the billions of years typical stars enjoy. During that brief window, they experience violent starquakes, emit radiation that crosses galaxies, and demonstrate physics that nothing else in nature provides access to. Then they fade, leaving behind only their mass and gravity. Understanding this life cycle connects to broader questions about stellar evolution and galactic ecology. Massive stars create most elements heavier than helium through fusion and supernova nucleosynthesis. When they collapse into neutron stars, magnetars included, they remove that material from circulation temporarily. Eventually, given enough time, even neutron stars might decay through quantum processes, returning their mass to the universe in forms we can only speculate about. But that's trillions of years away, far beyond anything we can observe directly. In the meantime, magnetars continue doing what they do best, being dangerous, dramatic, and scientifically invaluable. Every burst we detect, every pulse we time, every spectrum we analyze adds another piece to the puzzle. The picture emerging shows a universe more violent and more interesting than we imagined, where dead stars can terrorize their neighborhoods for millennia and where the strongest magnetic fields in existence emerge from stellar corpses no bigger than cities. The galaxy contains wonders we're only beginning to catalog. Magnetars rank among the most extreme, pushing matter and fields to limits that seem designed to test our theories. They're not the only exotic objects out there, but they might be the most thoroughly hostile to anything complex enough to observe them. From 1,000 kilometers away, your atoms would deform. From halfway to the moon, your credit cards would erase. From 42,000 light-years, they can disrupt Earth's ionosphere with a single bad day. That's the universe we inhabit. One where stellar remnants command physics that shouldn't exist, where quantum mechanics warps vacuum into optical crystals, and where the brightest explosions since the Big Bang happen regularly in objects smaller than the island of Manhattan. Magnetars aren't comfortable. They don't fit into neat categories. They challenge our assumptions about what's possible. And somewhere out there, hidden in the stellar nurseries where massive stars are being born right now, future magnetars are waiting. Stars that will live brilliantly for a few million years before collapsing into objects we'll study with instruments that haven't been invented yet. The cycle continues, generation after generation, creating laboratories that test physics at its breaking point and reminding us that the universe operates on scales we're only beginning to comprehend.